Close your eyes, or let them rest halfway open. Tonight we are not going anywhere on Earth. We are going back. Further back than memory. Further back than history. Further back than the first flicker of life on this planet. We are going back to the very beginning of everything that has ever existed. Let your body sink into the bed beneath you. Let your breathing slow. There is nothing you need to do right now, except listen and drift, while we walk gently through the birth of the universe itself. Before we can talk about stars, or planets, or galaxies, we have to talk about something much stranger. We have to talk about the moment before any of those things were possible. A time so early, so strange, that the normal words we use for time and space start to lose their meaning. It is hard to picture, but that is all right. You do not need to picture it perfectly. You only need to let the story wash over you, the way warm water washes over tired muscles, slowly, gently, without any hurry at all. Scientists tell us the universe began about 13.8 billion years ago. That number comes from careful measurements of how fast the universe is expanding and how old the oldest light in the sky appears to be. 13.8 billion years is such a large number that it stops meaning anything to our minds. So let us not try to hold the whole number at once. Let us simply start at the start and move forward one small step at a time, the way you might climb down a staircase in the dark, one stair, then the next, feeling your way with your hand on the rail. The very first step is the strangest one of all, so we will move through it slowly and gently, and then things will start to feel a little more solid, a little more like the universe we know. Think for a moment about how ordinary your evening probably was. Maybe you brushed your teeth. Maybe you checked the time. Maybe you pulled a blanket up over your shoulders and felt the small, familiar comfort of a bed that knows the shape of you. None of that seems connected to galaxies or ancient light, and yet every atom in your hand, every atom in the blanket, every atom in the walls around you has a history stretching back to the very first moments we are about to describe. You are not separate from this story. You are, in a very real and very literal sense, made of it. Understanding where the universe came from is also understanding where you came from, all the way down to the smallest pieces of you. So let this be less like a lecture and more like a long, slow exhale. There is no test at the end of this. There is nothing you need to remember. If your mind starts to drift, if your eyelids grow heavy, if you lose the thread of a sentence halfway through, that is not a failure. That is exactly what this story is for. Asterisk. The question of what came before. Almost everyone who first hears about the Big Bang asks the same question. What happened before it? It feels like the most natural question in the world. Every event we know of has something that came before it. A seed comes before a tree. A spark comes before a fire. So surely something must have come before the beginning of everything. But here is where the universe surprises us. According to our best understanding of physics, the Big Bang was not just the beginning of matter and space. It was the beginning of time itself. Before time existed, there was no before. Not empty space, not darkness, not silence waiting. Time itself had not yet begun, so there was no timeline for anything to sit on. Physicists sometimes compare this to a much simpler question. What lies north of the North Pole? You cannot answer that question by pointing to some hidden place beyond the pole. There is no such place. North is a direction that only makes sense once you are somewhere south of the pole. Once you reach the pole itself, the idea of north simply runs out of meaning. It is not that the answer is hidden from us. It is that the question stops making sense at that point. Time may work the same way. As you trace the universe backward, getting closer and closer to its beginning, the concept of before may simply run out, the same way north runs out at the pole. This is not a dodge or a trick to avoid a hard question. It is one of the most carefully reasoned ideas in modern physics, and respected scientists such as Stephen Hawking help develop this way of thinking about it. I want to be honest with you here, the way I try to be honest in every one of these videos. This is not a settled question. Some physicists suspect that something did exist before our universe's expansion began, perhaps an earlier phase of the same universe, or perhaps a much larger structure that our universe is only a small part of. Ideas like the no-boundary proposal, developed by physicists James Hartle and Stephen Hawking in the 1980s, suggest that if you could rewind time back toward the beginning, time would not hit a wall the way a road hits a cliff edge. Instead, it would gradually behave more and more like a dimension of space, the way the very idea of south quietly loses its meaning once you actually stand at the South Pole. In this picture, the universe does not have a ragged edge that needs explaining. It is simply, quietly, whole, the way a sphere has no starting point on its surface, no matter where you begin tracing it. Other physicists have proposed different pictures entirely. Some suggest our universe may have emerged from the collapse of an earlier one, in what is sometimes called a bouncing universe, where expansion and contraction repeat across unimaginable stretches of time. One universe's ending quietly becoming the next universe's beginning. Others, drawing on string theory, imagine our universe as one bubble among countless others, each with its own laws of physics, most of them perhaps too hostile to ever support anything like a star or a planet, or a mind capable of wondering about any of it. None of these ideas have been confirmed by observation. They remain for now careful speculation built on solid mathematics, not proven fact. Serious scientists disagree with one another about which, if any, of these pictures is correct, and some suspect we may never have the tools to know for certain. What is far more certain is this: our equations, our physics, our ability to describe what happened, all of it breaks down as we approach the very first sliver of time. We simply cannot see past that point with the tools we have today, and we may never be able to. There is a kind of humility built into the best science, a willingness to say clearly, this is where our knowledge ends, without pretending otherwise. So let us begin exactly there, at the edge of what we can describe, and step forward together into the story that science can actually tell us. The Planck Epoch, the edge of knowing, in the first tiny fraction of a second, so small that it is almost impossible to picture, the universe existed in a state that no current theory can fully explain. Scientists call this the Planck Epoch. It lasted from the very first moment up to about 10 to the negative 43 seconds. That is a decimal point followed by 42 zeros and then a 1. It is a length of time so short that comparing it to a single second is like comparing a single second to many times the entire age of the universe. During the Planck Epoch, physicists believe that all four of the fundamental forces of nature, the ones that shape everything in the universe today, gravity, electromagnetism, and the two nuclear forces, were joined together as a single unified force. Temperatures and densities were so extreme that the rules of general relativity, the same rules that describe gravity, and the shape of space itself, stopped working. We would need a complete theory of quantum gravity, joining Einstein's description of gravity with the strange rules of quantum mechanics. To describe this moment properly, that theory does not exist yet. Scientists are working on candidates, ideas like string theory and loop quantum gravity, but none of them have been confirmed. So when I tell you what happened during the Planck Epoch, understand that I am describing the edge of human knowledge, not a settled fact. It is a place where our best science quietly raises its hand and says, honestly, we do not know yet. There is something deeply comforting in that honesty. The universe still holds mysteries. We have not run out of things to wonder about. Try to imagine, just for a moment, a length of time so short that if you stretched the entire age of the universe out to fill a single year, the Planck Epoch would be over before the year had even begun to tick forward, faster than any measurement could register, faster than the idea of fast can really hold. Numbers like 10 to the negative 43 seconds are easy to write down and almost impossible to actually feel. Perhaps the gentlest way to hold this idea is simply to accept that it is not meant to be felt, only trusted. The way you trust that the ocean has a floor you will never personally touch. Some things in this universe exist at scales built for equations, not for imagination, and that is perfectly all right. We can still stand at the shore of that vast idea and feel something like wonder, even without touching the bottom. Inflation, the great stretching, just after the Planck Epoch, something remarkable happened. Something that most cosmologists consider one of the best supported ideas about the early universe, even though a few of its details are still debated. Physicist Alan Guth proposed this idea in the early 1980s, and it is called cosmic inflation. For an incredibly brief moment, somewhere between about 10 to the negative 36 seconds and 10 to the negative 32 seconds after the beginning, the universe expanded at a staggering, almost unbelievable rate. In that tiny sliver of time, the universe grew by a factor of at least 10 to the 26th. To put that into words, imagine something smaller than a single atom swelling, in far less than the blink of an eye, to a size you could hold in your hand, roughly the size of a grapefruit. That growth happened not because matter was flying outward through space, the way debris flies outward from an explosion. It happened because space itself was stretching, expanding in every direction at once, carrying everything within it along for the ride. This is an important distinction, and it will matter again later in our story, so let us sit with it for a moment. Special relativity tells us that nothing can travel through space faster than the speed of light. But inflation did not involve anything moving through space. It involved space itself growing, and general relativity places no such speed limit on the growth of space. 2 points in the universe can move apart from the other faster than light without either of them ever actually moving through space at all. It is a strange idea, but it is a real and well-supported part of physics. Why do scientists believe inflation happened if we cannot see it directly? Because it elegantly solves several puzzles that would otherwise be very hard to explain. One of these is called the horizon problem. When we look at the cosmic microwave background, the ancient light we will talk about later in this chapter, we find that it has almost exactly the same temperature in every direction we look, even in directions that under ordinary expansion would never have been in contact with each other, would never have had time to exchange heat and settle into the same temperature. Inflation solves this by suggesting that all these regions were once close together, in contact, before the great stretching carried them far apart. Inflation also explains why the universe looks so remarkably flat on the largest scales, rather than curved in the way that a sphere or saddle might be curved. A brief period of enormous expansion would smooth out any curvature almost perfectly, the same way stretching a small wrinkled balloon into an enormous size would make its surface look almost perfectly flat to something standing on it. In 2014, a team working with a telescope called BSEP-2 announced they had found direct evidence of inflation in the form of a particular pattern in the cosmic microwave background that could have come from gravitational waves generated during that early stretching. That particular claim was later found to be affected by cosmic dust rather than a clean signal of inflation itself, and the finding was walked back after further analysis. This is worth mentioning, honestly, because it shows how science actually works. Scientists proposed an exciting result, other scientists checked it carefully, and the community adjusted its conclusions based on the evidence. The search for a clean, confirmed signature of inflation in the cosmic microwave background continues today, and it remains one of the most sought-after prizes in cosmology. Even without that particular piece of direct evidence, the broader case for inflation remains strong, supported by how well it explains the flatness and uniformity we observe. It is currently the leading explanation, even if some specific details are still being worked out and refined. There is something almost tender about this part of the story, if you let yourself feel it. In that first unimaginable instant, tiny quantum fluctuations, the smallest possible ripples allowed by the strange rules of quantum mechanics, were stretched by inflation from the microscopic scale up to the size of galaxies. Those tiny ripples became the seeds for every structure that would ever exist, every star, every galaxy, every planet, every person who would ever look up at the night sky and wonder where it all came from. The unevenness that would one day become you and me was written into the universe in that first fraction of a second, long before there was anything you could call matter at all. Picture the smoothest, calmest lake you have ever seen. its surface so still it looks almost solid, mirroring the sky perfectly. Now imagine that lake being stretched, gently but immensely, across an area larger than anything you could walk in 100 lifetimes, and every tiny ripple that had been sitting on its original surface stretching along with it, growing from something barely visible into something vast. That, the softest possible language, is something like what inflation did to the fabric of the early universe. The smallest quantum trembling, the kind of flicker that would normally vanish before it was ever noticed, was carried outward and preserved, frozen into the geometry of space itself, waiting patiently for billions of years until gravity was ready to use it. By the time inflation finished its brief, explosive work, the universe had grown from something far smaller than a single proton into a space many times larger than anything we can observe, even with our most powerful telescopes today. And it had done this without violating a single law of physics, without a single spark of matter moving faster than light, simply by letting space itself do what space, apparently, is capable of doing under the right conditions. It is one of the strangest and most quietly astonishing facts in all of science, and it happened before the universe was even a trillionth of a second old. Asterisk, a soup of pure energy. Once inflation ended, the universe kept expanding, though now at a far gentler pace compared to what had just happened. It was still unimaginably hot and dense, glowing with an almost incomprehensible amount of energy packed into a tiny volume. There were no atoms yet. There were not even any protons or neutrons yet. The universe at this stage was a formless, seething soup of fundamental particles and pure energy, constantly transforming from one form to another, so hot that particles could not hold together in any stable way. As the universe continued expanding, it also continued cooling, because expansion and cooling go hand in hand. Think of a gas escaping from a can. As it spreads out, it cools. The universe followed the same basic pattern on a scale beyond imagining, and as it cooled, it passed through a series of transformations, almost like a substance changing from one state to another, from gas to liquid to solid. Except here the transformations were far more fundamental than that. They were changes in the very nature of matter itself. One of the most important of these transformations is something called the quark-gluon plasma. In the first millionths of a second after the beginning, the entire universe was filled with a blazing hot soup of particles called quarks and gluons, unable to bind together the way they do today. Quarks are the tiny building blocks that make up protons and neutrons, and gluons are the particles that carry the force which normally holds quarks tightly together. But at these extreme temperatures, estimated by researchers to have reached around 4 trillion degrees Celsius, roughly 250,000 times hotter than the core of our Sun, quarks and gluons moved around freely, unbound, like a liquid or a gas, rather than being locked inside particles. Scientists have actually recreated tiny amounts of quark-gluon plasma here on Earth, smashing heavy atomic nuclei together at enormous speeds inside particle accelerators, such as the relativistic heavy ion collider in New York and the Large Hadron Collider in Europe. These experiments only produce quark-gluon plasma for the briefest possible flash of time, far less than a second, but they allow physicists to study its properties directly, measuring things like its temperature and how it flows, almost like a fluid with a strange and specific thickness. Researchers have used these experiments to measure the plasma's temperature at different stages, with average values around 2 trillion Kelvin in some ranges and higher in others, helping build a detailed picture of conditions in the earliest universe. This state of matter could not last. As the universe continued expanding and cooling, it dropped below a critical temperature, estimated to be somewhere around 150 to 170 million electron volts of energy. A strange but standard way physicists measure such enormous temperatures. This happened when the universe was only about 20 millionths of a second old. At that point, something like a phase transition took place, similar in spirit to water freezing into ice, though far more exotic. The free-roaming quarks and gluons suddenly became bound together, locked into new particles. This was the birth of protons and neutrons, the two building blocks that would eventually form the nucleus of every atom in existence. It can help to think of this transition the way you might think of steam turning into water droplets on a cold window. One moment the water molecules are spread apart, moving freely, mixed in with the air, invisible. The next moment, as the temperature drops just enough, they suddenly cling together, forming something new, something you can actually see and touch. The transition from quark-gluon plasma into protons and neutrons was something like that, except it happened everywhere in the universe at almost exactly the same time. An enormous, simultaneous condensation spread across the whole of existence, locking the fundamental particles of matter into the shapes they would carry for the rest of cosmic history. Scientists studying quark-gluon plasma in laboratories today describe it as behaving almost like a fluid, one with remarkably little internal resistance, flowing more smoothly than almost anything else ever measured. For a few millionths of a second, the entire universe was made of that same strange flowing substance. Asterisk. The first heavy particles form, protons and neutrons, are what physicists call baryons, particles made from three quarks bound tightly together by the strong nuclear force. Once the universe cooled below that critical threshold, quarks stopped roaming freely and became trapped inside these new particles, unable to escape their bonds under normal conditions ever again. This moment marked the true beginning of what we would recognize as ordinary matter, the same kind of matter that makes up your body, this bed you may be lying in, the air in the room around you, and every star and planet in the sky. For a good while after this, the young universe remained a blisteringly hot mixture of protons, neutrons, electrons, and other particles, along with enormous amounts of radiation in the form of photons, particles of light. It was still far too hot and dense for atoms to form. Protons and electrons, if they ever drifted close together, were instantly blasted apart again by the intense radiation surrounding them. The universe at this stage behaved less like the gentle night sky you might imagine, and more like the inside of an active star, glowing, opaque, and violent, though evenly and uniformly so across its entire volume, without stars or structure of any kind yet. During this period, protons and neutrons converted back and forth into each other through interactions with other particles governed by a delicate balance of nuclear physics. As the universe cooled further, this balance began to shift, and slightly more protons than neutrons remained, a ratio that would turn out to matter enormously for what came next. Asterisk, the first 3 minutes, building the first nuclei. About 1 second after the beginning, the universe had cooled to roughly 10 billion degrees. This might still sound impossibly hot, and it is, but it was cool enough for a new kind of chemistry, or rather nuclear physics, to begin. Over the next few minutes, in a process called Big Bang nucleosynthesis, protons and neutrons started fusing together to form the very first atomic nuclei. This process could only happen within a narrow and precisely balanced window of time. If the universe had remained too hot for too long, any nuclei that tried to form would have been blasted apart again by the surrounding radiation, the same way early attempts to form neutral atoms kept failing before recombination. But if the universe had cooled too quickly, the particles would have spread too far apart to find each other and fuse at all. The conditions needed to be just right, and for a few crucial minutes they were. It began with the simplest possible combination. A single proton fusing with a single neutron created deuterium, sometimes called heavy hydrogen, releasing a burst of energy in the form of a photon as it formed. This happened for the first time roughly 2 minutes after the beginning of the universe, marking the very first appearance of a nucleus more complex than a lone proton. From there, the process moved quickly. Deuterium nuclei combined with each other and with additional protons and neutrons, building up helium-3, then helium-4, and small trace amounts of lithium. Nearly all of the neutrons in the universe at this stage, since they were slightly outnumbered by protons, in a ratio of roughly 7 protons for every 1 neutron, ended up locked inside helium nuclei, since that combination was especially stable. This entire process lasted only about 3 to 20 minutes before the universe had expanded and cooled enough to shut it down completely. After that point, the density and temperature dropped too low for further nuclear fusion to occur on any significant scale. Whatever elements existed at the end of those 20 minutes would remain largely unchanged until stars were born hundreds of millions of years later and began forging heavier elements of their own, a story that belongs to a much later chapter. What did the universe look like? Chemically, once this brief window closed, scientists have calculated the answer with remarkable precision, and observations of the oldest stars and gas clouds in the universe confirm it closely. The matter that emerged from those first minutes was roughly 75% hydrogen by mass, and about 25% helium, with only the faintest trace amounts of lithium and nothing heavier. This is one of the most beautiful confirmations of the entire Big Bang model. Scientists calculated these numbers based purely on nuclear physics, long before precise instruments could measure the actual chemical makeup of ancient gas clouds. When those measurements finally came in, they matched the prediction closely. It remains one of the strongest pillars of evidence we have for how the early universe unfolded. A long, dim, glowing wait. Once nucleosynthesis ended, the universe entered a strange quiet stretch that lasted for a very long time, at least by the standards of those first few frantic minutes. Nuclei of hydrogen and helium existed now, but they were still stripped of their electrons, charged particles drifting through an incredibly hot, dense glowing gas. Free electrons had not yet found stable homes. This mattered enormously because free electrons are extremely good at scattering light. Every time a photon of light tried to travel through this early universe, it would almost immediately bump into a free electron and get knocked off course over and over and over again. The result was an opaque universe, glowing brightly everywhere but impossible to see through in any meaningful way, not unlike trying to see through a thick, endless fog lit from within. For roughly the next several 100,000 years, the universe simply continued expanding and cooling in this hazy, glowing state. Nothing especially dramatic happened during this stretch, at least nothing visible. It was a long, slow unwinding, matter and radiation locked together in a tight embrace, unable to separate, the universe glowing uniformly bright but hidden behind its own dense fog. If you could have been there, floating in that primordial haze, you would have seen light everywhere around you, but never any distinct shape, never a single point of focus, only an endless, even glow in every direction. Recombination. When the fog finally lifted, then, roughly 380,000 years after the beginning, something changed. The universe had continued expanding and cooling all this time, and it finally dropped below a critical temperature of around 3,000 degrees. At that temperature, electrons could finally slow down enough to be captured by atomic nuclei and held there, without immediately being stripped away again by the surrounding radiation. Hydrogen nuclei captured electrons to form neutral hydrogen atoms. Helium nuclei did the same, forming neutral helium. Scientists call this moment recombination, even though it is something of a misleading name. Electrons and nuclei were never combined before this point, so nothing was truly happening for a second time. The name stuck simply because of how the idea was first described. Long before the Big Bang model became widely accepted, what matters is not the name but the transformation itself. Within a relatively short span of cosmic time, the universe shifted from a hot, opaque plasma into a cool, transparent gas of neutral atoms. This had an extraordinary consequence. Once electrons were bound into atoms, they stopped scattering light so relentlessly. Photons that had been trapped, bouncing endlessly from one free electron to another, were suddenly set free. For the very first time since the beginning of the universe, light could travel in a straight line, uninterrupted, for enormous distances. The fog had lifted. The universe became transparent. This moment, sometimes called the moment of last scattering, is the earliest point in the history of the universe that we can actually observe directly with light. Everything before it is hidden behind that ancient fog. forever out of reach of any telescope that relies on light to see. Everything after it, in principle, can be traced by following the light that has been travelling toward us ever since. Imagine standing inside a thick bank of clouds, so dense that sunlight scatters in every direction before it can ever reach your eyes in a straight line. You know there is light somewhere above you. You can feel its warmth. You can see a diffuse brightness all around, but you cannot make out any shapes, any edges, any single point of origin. Then, gradually, the clouds thin, and at some particular moment they part completely, and suddenly you can see clearly in every direction, all the way to the horizon. That is something like what happened to the universe at recombination, except the clouds here were made of free electrons, scattering photons endlessly, and the parting of the clouds was not gradual in human terms at all. It happened on a cosmic timescale remarkably quickly, over a span of only a few tens of thousands of years, itself a blink compared to the hundreds of thousands of years the fog had already lasted. The first light, still arriving today, that ancient light did not simply vanish once it was released. It has been travelling through the universe ever since in every direction for nearly the entire age of the cosmos. As the universe continued to expand over the following 13.8 billion years, the space through which that light was travelling stretched along with it, and the light stretched too, its wavelength growing longer and longer, shifting further and further toward the red end of the spectrum, and eventually beyond visible light entirely, into the microwave range. Today we call this ancient light the cosmic microwave background, often shortened to the CMB. It reaches us not as visible light but as a faint, cold glow of microwave radiation, arriving equally from every direction in the sky, filling the entire universe evenly. Its temperature today has cooled to just 2.725 degrees above absolute zero, a whisper of warmth compared to the blistering heat of its origin, but a whisper that carries within it the earliest picture we will ever have of our universe. The discovery of this radiation is one of the great stories in the history of science, and it happened almost entirely by accident. In 1964, two radio astronomers working at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were using a large horn-shaped antenna, originally built for satellite communication, to make careful measurements of radio signals from space. No matter which direction they pointed their antenna, they kept picking up a faint, persistent hiss of noise they could not explain. They checked their equipment for faults. They even cleaned out pigeon droppings from inside the antenna, wondering if that could be the source of the interference. Nothing worked. The mysterious signal remained, the same strength, in every direction, day and night. At almost the same time, quite unknown to Penzias and Wilson, a team of physicists at nearby Princeton University, led by Robert Dick, was actively searching for exactly this kind of signal. Years earlier, physicist George Gamow and his colleagues had predicted that if the universe really did begin in a hot, dense state, it should have left behind a faint afterglow of radiation, cooled by billions of years of cosmic expansion down to just a few degrees above absolute zero. When Penzias and Wilson described their strange, stubborn noise to Dickey's team, the pieces fell into place almost immediately. What Penzias and Wilson had stumbled upon, quite by accident, was the very afterglow of the birth of the universe. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for this discovery. Their careful, patient measurement of what seemed at first like nothing more than background static turned out to be one of the strongest pieces of evidence ever found for the Big Bang, and it settled a major scientific debate of the time in favour of an expanding, evolving universe rather than a universe that had simply always existed unchanged. There is something quietly moving about how this discovery happened. Penzias and Wilson were not searching for the birth of the universe. They were engineers and radio astronomers trying to do careful, ordinary work with a sensitive antenna, chasing down a source of noise the way anyone might chase down a strange rattle in their car, assuming it was something mundane, something fixable. They checked their wiring. They checked for interference from nearby New York City. They climbed inside the antenna itself and cleared out what they called, In their own dry words, a white dielectric material, which was, in plainer language, pigeon droppings left by birds that had been nesting inside the horn. None of it explained the signal. The hiss remained, patient and unchanging, whether they pointed their antenna at the ground or at the depths of space, during the day or at night, in summer or in winter. It took a phone call to a group of physicists a short drive away, already searching for exactly this kind of signal on purely theoretical grounds, for all the pieces to finally click into place. Sometimes the biggest discoveries in science arrive quietly, almost by accident, found by people who were simply doing careful, patient work and refusing to ignore something they could not explain. Since that discovery, our ability to study this ancient light has grown enormously. 3 major space missions, COBE in 1989, WMAP beginning in 2001, and Planck beginning in 2009, each measured the cosmic microwave background with greater and greater precision, revealing not just its overall temperature but incredibly faint variations across the sky, differences of only a few millionths of a degree from one patch of sky to another. These tiny variations might sound too small to matter, but they are, in a very real sense, the most important wrinkles in the history of the universe. Asterisk reading the wrinkles in the oldest light. Why do these tiny temperature differences matter so much? Because they are not random noise. They are a direct fossil record of the uneven ripples that were stretched across the universe during inflation, all those billions of years earlier. Regions that were very slightly denser than average appear as very slightly warmer patches in the cosmic microwave background. Regions that were very slightly less dense appear very slightly cooler. Those slightly denser regions, though the differences were almost impossibly small at the time, would go on to matter enormously. Over the following hundreds of millions of years, and then billions of years, gravity slowly amplified these tiny differences. The very slightly denser regions pulled in more and more surrounding matter, growing denser still, while less dense regions were gradually emptied out as their matter drifted toward these growing concentrations. Eventually, this process gave rise to every large structure that exists in the universe today, every galaxy, every cluster of galaxies, and the enormous cosmic patterns connecting them across space, a story that belongs to later chapters in our journey tonight. In this sense, the cosmic microwave background truly is a baby picture of the universe, and I do not use that phrase lightly. It shows us the universe as it looked when it was only 380,000 years old, a tiny fraction of its current age, smooth and glowing, and almost, but not quite, perfectly uniform. Those faint variations, so subtle that scientists needed satellites operating far more precisely than any earlier instrument to detect them, contain the blueprint for everything that would eventually come. Every star that would ever burn, every world that would ever form, everything you can see when you look up at a clear night sky. Asterisk. A universe still without form. It is worth pausing here in this quiet cooling universe before we move any further forward in time. At this point in our story, roughly 380,000 years after the beginning, the universe was filled almost entirely with 2 simple elements, hydrogen and helium, drifting as neutral gas through an expanding darkness, lit only by the fading glow of that ancient light now stretching itself into the microwave. There were no stars yet. There were no galaxies yet. There was no light being actively created anywhere in the universe, only the last echo of the original glow, dimming and cooling and reddening as it travelled onward through the growing darkness. If you could somehow hang suspended in that early cosmos, drifting through the neutral hydrogen and helium gas, you would find yourself surrounded by a faint, even, reddening light in every direction. And nothing else. No twinkle of a star, no glow of a galaxy, just gas and darkness, and the last patient traces of that first ancient light, fading slowly around you like the final light of dusk, stretching on and on without ever quite becoming full night. It would take hundreds of millions of years more before gravity, patiently working on those tiny ripples left behind by inflation, pulled enough gas together in dense enough pockets to ignite the very first stars. and end this long, quiet, formless age of the cosmos. Those ripples, remember, the ones stretched across the universe in that first unimaginable fraction of a second, were still there, still patiently doing their slow work in the dark, drawing gas together atom by atom, cloud by cloud, across a silence that would last longer than the entire span of human history, repeated many thousands of times over. That part of the story, the slow gathering of gas into the first flickers of starlight, and the strange dark stretch of time that came before it, is where we will go next, drifting further along this river of cosmic time, deeper into the unfolding history of everything that surrounds us. For now, rest here a while in this vast, cooling darkness, 380,000 years into the life of a universe that still had 13 billion years of becoming ahead of it. Let the quiet of that ancient moment settle over you, and let yourself drift along with it as the first shadows of the coming stars begin, ever so slowly, to gather somewhere out in that patient darkness, settle back in. Let your shoulders drop a little further into the mattress. If you listen to the last chapter, you already know where we left the universe. It was young, cooling, and completely dark, glowing only with the faint, reddening afterglow of its own birth. Hydrogen and helium drifted quietly through an expanding blackness, and nothing else existed yet. No stars, no galaxies, no light being made anywhere at all. Tonight we stay in that darkness a while longer, because darkness, it turns out, is not the same thing as emptiness. Something patient and invisible was already at work, and eventually it would light the first fire the universe had ever known. You do not need to hold on to every detail here. Let the numbers and the names pass through you gently, like a slow tide moving over sand. What matters is the shape of the story, the long, quiet waiting, and the moment that waiting finally ended. There is something almost restful about this part of the universe's history. If you let yourself sit with it, nothing was rushing, nothing was urgent. For hundreds of millions of years, the cosmos simply expanded, and cooled, and waited, the way a held breath waits before it is finally released. If you have ever lain awake in a completely dark room, listening to your own heartbeat, feeling time pass without any visible marker of it passing, you have some small sense of what this era might have felt like, stretched out across a scale so vast it barely fits inside a single thought. Asterisk. A universe with the lights off. Astronomers have a name for this stretch of cosmic history. They call it the Dark Ages. And for once, a scientific name matches its subject almost perfectly. This era began right around the point where our last chapter ended, about 380,000 years after the beginning, when the universe first became transparent, and it continued for a very long time afterward, roughly several 100 million years, before the first true starlight finally broke through. Try to picture that span honestly, because it is easy to let a phrase like hundreds of millions of years slide past without really landing. If you compressed the entire current age of the universe into a single calendar year, with the Big Bang happening at the first moment of January 1st, the Dark Ages would still be going by the middle of January. Nearly 2 weeks of that imagined year, and every single one of those imagined days would pass in total silence and total darkness, with nothing lit anywhere in the cosmos. During this period, the temperature of the universe continued dropping steadily, falling from around 4,000 degrees at the start of the Dark Ages down to something closer to 60 degrees above absolute zero by the time they ended. Space itself kept expanding the whole while, thinning out the hydrogen and helium gas that filled it, spreading everything further apart, slower and colder with each passing age. It's worth pausing to notice what was still present during this long night, even without any light. The universe was not simply an inert void, waiting around for something to happen to it. 2 very faint sources of radiation were technically still there. One was the fading cosmic microwave background itself, the ancient light from recombination growing dimmer and redder by the day. The other came from the hydrogen atoms themselves, which occasionally emitted extremely faint radio signals as their internal structure shifted in tiny quantum ways. Neither of these was anything close to visible light. If you had been able to float somewhere in that early universe with human eyes, you would have seen nothing at all, an endless black stretching in every direction, patient and still. Asterisk, where gravity was already working. But something was happening, even in that darkness, something slow and invisible and enormously important. This is where we need to go back briefly to a detail from the last chapter. The tiny ripples of density that inflation stretched across the fabric of the early universe, the same ripples that later appeared as faint temperature variations in the cosmic microwave background. Those ripples never went away. They were still there, woven into the fabric of the cosmos. And throughout the Dark Ages, gravity was quietly doing exactly what gravity always does. It was pulling matter toward the places where there was already slightly more of it. Here it helps to remember that ordinary matter, the hydrogen and helium we can see and touch, was not the only kind of matter in the early universe. Cosmologists have found overwhelming evidence, mostly through its gravitational effects, for a second kind of matter that does not interact with light at all. It is called dark matter, and though we do not yet know exactly what it is made of, a mystery that remains one of the biggest open questions in all of physics, we do know that it vastly outweighs the ordinary matter that makes up stars and planets and people. This is a story for a much later chapter, but for now, all you need to know is that dark matter played the leading role during the Dark Ages. It felt no resistance from light or radiation, so it began clumping together first, forming vast invisible structures called halos long before ordinary matter caught up. Think of it almost like a scaffolding going up before any of the building materials arrive. Dark matter halos formed first, purely under the pull of gravity, gathering into denser and denser knots scattered unevenly across the young universe. Ordinary hydrogen and helium gas, still glowing faintly with the last heat of the Big Bang, gradually began falling into these invisible gravitational wells, drawn in like water trickling down toward the lowest points of a landscape carved long before any rain ever fell. This process was agonizingly slow by human standards, though inevitable on cosmic timescales. Small halos formed first, some with masses only around 100,000 to a few million times the mass of our Sun, still almost impossibly vast compared to anything on Earth, but modest by the standards of galaxies that would come later. Astronomers sometimes call these early, humble structures mini-halos, and it was inside these mini-halos that the very first stars in the history of the universe would eventually be born. It is worth sitting for a moment with just how strange this idea really is. Everything you can see in the night sky, every star, every galaxy, every glowing cloud of gas, sits inside one of these invisible gravitational wells, cradled by something we cannot touch, cannot see, and do not yet fully understand. The visible universe, in a very real sense, is riding on the back of an invisible one. That was true from the very earliest moments of structure formation, and it remains true today in every corner of the observable cosmos. Ordinary matter, the stuff of stars and planets and living things, has always been the smaller, quieter partner in this arrangement, gathering wherever the unseen scaffolding of dark matter happened to already be waiting. Asterisk. How a cloud of gas becomes a fire. It's worth slowing down here and asking a simple question. How does a cold, dark cloud of gas actually turn itself into a star? The basic idea is beautifully simple, even if the details are wildly complex. Gravity pulls the gas inward. As it falls inward, the gas compresses. As it compresses, it heats up, in much the same way that pumping air rapidly into a bicycle tire makes the pump itself feel warm to the touch. If enough gas gathers in one place, and if it can shed some of that heat quickly enough to keep collapsing, rather than pushing back against its own gravity, the center of the cloud will eventually grow hot and dense enough to ignite nuclear fusion. At that moment, a star is born. The catch is that phrase, if it can shed some of that heat quickly enough. In the universe today, gas clouds cool efficiently because they are laced with what astronomers call metals, meaning any element heavier than hydrogen and helium, things like carbon, oxygen, and dust grains built from various heavier atoms. These elements are extremely good at radiating away excess heat, allowing a collapsing cloud to keep shrinking fragmenting into many smaller clumps along the way, each one eventually becoming an individual, modestly sized star. But in the early universe during the Dark Ages, none of those heavier elements existed yet. Remember, the only material available was the hydrogen and helium forged in the first few minutes after the Big Bang, plus the faintest trace of lithium. There was no dust, there were no metals of any kind. This left the collapsing gas clouds with only one significant way to cool themselves, a much less efficient process involving molecules of hydrogen, two hydrogen atoms bonded together, which could radiate away small amounts of heat as they tumbled and vibrated during the collapse. This single, weak cooling method changed everything about how the very first stars formed. Because the gas could not cool quickly or efficiently, it could not easily fragment into many smaller pieces the way gas clouds do today. Instead, it tended to collapse as one large, continuous mass, gathering more and more material before it finally became dense and hot enough at its core to ignite. As this primordial cloud fell inward, it would have heated slowly, passing through a range of a few hundred degrees, dense at its center but still loose and extended at its edges, a long gradual tightening rather than any sudden collapse. The result, according to essentially every model built by astronomers who study this era, was stars unlike anything that exists in the universe today. Enormous stars, stars far more massive than our Sun, and far more massive than almost anything that forms from gas clouds now. Asterisk. The first stars, called Population 3, astronomers have a specific name for this very first generation of stars. They call them Population 3 stars, a slightly backward label born from the history of how stars were classified, but one that has stuck. These were stars built entirely from primordial gas, with no heavier elements mixed in at all, the purest possible stars the universe would ever produce, and also, in a sense, the only stars that would ever be made this way, since every star born afterward would carry at least a trace of the heavier elements these first stars eventually created. Current models suggest that Population 3 stars typically had masses ranging from tens to hundreds of times the mass of our Sun, and in some simulations may have occasionally reached even more extreme sizes. This remains an active area of research, with real uncertainty about the exact numbers, and I want to be honest that scientists are still refining their understanding of exactly how massive these first stars typically were. What is far more settled is the general picture, that Population 3 stars were, on average, dramatically more massive than the stars being born in the universe today. Recent research has added an interesting wrinkle to this picture. For a long time, astronomers pictured the formation of these first stars as a relatively calm, orderly process, gas quietly, and steadily falling inward under gravity's patient pull. But detailed computer simulations published in 2026 suggest the reality may have been considerably more chaotic. As gas streamed into these early dark matter halos from multiple directions at once, the different streams collided and churned against each other, creating powerful turbulence, swirling motions moving several times faster than the local speed of sound. Rather than settling smoothly into a single enormous star, this turbulent gas sometimes fragmented into multiple dense clumps within the same halo, suggesting that the first stars may often have formed in small groups or clusters rather than in perfect isolation. This is a very recent and still developing area of research, so treat it as an evolving picture rather than a settled conclusion. But it offers a wonderfully vivid image. Dark matter halos not as calm, silent nurseries, but as turbulent, stormy cradles out of which the universe's first fires were born. When Population 3 stars finally did ignite, likely somewhere between about 100 million and 250 million years after the Big Bang, though the earliest possible date remains debated among researchers, they would have been almost unimaginably bright and hot. Without heavy elements to help regulate their internal fusion, these massive stars burned through their hydrogen fuel far more aggressively than stars do today, forcing their cores to reach especially high temperatures, which in turn made their surfaces blaze with intense ultraviolet light. I want to gently note something here. since it connects to a later chapter without stepping into it. These enormous first stars did not live long. Given how ferociously they burned through their fuel, most population 3 stars likely existed for only a few million years, a fleeting flash of light compared to the billions of years stars like our own sun can shine. What happened at the end of their brief lives, and the extraordinary way some of them may have exploded, belongs to a story we will tell properly a little further along in this journey. For now, simply hold on to this one plain fact. The very first stars in the history of the universe burned bright, burned fast, and did not last. Asterisk. Light finally breaks the darkness, whatever their eventual fate. The important thing, for our purposes tonight, is what these first stars did while they were shining. For the first time since the Big Bang, over 100 million years earlier, actual starlight existed in the universe, streaming outward from these massive, blazing objects into the surrounding darkness. This starlight carried an enormous amount of energy, particularly in the ultraviolet range, invisible to human eyes but extremely potent all the same. And that ultraviolet light was about to do something remarkable to the gas surrounding these first stars, something that would eventually transform the entire visible universe. Remember that space at this point in history was still filled almost entirely with neutral hydrogen atoms, meaning atoms where a single electron remained calmly bound to a single proton, exactly as it had been since recombination hundreds of millions of years earlier. Ultraviolet light, especially the intensely energetic light pouring off these massive first stars, carries enough energy to knock that electron clean off its proton, splitting the atom back into its separated charged pieces. Astronomers call this process ionization, and it is, in a very real sense, the reverse of recombination, the very transformation we spent so much time on in the previous chapter. Around every one of these first blazing stars, a growing bubble of ionized hydrogen began to spread outward into the surrounding neutral gas, like a growing patch of daylight, pushing back an endless night. As more and more of these stars ignited across the universe, more and more of these bubbles began appearing, scattered through the darkness like scattered campfires, slowly growing larger and larger, each one steadily eating away at the neutral hydrogen fog surrounding it. Asterisks. The slow tide of reionization. Astronomers call this entire, extended process the epoch of reionization, and unlike the relatively swift transition of recombination hundreds of millions of years earlier, reionization was a long, gradual, uneven affair, unfolding patchily across different regions of the universe over an enormous span of time. It did not happen everywhere at once. Regions of the universe with more matter, and therefore more early stars and later, early galaxies, ionized first, their bubbles of charged hydrogen expanding and eventually merging with neighboring bubbles from nearby star-forming regions. Emptier regions of the universe, with fewer stars to do the work, remained wrapped in neutral hydrogen fog for much longer. For a very long stretch of cosmic history, the universe would have looked something like a nighttime landscape dotted with isolated, growing patches of daylight, some regions bright and clear, others still submerged in darkness, the boundaries between them slowly shifting and expanding as more stars, and eventually the first true galaxies added their light to the effort. Imagine looking down on a vast, dark countryside from somewhere high above, before sunrise, watching as scattered porch lights and street lamps begin flickering on here and there, clustered thickly in some neighborhoods, sparse and scattered in others, with wide stretches of unbroken darkness still lying between them. Slowly, as more and more lights come on, the bright patches spread and touch each other, until entire regions are lit continuously, while a few stubborn pockets of darkness linger on at the edges, holding out a little longer before finally joining the rest. That, stretched across hundreds of millions of years and scaled up to the size of the observable universe, is something like what reionization actually looked like, at least according to the simulations and models astronomers have built to describe it. Pinning down exactly when reionization began and ended has been one of the great challenges in modern cosmology, and it remains an active, evolving area of research even now. For many years, the most widely accepted estimate placed the end of reionization, the point when nearly all of the hydrogen scattered between galaxies had become ionized, at around 1 billion years after the Big Bang. A careful and widely respected study published in 2022, led by astronomer Sarah Bosman and her colleagues, examined the light from 67 distant quasars, extremely bright and distant objects whose light passes through and is subtly altered by any remaining neutral hydrogen gas along its path to Earth. Their analysis placed the end of reionization at approximately 1.1 billion years after the Big Bang, helping to settle a debate that had continued for roughly 2 decades among researchers studying this period. More recent observations, however, particularly from the James Webb Space Telescope, have complicated this picture somewhat. Webb has revealed a greater abundance of early galaxies than many earlier models predicted, and these galaxies appear to be producing more ultraviolet radiation than expected. Some researchers now suggest reionization may have concluded somewhat earlier, perhaps between 550 and 650 million years after the Big Bang, rather than the previously favoured figure closer to 1 billion years. This remains a genuinely open and actively debated question in astronomy today. And I want to be honest that scientists have not yet reached full agreement on the precise timeline. What is not in question is the overall arc of the story, that reionization was a long, gradual process driven by the light of the first stars and later the first galaxies, and that it eventually succeeded in transforming the entire observable universe from a darkened neutral fog into the clear, transparent expanse of space we observe today. Listening for an echo instead of watching for light. Because population 3 stars were so faint by modern standards, so distant, and so brief in their individual lifetimes, astronomers cannot simply point a telescope at the sky and expect to see them directly, not even with an instrument as powerful as the James Webb Space Telescope. To date, no population 3 star has ever been directly and unambiguously observed despite years of dedicated searching. This is one of the true frontiers of modern astronomy, and finding solid direct evidence of these very first stars remains an active and highly sought-after goal. Instead of watching for the faint light of these ancient stars directly, some astronomers have turned to an entirely different technique, one that involves listening rather than looking, in a manner of speaking. Neutral hydrogen atoms, scattered throughout the early universe, occasionally emit an extremely faint signal at a specific radio wavelength of about 21 centimeters, caused by a tiny quantum flip in the alignment of the atom's internal particles. As the universe expanded over billions of years, this signal stretched out along with space itself, shifting down into much lower radio frequencies that specialized instruments on Earth can, in principle, detect today. The presence, strength, and pattern of this faint 21 centimeter signal changes depending on the temperature and ionization state of the hydrogen gas at the time it was emitted, which means it carries encoded information about exactly the era we have been discussing tonight: the dark ages, the emergence of the first stars, and the long, uneven process of reionization. In 2018, a ground-based radio telescope in a remote part of Western Australia, part of an experiment called EGIS, reported detecting a signal that researchers interpreted as the first ever direct evidence of this ancient 21 centimeter absorption feature from the era of the very first stars. I want to be especially careful and honest here, because this result remains genuinely unsettled within the scientific community. The signal reported by the EGS team was notably stronger, roughly twice as deep, as most standard theoretical models predicted it should be, which suggests either some unexpected physics at work during this era, perhaps involving dark matter interacting with ordinary matter in unanticipated ways, or possibly some instrumental or environmental factor that has not yet been fully accounted for. As of the most recent research available, this detection has not been independently confirmed by any other experiment, and several careful follow-up studies have suggested the original signal might be explainable through standard astrophysics after all. without requiring any new or exotic physics. Multiple research teams around the world, using new and more sensitive instruments, continue working to confirm or refine this result. And it remains one of the most closely watched open questions in the study of the early universe. Whatever the final answer turns out to be, the 21 centimeter signal represents one of our best hopes for eventually studying the dark ages and the first stars directly, rather than only inferring their existence from theory and simulation. A universe waking up. Let yourself picture one more time what this era might have looked like if there had been anyone there to see it. A vast, cold darkness, stretching in every direction, filled with an invisible gas slowly gathering itself into denser and denser pockets under gravity's patient, silent pull. And then, scattered unevenly across that darkness, the first points of light beginning to flicker on, one by one, then in growing numbers, each one a colossal, short-lived star, burning fiercely, blazing with ultraviolet fire, carving a small bubble of clarity into the endless neutral fog around it. Over the following hundreds of millions of years, those bubbles grew and multiplied, and gradually began to merge with one another, until at last the fog that had blanketed the entire universe, since the moment it first became transparent, was finally, fully burned away. The Dark Ages, that long, quiet, patient stretch of cosmic history, had come to an end. If you try to hold the whole shape of this era in your mind at once, it traces a slow, gentle arc. First, an unbroken darkness, hundreds of millions of years of silent gathering, with nothing to see and nothing to hear, only gravity, working alone, patiently drawing matter toward the places where the universe happened to be very slightly denser than everywhere else. Then the first faint sparks, scattered thinly across an enormous darkness, each one a colossal, short-lived star burning through its fuel at a furious pace. Then, slowly, the spreading bubbles of light, growing, reaching toward one another, merging, until finally the entire visible universe had been touched by starlight, and the ancient fog that had covered everything since the very beginning had lifted for good. But something else was happening during all of this as well. Something we have only touched on lightly tonight. Those first blazing stars did not simply light up the darkness and then vanish without a trace. Deep within their cores, in temperatures and pressures far beyond anything achievable, inside an ordinary star, today something new was beginning to happen. A process that would eventually fill the universe with a richness of materials it had never possessed before. Hydrogen and helium alone had built the first generation of stars, but those stars, in the astonishingly brief span of their brilliant lives, were quietly forging something the universe had never seen. And when those short, ferocious lives finally came to an end, they would scatter that new material outward into the surrounding darkness, seeding the cosmos with the raw ingredients for everything that would come afterward: planets, dust, and eventually, unimaginably far in the future, the very atoms that would one day form living things. That transformation, the slow, patient life of a star, and the extraordinary way stars are born, live, and change over time, is where we will travel next, drifting further along this long river of cosmic history, deeper into the quiet, endless dark, toward the gentle, gathering light of the stars still waiting to be born. Rest here a little longer if you like, in this early universe of scattered fires and slowly spreading dawn, and let the rest of the story come to you gently, one soft unfolding moment at a time. Welcome back to the quiet dark. Let your body settle again into the place where you are resting. In our last chapter, we watched the first stars flicker on across a young, cooling universe, enormous, blazing, and short-lived, burning away the fog that had covered everything since the beginning. Tonight, we slow down and look more closely at something we only glimpsed before. We are going to follow the full, unhurried story of how a star is born, how it lives, and how it slowly changes as the billions of years pass. This is not the story of any one particular star. It is the story every star follows, with small variations, across the entire history of the universe, including the star quietly warming the world you are lying on right now. Let your eyes stay closed. There is nothing to watch here, only something to imagine, slowly, gently, one soft image at a time. Think of the stars you may have seen on a clear night, scattered like tiny points of salt across a dark table. Each one of them, without exception, followed some version of the story you are about to hear. Each one began as nothing more than a slight thickening in a cold, drifting cloud, a whisper of extra gravity in an otherwise even darkness. It is strange to think that something as vast and blinding as a star begins its life so quietly, so gradually, with nothing more dramatic than a little bit more matter, gathered in one place than in another. But that is exactly how it happens. Every single time, everywhere in the universe. Asterisks, clouds that are colder than anything on Earth. Every star, including our own sun, begins its life inside a cloud. Not a cloud like the ones that drift across an ordinary sky, but something astronomers call a molecular cloud, a vast, dim gathering of gas and dust spread out across many light years of space. These clouds are made mostly of hydrogen, along with helium and small amounts of dust, and they can be almost unimaginably large, some stretching for 100 light years or more, containing enough material to build many thousands, sometimes millions, of stars the size of our sun. What makes these clouds so different from the empty space around them is their temperature. Most of interstellar space is nearly, though not perfectly, empty, and can be surprisingly warm in a technical sense, its scattered atoms moving quickly even though there are so few of them that little heat is actually transferred. Molecular clouds are different. They are cold, often falling below 10 degrees is above absolute zero, cold enough for hydrogen atoms to pair up into hydrogen molecules, and cold enough for gravity to finally start winning its long, patient argument against the outward pressure of warm, fast-moving gas. Astronomers sometimes call these clouds stellar nurseries, and it is a fitting name. Within them, something like a slow cosmic pressure cooker is always quietly at work. Dense knots form within the cloud, tiny regions by cosmic standards, where slightly more gas and dust have gathered than in the surrounding space. It does not take very much of an imbalance. A region only slightly denser than its surroundings will exert a slightly stronger gravitational pull, drawing in a little more material, which makes its pull slightly stronger still. This is how it always begins, not with a dramatic event, but with a small, quiet asymmetry that gravity slowly, patiently amplifies over thousands and then millions of years. If you could somehow drift through one of these clouds yourself, you would find almost nothing to see with ordinary eyes. No glow, no visible motion, just a faint, cold haze of gas and dust so thin that in most places it would barely register as anything at all. And yet astronomers studying these regions with infrared and radio telescopes, instruments built to see past the dust that blocks ordinary visible light, find them anything but empty. They are humming quietly with activity, threaded through with filaments of slightly denser gas, dotted with the faint infrared glow of protostars already beginning to take shape deep inside, hidden from ordinary sight by the very dust that helped bring them into being. If you have ever pictured the night sky and imagined every star as separate and solitary, this stage of the story asks you to picture something different. Stars are almost never born alone. They tend to form in groups, clusters of newborn stars, all condensing out of the same enormous cloud at roughly the same time, siblings born from the same nursery, drifting slowly apart from each other over the following millions of years, as their individual gravity pulls them along separate paths. Asterisks, the slow collapse toward a star. As a dense knot within the cloud continues to gather more material, gravity begins to win more and more decisively. The knot starts to contract, and as it contracts, several things start happening at once. It heats up, because compression always generates heat, the same simple principle that makes a bicycle pump feel warm after you use it. It also begins to spin faster, for a reason connected to a basic law of physics called the conservation of angular momentum, the same principle that makes a spinning ice skater speed up when they pull their arms in close to their body. Any tiny, almost undetectable rotation the original cloud possessed becomes dramatically more noticeable as the cloud shrinks down to a much smaller size. This spinning has an important consequence. As the collapsing material shrinks inward, It cannot simply fall straight into the center from every direction. The spin flattens the surrounding material into a wide, rotating disk, with the densest material continuing to collapse toward the middle. At the very center of this disk, a dense hot core begins to take shape. Astronomers call this object a protostar, a star in the process of being made, but not yet a true star in the fullest sense. A protostar generates a considerable amount of light and heat, but at this stage none of it comes from nuclear fusion. It comes purely from gravity itself, from the sheer energy released as material continues falling inward and compressing under its own weight. This gravitational energy can make a protostar shine surprisingly brightly, especially in infrared light, even though the true nuclear furnace at its heart has not yet ignited. Surrounding the young protostar, the flattened disk of leftover gas and dust continues to swirl. In time, this disk will become deeply important for an entirely different reason, one we will return to in a much later chapter, because it is within disks exactly like this one that planets eventually form, condensing slowly out of the same material that did not quite make it into the star itself. For now, though, our attention stays on the protostar at the center, still growing, still gathering mass, still gradually heating up. Asterisk a star pretending to be a star. As the protostar continues its slow collapse, it eventually reaches a stage astronomers have given a distinct name. It becomes what is called a pre-main sequence star, and one especially well-studied and common type of these young objects is known as a T Tauri star, named after one of the first examples ever carefully studied. At this stage, the object looks remarkably similar, at least on the outside, to the kind of star we would recognize in the night sky. Its surface temperature is often comparable to a fully formed star of similar mass, but its core is still not hot enough to sustain true nuclear fusion. Everything it radiates still comes from the ongoing energy of gravitational collapse, not from fusion reactions, because it has not yet fully contracted down to its final compact size. This young star is often considerably larger, and therefore considerably more luminous, than the mature star it will eventually become. This adolescent stage in a star's life is anything but calm. Young stars at this point tend to be highly active, covered in enormous star spots, prone to violent flares, and often blasting out powerful outflows of material along their poles, sometimes called stellar winds, that can push back and help clear away some of the surrounding cloud material. It is a turbulent, energetic period, lasting roughly 100 million years for a star like our Sun, a surprisingly long stretch of cosmic adolescence before true stability finally arrives. Asterisk the moment of ignition. That stability arrives at a very specific and dramatic threshold. As gravity continues compressing the protostar's core, the temperature and pressure inside keep climbing, higher and higher, until they finally reach somewhere around 10 million degrees. At that precise temperature, something remarkable becomes possible. Hydrogen nuclei, which are simply single protons, are normally kept apart by their mutual electrical repulsion, since particles carrying the same electrical charge naturally push away from each other. But at 10 million degrees, protons are moving fast enough and colliding forcefully enough and often enough that a small but steady fraction of them manage to overcome that repulsion and fuse together. This is the process called nuclear fusion, and its ignition marks the true birth of a star. In stars roughly the size of our Sun or smaller, this fusion mostly proceeds through a specific sequence of reactions called the proton-proton chain. Two protons fuse to form a nucleus of heavy hydrogen, called deuterium, releasing a small burst of energy. That deuterium nucleus then fuses with another proton to form a light form of helium. Finally, two of these light helium nuclei combine to form a stable, ordinary helium nucleus, releasing two protons back into the surrounding plasma to begin the process again elsewhere. Taken as a whole, this chain of reactions converts 4 hydrogen nuclei into one helium nucleus, and in doing so, releases a small but significant amount of energy. Following the same basic principle Einstein described when he showed that mass and energy are, in a very real sense, interchangeable. It is worth appreciating just how remarkable this reaction actually is. The very first step of the proton-proton chain, two protons managing to fuse together at all, is astonishingly rare on an individual particle-by-particle basis. It happens only because of a strange quantum mechanical effect that allows particles an occasional unlikely chance to overcome a barrier that classical physics says should be impossible for them to cross. This slowness is not a flaw. It is, in fact, precisely why stars like our Sun burn so steadily and for so long, gently sipping their fuel across billions of years rather than consuming it all in a sudden burst. Once fusion ignites steadily in a star's core, something crucial happens. The outward pressure created by all this newly released energy finally pushes back hard enough to balance the star's own inward gravitational pull. Astronomers call this balance hydrostatic equilibrium, and it is this delicate, ongoing balance, gravity pulling inward, fusion pushing outward, that allows a star to remain stable in size for the vast majority of its life. The chaotic, contracting protostar has become a true, steady star. Bright, hot, and burning fast. Not every star follows exactly the same fusion pathway. In stars noticeably more massive than our Sun, roughly 1.5 times the Sun's mass or greater, a different process called the CNO cycle takes over as the dominant source of fusion energy. This process uses carbon, nitrogen, and oxygen nuclei, not as fuel that gets consumed, but as a kind of a chemical assistant, cycling through a series of reactions that ultimately accomplishes the same basic transformation, turning hydrogen into helium, but at a much faster rate, because it depends far more sensitively on core temperature. The more massive and hotter a star's core, the more this faster pathway tends to dominate its fusion output. This distinction matters enormously for how long a star lives, and it introduces one of the most important and almost paradoxical patterns in all of stellar astronomy. You might reasonably assume that a star with far more fuel available would naturally burn for a much longer time. In reality, the opposite is true. More massive stars burn through their hydrogen at a dramatically faster rate than their extra fuel can compensate for, because their cores are so much hotter and denser, driving fusion reactions at a far more furious pace. The result is that the most massive stars in the universe often live only a few million years before exhausting their fuel, a brief flash by cosmic standards, while smaller, cooler stars can continue quietly fusing hydrogen for billions, and in some cases trillions of years. Sorting the stars, the Great Diagram. Early in the 20th century, two astronomers, Ejnar Hertzsprung and Henry Norris Russell, working independently of one another, noticed something elegant hidden within the scattered data astronomers had been collecting about stars. If you plot every star according to two simple properties, its surface temperature and its intrinsic brightness or luminosity, the stars do not scatter randomly across the resulting chart. Instead, they fall into clear, distinct patterns and families. This chart, now called the Hertzsprung-Russell diagram, remains one of the most useful tools in all of astronomy, a kind of map that reveals a star's entire life story if you know how to read it. The great majority of stars, roughly 90% of all the stars in the sky at any given moment, fall along a long diagonal band running from the upper left of this diagram down to the lower right. Astronomers call this band the main sequence, and it represents stars steadily fusing hydrogen into helium in their cores. Exactly the stable balanced state we just described. Hot, massive blue-white stars sit at the upper left of this band. Cooler, smaller, redder stars sit toward the lower right. Our own Sun sits comfortably in the middle of this band, a fairly ordinary, moderate star by the standards of the wider universe. The quiet, patient red dwarfs. At the very lower right end of the main sequence sit the smallest true stars capable of sustaining fusion, the red dwarfs. These stars typically contain somewhere between about 8% and 60% of the mass of our Sun, glowing with a dim, reddish light. Their surface is only a few thousand degrees, far cooler than our own Sun's roughly 6,000 degree surface. Red dwarfs are, without question, the most common type of star in the universe, making up roughly 3/4 of all the stars in our galaxy alone. And yet, because they are so faint, not a single one is visible to the unaided human eye from Earth, even though the nearest star system beyond our own Sun, a red dwarf called Proxima Centauri, is actually one of them. What makes red dwarfs especially remarkable is not their brightness, but their extraordinary patience. Because of their small size and internal structure, red dwarfs mix their material far more thoroughly than larger stars do, constantly circulating gas from their outer layers down into the fusion-powered core in a continuous process astronomers call convection. This means a red dwarf eventually burns through nearly all of its hydrogen, not just the portion sitting in its core, unlike larger stars that leave much of their outer hydrogen unused. Combined with their naturally slow, gentle fusion rate, this allows red dwarfs to shine steadily for an almost incomprehensible span of time. Estimates suggest the smallest red dwarfs may continue fusing hydrogen for trillions of years, some calculations suggesting numbers as high as 10 trillion years or more for the very lowest mass examples. Since the universe itself is only about 13.8 billion years old, every single red dwarf that has ever formed is, in a very real sense, still young. Not one of them, anywhere in the observable universe, has yet had enough time to reach the end of its life. I want to be clear that these extremely long lifetime estimates come from theoretical models rather than direct observation, since no one has ever watched a red dwarf actually complete its life cycle, but the underlying physics behind these calculations is considered very well established. Asterisk, a star like our own. Further up the main sequence sit stars like our Sun. Astronomers classify it specifically as a G-type star, sometimes casually called a yellow dwarf, even though its light is closer to white than true yellow. Our Sun formed roughly 4.6 billion years ago, and has spent the time since then quietly and steadily fusing hydrogen into helium within its core, maintaining a stable size and output this entire time, exactly the calm, balanced main sequence life we described earlier. A star like the Sun spends the great majority of its total life, roughly 80 to 90% of it, in this stable main sequence phase. For the Sun, this stretch of steady hydrogen-burning life is expected to last around 10 billion years in total. Having already used up about half of that allotted time, our Sun still has approximately 5 billion more years of stable, main sequence life ahead of it. A genuinely comforting thought, if you take a moment to let it settle in. Whatever concerns fill your day tomorrow, the star warming this planet has an enormous amount of steady, reliable life left to give. There is something worth sitting with in that number. 5 billion years is longer than the entire history of life on Earth so far, longer than the time since the very first single-celled organisms appeared in ancient oceans, longer than the age of the oldest rocks we have ever found. And it is only the time remaining, not the whole story. Every sunrise you have ever watched, every quiet evening spent under a darkening sky, has been powered by a star quietly, faithfully converting hydrogen into helium, deep in its core, at a pace so steady and so patient that it will keep going for billions of years still to come. Asterisk, when the fuel begins to run low. Eventually, though, every main sequence star, no matter its size, faces the same fundamental challenge. The hydrogen fuel in its core is finite, and eventually it starts running low. For a star like our Sun, this moment lies billions of years in the future, but it is worth walking through gently now, since it reveals one of the most beautiful and dramatic transformations in all of stellar life. As hydrogen becomes scarce in the very centre of the star, fusion there begins to slow, and the outward pressure that had been so carefully balancing gravity starts to weaken. Gravity, patient as always, begins to win again. The core starts to contract, and as it contracts, just as we saw during the star's very earliest formation, that contraction generates heat. This new heat is intense enough to ignite a shell of hydrogen fusion in a layer surrounding the shrinking core, even though the core itself has run out of fuel. This shell of fusion, positioned around the shrinking, inert core, actually produces even more energy than the core fusion had originally, and this surge of energy pushes outward on the star's outer layers with tremendous force. The result is dramatic. The star begins to swell. its outer layers expanding enormously while cooling, as they spread across a much larger surface area. As the surface cools, its colour shifts, moving from white or yellow toward a deep glowing red. The star has become what astronomers call a red giant. A star grown vast and strange, the transformation into a red giant is genuinely staggering in scale. A star like our Sun, only about 1.4 million kilometres across today, is expected to swell to somewhere between 100 and 250 times its current radius during this phase, easily large enough to engulf Mercury, and quite possibly Venus and Earth as well, depending on exactly how much mass the Sun loses along the way, a detail astronomers are still refining through ongoing research. Despite this enormous increase in size, and a dramatic increase in overall brightness, the surface temperature of a red giant actually drops, often down to somewhere between 2,000 and 3,000 degrees, cooler than the star's original main sequence temperature, because that same energy is now spread across a vastly larger surface. Deep inside this bloated red giant, the story is not yet finished. The core, still contracting under gravity's steady pull, eventually reaches a new critical threshold, somewhere around 100 million degrees. At that temperature, an entirely new fusion reaction becomes possible, one capable of fusing helium nuclei together to form carbon, in a process called the triple alpha process, named for the old scientific nickname for a helium nucleus, an alpha particle. In stars close to the Sun's mass, this new phase of core fusion often ignites suddenly in an event called the helium flash, briefly unleashing an enormous burst of energy deep within the star, though this burst is absorbed internally and does not disrupt the star's outer appearance in any dramatic way. With this new fusion source stabilizing its core, the star actually shrinks back down somewhat, entering a calmer, more settled phase, sometimes called the horizontal branch, quietly fusing helium into carbon for a period lasting perhaps around 100 million years. A much shorter stretch than the billions of years spent earlier on the main sequence. Eventually, though, the helium in the core runs out as well, and the entire sequence essentially repeats itself one more time. The core contracts again, a new shell, this time burning helium, ignites around it, and the star swells outward once more, entering a second and often even larger red giant phase, called the asymptotic giant branch, a gentle, gradual unwinding. For a star like our Sun, this entire red giant sequence, from the initial swelling to this final, extended phase, unfolds across roughly 1 to 1.5 billion years in total, an enormous span of time by any ordinary measure, though genuinely brief compared to the 10 billion years spent quietly on the main sequence beforehand. It represents the true old age of a star like our Sun, a slow gradual unwinding of the stable balance that had defined most of its life. Not every star follows exactly this same path, however, and mass, once again, makes all the difference. Stars considerably more massive than the Sun, roughly 8 times the Sun's mass or greater, follow a noticeably different and even more dramatic evolutionary track, continuing to fuse progressively heavier elements deep within layered, onion-like shells inside their cores, evolving into truly enormous stars called supergiants, rather than the more modest giants that stars like our Sun become. And on the opposite end of the scale, we already learned that the smallest red dwarfs, the ones with less than roughly half the Sun's mass, may never become red giants at all, since they may lack the necessary conditions ever to ignite helium fusion within their small, thoroughly mixed cores, potentially continuing instead to shine steadily, slowly, and almost changelessly for trillions of uninterrupted years. Whatever path a particular star ultimately follows, the picture that emerges across this entire chapter is really a story about balance, and about the passage of time. A cold cloud grows slightly denser than its surroundings. Gravity notices, and begins, patiently, to pull. A protostar forms, spins and glows with the simple heat of its own collapse. A threshold is crossed, fusion ignites, and a genuine star is born, settling into a long, stable equilibrium that can last anywhere from a few brief million years to many trillions, depending entirely on how much material it happened to gather at the very start. And then, eventually, inevitably, that fuel begins to run low, and the star begins the slow, glowing transformation into something larger, cooler, and shinier than it once was. We have carried this story right up to the edge of something enormous, the true old age and eventual ending of a star's life, the moment when all of this slow, patient balance finally comes undone for good. Depending on how much mass a star carries within it, that ending can take remarkably different forms: quiet or catastrophic, gentle or almost unimaginably violent. And in some of those endings, the universe itself receives an extraordinary gift: the very elements that would one day become planets, oceans, and living things. That story, the story of how stars end, and what they leave behind when they do, is where we will travel next, drifting further along this long, unhurried river of cosmic time, toward the final, transformative chapter in the life of every star that has ever shined. Every atom in your body has already survived the death of a star. Not one star, maybe. Many stars, across billions of years, each one living, aging, and finally breaking apart so that something new could form from the pieces. Tonight we follow that process. We watch stars die. We watch what they leave behind. And we find out how the wreckage of those deaths became you. This part of the story is slow and heavy, so let your body sink into the bed a little more. There is nothing you need to do now except listen and breathe and drift. Let's start with something simple. A star is a battle. On one side, gravity, always pulling inward, always trying to crush the star down into a single point. On the other side, the heat and pressure made by nuclear fusion in the star's core, pushing outward. For most of a star's life, these two forces are in balance. The star burns steadily, and it holds its shape. This balance can last for millions of years, or for smaller stars, tens of billions of years, but it never lasts forever. Eventually the fuel runs low, and when the fuel runs low, the balance breaks. Gravity wins. What happens next depends on one thing above almost everything else: how much mass the star started with. A star like our Sun will die quietly, compared to what we're about to describe. It will swell into a red giant, its outer layers puffing outward into space, and its core will shrink down into a small, dense object called a white dwarf. We'll come back to that. But stars far more massive than the Sun, stars at least 8 times heavier, die in a completely different way. They die in an explosion so bright that for a few weeks a single dying star can outshine every other star in its entire galaxy combined. This is a supernova, and it's where most of the heavier elements in the universe are born. Think, for a moment, about the ordinary scale of a star's life. Our own Sun has been quietly burning for about 4.5 billion years, and it will keep burning in roughly the same way for another 5 billion years after that. 10 billion years, give or take, of steady, patient fusion. Massive stars don't get that kind of time. A star 20 times heavier than the Sun might burn through its entire life in just a few million years, a blink of an eye by comparison. The heavier a star is, the faster it burns, and the more violent its ending tends to be. It's almost like the universe trades brightness for lifespan. Burn hot and fast, and your death arrives sooner, but it arrives with far more force. That trade matters for everything that follows tonight, because the fastest, brightest, most short-lived stars are exactly the ones responsible for building most of the universe's heavier elements. Slow-burning stars like our Sun live long, gentle lives and leave gentle remains. Massive stars live in a hurry, and when they finally run out of road, the universe notices. Let's slow down and walk through exactly how this happens, because the physics is strange enough to sound almost impossible, and yet we've watched it happen, over and over, across the galaxy and beyond. A massive star spends its life fusing lighter elements into heavier ones. It starts by fusing hydrogen into helium, the same basic process that powers our own Sun. When the hydrogen in the core runs low, the core contracts, heats up further, and begins fusing helium into carbon. When the helium runs low, the star contracts again, heats up again, and starts fusing carbon into even heavier elements, like oxygen and neon. This continues, stage after stage, each one faster than the last. By the time a massive star is fusing silicon into iron, that final stage might last only a single day. Astronomers sometimes describe the internal structure of a star at this late stage using the image of an onion, layer after layer, each one built from a different element, with the lightest elements on the outside and the heaviest ones packed into the center. Hydrogen on the outer shell, then helium, then carbon, then oxygen, then neon, then silicon, and at the very core, iron. It's worth picturing this slowly. Somewhere near the surface, hydrogen is still fusing gently into helium, much the way it has been for the star's entire life. A little deeper in a shell around the core, helium is fusing into carbon and oxygen. Deeper still, carbon is fusing into neon and magnesium, then a layer of neon burning, then oxygen burning, then silicon burning, each layer sitting on top of the next like the walls of a nested chamber. Each stage burns faster than the one before it. Where hydrogen fusion in the core might have lasted for millions of years, silicon fusion, right at the very end, can burn itself out in a single day. The star is racing now, sprinting toward an ending it can't avoid, even though from the outside it might still look calm, still glowing steadily in some far-off sky. And this is where the star runs into a problem it cannot solve. Every fusion reaction up to this point has released energy. That released energy is what pushed outward against gravity and kept the star stable. But iron is different. Fusing iron into anything heavier doesn't release energy. It actually absorbs energy. Iron sits at a kind of peak in nuclear physics, the point of maximum stability. Fusing it into anything larger costs more energy than it gives back. So the star's furnace, which has kept it alive for millions of years, suddenly has nothing left to burn. The iron core just sits there, inert, growing heavier every second as the layers above keep dumping more iron onto it, but producing no new energy at all. For a brief moment, the core is held up only by something called electron degeneracy pressure. This is a strange quantum effect, related to the fact the electrons resist being squeezed into the same space as one another. It's the same force that supports a white dwarf, which we'll get to shortly. But there's a limit to how much weight this pressure can support. That limit is called the Chandrasekhar limit, named after the astrophysicist Subrahmanyan Chandrasekhar, and it sits at around 1.4 times the mass of our Sun. Once the iron core crosses that threshold, electron degeneracy pressure fails, and the core collapses. And when we say collapses, we mean it collapses fast. In less than a second, a core the size of the Earth crushes down into a sphere only about 20 kilometers across, roughly the size of a small city. The core's material, at the moment of collapse, reaches densities and temperatures beyond anything else in the modern universe outside of a black hole. Electrons are forced to merge with protons, transforming into neutrons and releasing a flood of nearly massless particles called neutrinos. This process is called electron capture, and it happens to an almost unimaginable number of particles in an almost unimaginably short span of time. The collapsing core doesn't stop smoothly, it overshoots. The neutrons packed at the center reach a density where the strong nuclear force, the same force that holds atomic nuclei together, suddenly resists further compression. The collapse slams to a halt and rebounds, sending a shockwave rippling back outward through the star. For a while, astronomers thought this shockwave alone was enough to blow the rest of the star apart. But the physics turned out to be more complicated. As the shockwave travels outward, it loses energy tearing heavy nuclei back apart into individual protons and neutrons, and it loses more energy to the same neutrino emission that helped trigger the collapse in the first place. In many simulations, the shockwave actually stalls before it can escape the star. What seems to save the explosion, according to the leading models astrophysicists currently use, is that flood of neutrinos streaming out from the newly formed core. Even though neutrinos barely interact with matter, so weakly that trillions of them are passing through your body right now, without you ever noticing, the sheer number of them pouring outward from the collapsing core is so enormous that a small fraction still get absorbed by the material sitting just outside it. That absorbed energy reheats the stalled shockwave, and after a delay of maybe half a second to a full second, the shock revives and successfully blasts its way out through the remaining layers of the star. This is called the neutrino-driven mechanism, and it's the model most supported by current research. Those scientists will tell you honestly that the exact details of how every supernova achieves this final push are still being worked out. Some stars, particularly ones that spin very fast and carry strong magnetic fields, may explode through a related but distinct process, where rotational energy and magnetic fields help drive the explosion instead. However it happens, the outward journey from the core to the surface of the star takes time. In a star that might be many times wider than our entire solar system, the shock wave has to plough through layer after layer of stellar material, heating everything it passes through to temperatures of billions of degrees. It's in this brief violent passage that some of the star's outer layers undergo one last burst of fusion. Different from anything that happened earlier in the star's calm life, fusion driven by heat and pressure that only exist for a few fleeting seconds. Then the shock wave reaches the surface, and the star's outer layers are blown outward into space at speeds that can reach tens of thousands of kilometers per second. For a distant observer, this is the moment the supernova becomes visible, a point of light that wasn't there before, suddenly rivaling the brightness of an entire galaxy. This entire class of explosion, triggered by the collapse of an iron core, is called a core collapse supernova. It's also sometimes labelled a Type II supernova, especially when the dying star still has a hydrogen-rich outer envelope at the time of explosion, which shows up as a specific pattern in the light the explosion gives off. Stars that have already lost their outer hydrogen layers before exploding, often because a companion star or their own stellar winds stripped it away, produce related but slightly different explosions labelled Type Ib or Type IC. All of these fall under the same basic physical story. A massive star runs out of fuel, its iron core collapses, and the rebound tears the star apart. There's a second, entirely different way for a supernova to happen, and this one doesn't require a massive star at all. This is the Type Ia supernova, and it involves a white dwarf. We'll talk about white dwarfs properly in a moment, but for now, picture a small, dense, stellar remnant left behind after a sun-like star dies peacefully. If that white dwarf happens to be part of a binary system orbiting closely with a companion star, it can slowly pull material off its neighbour over time, gradually adding to its own mass. A white dwarf has an upper mass limit of its own, the same Chandrasekhar limit we just described, around 1.4 times the mass of the Sun. As the white dwarf's mass creeps toward that limit, pressure and temperature inside it climb steadily higher. At some point, conditions inside the white dwarf become extreme enough to ignite runaway nuclear fusion all at once, throughout the star. Unlike the core collapse process, there's no huge outer envelope of unburned material left afterward. The white dwarf, made mostly of carbon and oxygen, essentially detonates completely, leaving no remnant behind at all. Researchers are still refining the precise details of how this ignition begins, whether it starts as a slower burning front that later turns into a full detonation, or whether it might sometimes be triggered by a direct collision between two white dwarfs in a binary pair. What's well established, though, is the basic outcome: a runaway thermonuclear explosion that briefly makes the white dwarf shine with the brightness of billions of suns. Because these explosions tend to happen at almost exactly the same mass threshold every time, they tend to release almost exactly the same amount of energy every time too. That consistency turns out to be enormously useful. Type Ia supernovae are so predictable in their brightness that astronomers use them as reference points, sometimes called standard candles, to measure distances across the universe. If you know how bright an object truly is up close, and you measure how dim it appears from far away, you can work out the distance between you and it. A car's headlights work the same way, in a much smaller sense. You already have a rough sense of how bright headlights should look nearby. So when you see a dim pair of lights on a dark road, some part of your mind automatically judges how far off that car still is. Type I supernovae let astronomers do the same thing across billions of light years. It was actually the study of these very explosions in the late 1990s that first revealed something startling. Distant galaxies were farther away than their expected brightness suggested they should be, meaning the universe's expansion is speeding up rather than slowing down, the opposite of what most astronomers had assumed gravity alone would produce. That discovery reshaped our understanding of the cosmos and eventually led to the concept of dark energy. Though that's a story for a different chapter of this cosmic history. For now, it's enough to notice something quietly remarkable. The same stellar deaths responsible for scattering iron and other elements across the galaxy also happened to hand astronomers one of the most important measuring tools they've ever had, a way of reading distance itself out of the brightness of a dying star. For now, what matters most is this: whether through the collapse of a massive star's iron core or the thermonuclear detonation of a white dwarf, supernovae are the universe's way of returning material to space. And the material they return isn't the same material that fell into the star in the first place. It's been transformed, forged into new elements inside the extreme heat of the explosion itself, elements that never existed until that dying star made them. Let's slow down here because this part deserves real attention. Before the shockwave of a core collapse supernova blasts outward, the star had already spent its life quietly building up elements up through iron, layer by layer, through ordinary fusion. But the explosion itself does something additional. In the extreme heat and pressure of those final seconds and minutes, as the shockwave tears through the outer layers of the star, brand new nuclear reactions become possible. Reactions that could never happen inside a stable, calm star. Some of these reactions build elements heavier than iron, something ordinary fusion inside the star's core could never manage, since fusing iron costs energy rather than releasing it. One especially important process happens when free neutrons, released during the explosion, get captured rapidly by atomic nuclei, faster than those nuclei have time to undergo radioactive decay. This is called rapid neutron capture, or the R process for short. Think of an atomic nucleus as a small cluster of protons and neutrons. Normally, if you add a neutron to that cluster, the nucleus has time to settle, sometimes undergoing a small radioactive decay that shifts a neutron into a proton, gradually working its way toward a stable configuration. But in an environment absolutely flooded with free neutrons, like the aftermath of certain explosive events, that same nucleus might catch another neutron, and then another, faster than it has any chance to decay in between. It gets pushed further and further from stability, growing heavier and heavier until the flood of neutrons eases off, and the resulting unstable, overloaded nuclei are finally free to decay their way back down towards stability, settling into new, heavier elements along the way. We'll return to this process very soon, because it turns out that supernovae alone aren't the main source of it. There's an even more violent event responsible for most of the heaviest elements in the universe, and we're going to get there. But first, let's sit with white dwarfs a little longer, because they deserve their own quiet moment of attention. Picture a star like our Sun, nearing the end of its life. It has spent about 10 billion years fusing hydrogen into helium in its core, patiently, steadily. Eventually, the hydrogen in the core runs out. The core contracts and heats up, while the outer layers of the star swell outward dramatically, cooling as they expand, turning the star into a red giant, sometimes vast enough to swallow the orbits of its own inner planets. Inside that swollen red giant, the core keeps contracting until it's hot enough to fuse helium into carbon and oxygen. But a star like the Sun never gets hot enough to fuse carbon any further. Once the helium runs out too, the star has no more fuel it can use. Slowly, gently, compared to what we described with supernovae, the outer layers of the star drift away into space, forming an expanding, glowing shell of gas called a planetary nebula. Despite the name, it has nothing to do with planets. Early astronomers just thought these glowing shells resembled the disks of distant planets when viewed through primitive telescopes, and the name stuck. What's left behind, once the outer layers have drifted away, is the exposed core of the star. This is the white dwarf. It's roughly the size of Earth, but it holds a mass close to that of the Sun, which means it's staggeringly dense. According to NASA, a single teaspoon of white dwarf material would weigh about 5.5 tons here on Earth, about the same as a fully grown adult elephant. The star's matter has been compressed to the point where ordinary atomic structure barely applies anymore. It's held up not by fusion, since there's no fusion left to power it, but by that same quantum mechanical effect we mentioned earlier, electron degeneracy pressure. Electrons resist being squeezed any closer together, and that resistance alone is enough to hold the white dwarf's mass against the crush of its own gravity, as long as the white dwarf stays below that 1.4 solar mass Chandrasekhar limit. Most white dwarfs, including the one our own Sun will eventually become, are made mostly of carbon and oxygen, the ashes left over from helium fusion. Some lighter stars, ones that never got hot enough to fuse helium at all, can leave behind white dwarfs made mostly of helium instead, and some more massive stars, right at the upper edge of what can still become a white dwarf rather than exploding, can leave behind a rarer kind, made of oxygen, neon, and magnesium. Whatever the mixture, the underlying story is the same. A star runs out of the specific fuel it needs, gravity wins the long argument it's been having with fusion, and what remains behind is a dense, inert core radiating away its leftover heat into the surrounding dark. A white dwarf has no fuel left to burn, so it simply cools, slowly, over an immense stretch of time. It radiates away the heat stored up from its former life as a star, fading gradually from white hot toward a dim red, and eventually, in theory, toward complete darkness. But here's something worth pausing on. This cooling process is so slow that it's expected to take on the order of 10 trillion years for a white dwarf to fully cool into a cold, dark object, sometimes called a black dwarf. The universe itself is only about 13.8 billion years old. 10 trillion years is roughly 700 times longer than that, which means that, as far as we currently understand physics, not a single black dwarf exists anywhere in the universe yet. Every white dwarf that has ever formed in the entire history of the cosmos is still cooling. Nothing has had enough time to finish. Our own Sun will follow this same path one day, though we don't need to spend this quiet night worrying about it. That transformation is still around 5 billion years away. Now let's turn to what happens when a star is far too massive to end up as a gentle white dwarf. This is where things get stranger, and where we return to the aftermath of a core collapse supernova. When a massive star's iron core collapses, and the shockwave successfully blows the rest of the star apart, something usually remains behind at the very centre. The collapsed core itself, now compressed even further than a white dwarf ever could be. If this remaining core has a mass somewhere between roughly 1.4 and about 3 times the mass of the Sun, the collapse halts at the point where neutrons themselves resist, being squeezed any closer together, a related quantum effect called neutron degeneracy pressure, reinforced by the strong nuclear force. What's left is a neutron star. It's difficult to overstate how extreme these objects are. A typical neutron star packs more mass than our entire Sun into a sphere only about 20 kilometers across, roughly the width of a mid-sized city. According to NASA's description of its Nike mission, which studies these objects directly, a teaspoon of neutron star material would weigh about 1 billion tons here on Earth. To put that in perspective, the combined mass of every single human being alive today, all 8 billion of us, is estimated at somewhere around 500 million tons. A teaspoon of neutron star matter would outweigh the entire population of Earth several times over. It helps to sit with that density for a moment, because numbers this large tend to slide past us without really landing. Imagine taking Mount Everest, the entire mountain, all of its rock and snow and stone, and compressing it down until it fits inside a single sugar cube. That's roughly the density we're talking about. A neutron star isn't a solid object in any way we normally understand solidity. It's closer to being a single, enormous atomic nucleus stretched out to the width of a city, held together not by the strong nuclear force alone, the way an actual atomic nucleus is, but by the sheer, overwhelming weight of its own gravity, pressing in from every direction. Gravity at the surface of a neutron star is estimated to be over 200 billion times stronger than gravity at the surface of the Earth. If you could somehow stand there, though nothing resembling you or your body could survive the attempt, the pull would be strong enough to flatten anything and everything into an even, featureless layer within a fraction of a second. Neutron stars form so quickly and conserve so much of the original star's rotational momentum in such a small space that they end up spinning at extraordinary speeds. Some rotate dozens of times per second right after formation. In binary systems, where a neutron star can pull in extra material from a companion, some have been measured spinning more than 700 times every second. Many neutron stars also carry magnetic fields trillions of times stronger than Earth's own. When a neutron star's magnetic field is angled away from its spin axis, it can sweep beams of radiation across space like a lighthouse. And if that beam happens to sweep across Earth, we detect it as a rapid rhythmic pulse. These are called pulsars. Supernovae like the one that created the neutron star are rare, at least from the perspective of a single galaxy. Astronomers estimate that a core collapse supernova happens somewhere in a galaxy like our own Milky Way only about once or twice per century, on average. Given that our galaxy holds somewhere between 100 billion and 400 billion stars, that rarity says something important. Most stars, the vast majority, are smaller and dimmer than the Sun, and they'll live unimaginably long lives, ending softly, if they end at all within any timescale we could measure. Only a small fraction, the most massive, the brightest, the most short-lived among them, are destined for this kind of explosive ending. And yet, across the 10 billion year plus history of our galaxy, that small fraction still adds up to an immense number of supernovae, each one scattering another handful of forged elements into the surrounding dust and gas, slowly enriching the material that would eventually become new stars, new planets, and eventually life. One of the most famous pulsars sits at the very heart of the Crab Nebula, a glowing cloud of gas drifting in the constellation Taurus. We know almost exactly when the star that created it exploded, because people watched it happen. On a summer day in the year 1054, Chinese astronomers recorded the sudden appearance of a brilliant new light in the sky, what they called a guest star. Historical records describe it as bright enough to be visible during full daylight for about 3 weeks, and it remained visible in the night sky for roughly 2 years afterward, before finally fading beyond view. Astronomers in Japan and the Arab world recorded similar observations around the same time. Centuries later, when telescopes had advanced enough to study the region closely, astronomers identified the expanding remains of that explosion as the Crab Nebula, and eventually found a rapidly spinning neutron star, pulsing at its centre, the leftover core of the star that vanished from the daytime sky nearly 1,000 years ago. It's a strange thing to consider. The light those ancient observers saw was the shockwave of a dying star tearing through space. What they were witnessing, without any way of knowing it, was the birth of a neutron star. If the collapsing core is massive enough, more than about 3 solar masses, not even neutron degeneracy pressure, is enough to stop the collapse. In that case, the core keeps collapsing all the way down into a black hole. We're setting that part of the story aside for now. It deserves its own quiet, careful exploration later, when we come to talk about the objects that bend space and time so extremely that not even light can climb back out. For now, let's stay with neutron stars a while longer, because their story isn't finished. Sometimes a neutron star doesn't end its life alone. In some binary systems, 2 massive stars orbit each other closely enough, and both are massive enough, that each one eventually goes through its own core collapse supernova, leaving behind 2 neutron stars, still bound together in orbit. Over time, these 2 neutron stars spiral closer and closer together. As they orbit, they radiate away energy in the form of gravitational waves, ripples in the fabric of space and time itself, first predicted by Einstein's theory of general relativity. Losing that energy causes the 2 neutron stars to drift gradually inward, orbiting faster and faster, closer and closer, over what can be millions or even billions of years. Eventually, they collide. On August 17, 2017, scientists using the advanced LIGO and Virgo gravitational wave detectors picked up the unmistakable signature of two neutron stars spiraling together and merging, an event now known as GW170817. In the final fraction of a second before impact, the two neutron stars were whipping around each other hundreds of times per second, close enough that their immense gravity was already stretching and deforming one another. Just under 2 seconds after the gravitational wave signal peaked, a short burst of gamma rays arrived from the same direction. Telescopes around the world turned to observe the spot, and within about 11 hours, they found something glowing there, a fading, reddish light in a galaxy roughly 130 million light-years away, in the direction of the constellation Hydra. This glow is called a kilonova, and it gave scientists something they had never had before: direct observational proof of where most of the universe's heaviest elements actually come from. Researchers watching the kilonova's light over the following days and weeks noticed something telling. In its earliest hours, the glow was bright and blue. Within days, it shifted toward red and infrared wavelengths, fading slowly as it went. That shift in color turned out to be a signature in itself. The early blue light came from lighter elements in the outer, fast-moving ejecta. The later red and infrared glow came from heavier elements, deeper in the ejected material, including what scientists identify as lanthanides, a group of elements that sit near the heavy end of the periodic table. Piecing together the color, the brightness, and the way both changed over time let astronomers work out, in remarkable detail, what kinds of atoms were being built in the aftermath of the collision. Here's what happens in that collision. As the two neutron stars spiral together in their final moments, immense tidal forces rip material away from their outer layers, flinging it outward into space. This ejected material is almost unimaginably rich in neutrons, since it came from the crushed interior of a neutron star, and in that neutron-rich environment, an especially intense version of that rapid neutron capture process we mentioned earlier takes place. Atomic nuclei absorb neutron after neutron in rapid succession, far faster than the nuclei have time to decay, building up increasingly heavy, increasingly unstable atoms. As these newly built nuclei then undergo radioactive decay, settling towards stability, they release energy, and that released energy is what powers the glowing light of the kilonova itself. The elements built this way include some of the heaviest and rarest atoms found in nature: gold, platinum, elements like uranium and thorium. According to the research published following the GW170817 observation, theoretical modelling combined with direct spectroscopic evidence from the kilonova confirmed that neutron star mergers can produce these heavy elements through exactly this rapid neutron capture process. It's worth being clear about the current state of the science here, since it's genuinely still an active area of research. Some more recent studies suggest that neutron star mergers alone might not fully account for every observed heavy element in our galaxy, and that other channels, possibly including certain rare types of supernovae, may also contribute to the total supply. But the core finding from GW170817 remains one of the most remarkable confirmations in modern astrophysics. For the first time, scientists watched in real time the birth of gold. Sit with that for a moment. Somewhere on Earth, in a ring on someone's hand, or a thread of wire inside a phone, or a filling in a tooth, there is gold that was forged not gently, not slowly, but in the final catastrophic collision of two collapsed stars, flung outward across space, drifting for millions or billions of years before becoming part of the dust that eventually became part of our solar system. Let's bring this all together now gently. The way a river gathers itself before it reaches the sea, every element heavier than hydrogen and helium, everything that makes up rock and water and air, and you, was built somewhere inside a star, or in the explosive death of one. The first generation of stars in the universe, forming from almost pure hydrogen and helium left over from the Big Bang, fused those light elements into slightly heavier ones, like carbon and oxygen, deep in their cores. When those early stars died, whether gently as white dwarfs or violently as supernovae, they scattered those elements outward into the surrounding gas clouds. That enriched gas eventually collapsed to form new stars, slightly richer in heavy elements than the generation before. Massive stars among that next generation built even heavier elements all the way up through iron, before dying in supernovae that flung those elements outward too, along with a scattering of elements heavier than iron, built briefly in the chaos of the explosion itself, and on the rarest, most violent occasions, when two neutron stars finally spiraled together and merged. The universe manufactured its heaviest elements of all, gold and platinum and uranium among them, and scattered those outward too. This cycle repeated. Generation after generation of stars, living and dying, each one leaving the surrounding gas a little richer than before. It's sometimes called cosmic chemical enrichment, and it took billions of years to build up anything close to the mixture of elements we find in our solar system today. Astronomers even use this enrichment as a kind of cosmic dating tool. The very first stars to form after the Big Bang were built almost entirely from hydrogen and helium, since almost nothing heavier existed yet. Stars that form today, by contrast, carry noticeably more of what astronomers broadly call metals, meaning any element heavier than helium, because they're built from gas that has already passed through the furnaces and explosions of countless earlier stellar generations. Measuring how much of these heavier elements a star contains gives scientists a rough sense of how early or how late in cosmic history that star was born. Our own Sun formed about 4.6 billion years ago from a cloud of gas and dust that had already been enriched by uncountable earlier generations of dying stars, stars that lived and burned and exploded, long before the first grain of rock that would become Earth ever came together. The elements in that cloud didn't just form the Sun. They formed the planets orbiting it too, including this one. Every mountain range, every ocean, every breath of atmosphere on this world began as scattered stardust, drifting slowly through space for millions of years before gravity finally gathered it together into something solid. According to research on the chemical makeup of the human body, and this has been studied carefully, most of the mass of a human body, somewhere around 93% according to one widely cited analysis, is made of elements that were originally formed inside stars. The oxygen you're breathing right now, filling your lungs with every slow breath, was forged inside the core of a star, likely one that lived and died long before our Sun even existed. The carbon that forms the backbone of every cell in your body, every strand of your DNA, was built the same way, fused together inside a stellar furnace. The calcium in your bones, giving them their strength and structure, was forged largely in the final violent moments of exploding stars. The iron carried in your blood, in the hemoglobin that lets you carry oxygen through your body, traces back to those same stellar deaths. The astronomer Carl Sagan put it simply, decades ago, when he said that we are made of star stuff. It's not just a poetic phrase, it's a literal, physical description of where your body's raw materials came from. Every atom heavier than hydrogen or helium in your body has a history stretching back through the death of at least one star, and in the case of the very heaviest elements, quite possibly the collision of two collapsed neutron cores flung outward in a kilonova long before Earth existed at all. Consider what that actually means, laid out slowly. The phosphorus that helps form the backbone of your DNA, quietly coiled inside nearly every one of your cells right now, was built inside a star, most likely through the same advanced burning stages that produce oxygen and silicon. The sodium and potassium that let your neurons fire, that are right now allowing you to hear these words, understand them, and feel whatever quiet response they stir in you, both trace their origins back to nuclear furnaces inside long-dead stars. Even the tiny trace amounts of rarer elements in your body, zinc, copper, selenium, each one carries its own particular stellar history, some forged in ordinary fusion, some built explosively in a supernova's final seconds, some possibly assembled in the neutron-rich wreckage of a kilonova, billions of years ago. None of these atoms were built for you specifically, of course. They didn't wait around patiently for a body to arrive. They drifted for unimaginable stretches of time, sometimes bound up in gas clouds, sometimes locked inside grains of dust, sometimes swept into the slow, patient process of planet formation, long before anything resembling life existed anywhere to make use of them. And they'll keep drifting long after you're gone too, passing eventually back into soil, or air, or water, ready, in some distant and unhurried way, to become part of something else entirely. It's a strange kind of comfort, maybe, to think about it this way, lying here in the quiet dark. Nothing about you is new, exactly. The atoms that make up your body have existed for billions of years, moving through space, passing through stars, scattered by explosions, gathered again into clouds of dust, pulled together by gravity into a planet, and eventually, after an almost unthinkable journey, arranged themselves into you, if only for this brief stretch of cosmic time. Think about the sheer number of transformations required to get here. A cloud of hydrogen gas, drifting quietly after the Big Bang, slowly pulled together by its own gravity until it grew dense and hot enough to ignite as a star. That star burning for millions of years, fusing lighter elements into heavier ones, layer by layer, deep inside itself. That star finally running out of fuel, its core collapsing in less than a second, its outer layers blasted outward in an explosion bright enough to briefly outshine its entire galaxy. The scattered debris of that explosion drifting through space for millions of years more, cooling, mixing with other clouds of gas and dust, some of it eventually gathering into a new star, some of it into planets circling that star, some of it, after further billions of years of geological and chemical and biological history, on one particular small blue world, becoming part of a living, breathing, thinking creature capable of lying quietly in the dark and wondering about all of this. That's the journey behind every breath you take tonight. When you finally drift off, every part of you settling into stillness, you'll be doing so as a temporary, living arrangement of matter that has already survived the deaths of stars, far larger and far older than anything we can easily imagine. And someday, unimaginably far in the future, long after you and everyone you've ever known, those same atoms will scatter again, ready to become something else entirely. Perhaps another star, perhaps another world, perhaps, in some distant and unknowable way, part of another quiet, thinking creature, lying somewhere else in the universe, wondering about its own beginnings, the way you're wondering about yours right now. But that's a long way off. For now, rest. The stars that made you have already done their work, billions of years of it, patiently, violently, faithfully, long before you ever arrived to benefit from it. All that's left tonight is for you to close your eyes and let the quiet carry you the rest of the way, toward whatever waits next in the deep dark corners of the universe we haven't explored yet, in the places where gravity grows so strong that not even light itself can find its way back out. There's a kind of darkness in the universe that isn't just the absence of light. It's a place where light itself gets pulled in and never comes back out. Tonight, we drift toward that darkness, carefully, slowly, the way you might approach the edge of a still lake at night, not to fall in, just to look, and to understand what's actually down there. Let your shoulders soften into the mattress. Let your breathing slow. What we're about to describe is strange, some of the strangest physics in the entire universe, but there's nothing here to fear. We're just visiting, from a very safe distance, and then we'll come home again. Let's start with the basic idea, the part scientists are completely confident about, before we drift into the deeper mysteries. Every object with mass has gravity, and every object with gravity has something called an escape velocity. This is simply the speed something would need to travel to break completely free of that object's gravitational pull. For Earth, escape velocity is a little over 11 kilometers per second. That's why rockets need such enormous amounts of fuel to leave our planet. They have to reach that speed before Earth's gravity can be outrun. Even a bullet fired straight upward, however fast it leaves the barrel, will always slow down, stop, and fall back to the ground, because nothing we can build on Earth comes anywhere close to that threshold speed. Now imagine compressing the Earth down, shrinking it while keeping all of its mass the same. As the planet gets smaller, its gravity at the surface gets stronger because you're standing closer to all that same mass, packed into a smaller space. This is worth picturing slowly. Gravity doesn't care how spread out or how compact an object is, only how much mass it has, and how close you are to the center of that mass. Shrink the Earth down to the size of a marble, keeping every bit of its original mass, and its escape velocity would climb dramatically, far beyond anything a rocket could ever achieve. Keep shrinking it, and at a certain point, the escape velocity needed to break free would exceed the speed of light itself, the fastest speed anything in the universe can travel, according to Einstein's theory of relativity. At that point, nothing could escape anymore. Not a rocket, not a beam of light, nothing. That point, that boundary where escape velocity equals the speed of light, is called the event horizon, and an object compressed enough that its own gravity crosses this threshold is what we call a black hole. It's worth sitting with how specific this idea really is. A black hole isn't a hole in the usual sense, not a tear or a gap in space. It's simply matter, ordinary matter, crushed down into an extraordinarily small space, so small and so dense that the gravity it produces becomes inescapable within a certain distance. Outside the event horizon, gravity behaves the way gravity always behaves, following the same rules that keep the Moon orbiting Earth or Earth orbiting the Sun. It's only once you cross that specific boundary that the rules change completely, and escape becomes physically impossible. There's another strange, well-confirmed effect that shows up as you approach a black hole, long before you'd ever reach the event horizon itself. Time itself begins to slow down, relative to someone watching from a safe distance. This is called gravitational time dilation, and it's a direct, thoroughly tested prediction of general relativity, confirmed not just near black holes, but in much gentler settings too, including tiny measurable differences in the passage of time between clocks placed at different altitudes here on Earth. Near a black hole, the effect becomes extreme. If you imagine watching a clock slowly falling toward the event horizon from a safe distance, you would see it ticking slower and slower the closer it gets, the light from each tick stretching and dimming, until, from your perspective, the clock would appear to freeze completely right at the edge of the horizon. Its final tick stretched out toward what looks like an eternity, without ever quite seeming to finish crossing over. From the perspective of whatever is actually falling, though, nothing so dramatic happens at all. Time would continue to pass normally for it, and it would cross the event horizon in a perfectly ordinary, finite amount of its own time, feeling nothing unusual in the moment of crossing itself. It's one of the more genuinely mind-bending, yet fully confirmed, consequences of general relativity. Two honest observers, one falling and one watching from outside, would describe the exact same event completely differently, and both descriptions would be correct. The size of the event horizon depends entirely on how much mass is packed inside it. For an object with the mass of our Sun, the event horizon would sit at a radius about 3 kilometers, meaning the entire mass of the Sun would need to be compressed into a sphere smaller than most cities, worst cities, to become a black hole. For an object with the mass of the Earth, the event horizon would sit at a radius of less than a centimeter, smaller than a grape. This distance is called the Schwarzschild radius, named after Karl Schwarzschild, a German physicist who worked out the mathematics describing it in 1916. Using Einstein's newly published equations of general relativity, while serving on the Eastern Front during the First World War. It's a strange thought that some of the clearest early mathematics describing black holes was worked out under those circumstances, far from any observatory, using nothing but equations and careful thought. Schwarzschild's original solution described the simplest possible case, a black hole that isn't spinning at all. But almost every real black hole in the universe does spin, often quite rapidly, since it inherits the rotation of the star or gas cloud that collapsed to form it, the same conservation of angular momentum that makes a spinning skater speed up when she pulls in her arms. A rotating black hole is described by a different, more complex solution to Einstein's equations, worked out by the mathematician Roy Kerr in 1963, and it behaves in some genuinely strange ways. Its event horizon becomes slightly flattened rather than perfectly spherical, and just outside that event horizon, a rotating black hole drags the surrounding fabric of space itself around with it, a real, measured effect called frame dragging, meaning that even objects outside the event horizon can be pulled into a slow, forced orbit simply by the black hole's spin, whether or not they're falling inward at all. Now, here's where we need to slow down and separate what's firmly established from what remains genuinely theoretical, because this distinction matters, and it's one honest scientists are careful to maintain. The event horizon itself, as a concept, is on extremely solid ground. It follows directly from Einstein's general theory of relativity, a theory that has passed test after test for over a century, and it's been confirmed observationally in ways we'll get to shortly. What happens deep inside that event horizon, though, at the very centre of a black hole, is a different story. According to the equations of general relativity, all of the mass inside a black hole should collapse down to a single, infinitely small, infinitely dense point. This theoretical point is called a singularity. At a singularity, according to the pure mathematics of general relativity, gravity becomes infinite, and space and time as we normally understand them stop making sense entirely. But most physicists don't actually believe this infinite point is a real physical description of nature. Instead, most researchers in this field understand the singularity as a signal that general relativity, as powerful and accurate as it is almost everywhere else, simply breaks down under these particular extreme conditions. It's a sign that we need a more complete theory, one that combines general relativity with quantum mechanics, the physics that governs the behavior of particles at extremely small scales. Physicists call this hoped for, not yet completed framework quantum gravity, and building it successfully remains one of the biggest open challenges in all of physics. Some researchers are exploring specific approaches, with names like loop quantum gravity or string theory, that attempt to describe what might actually happen at these extreme densities instead of an infinite point. Some suggesting the collapsing matter might reach an extremely dense but finite state rather than a true infinity, effectively bouncing rather than vanishing into a mathematical point. But none of these approaches has been confirmed by observation, and none is currently considered the accepted answer. So when we talk about a singularity tonight, please hold it gently, as a placeholder in the math, for something we don't yet have the right tools to fully describe, rather than a confirmed physical object. Physicists sometimes point out, almost as a small comfort, that the mathematics of general relativity itself predicts exactly where and how it will fail. That's a genuinely unusual property for a scientific theory to have. Most theories simply give wrong answers once they're pushed past their limits, without any warning built into the theory itself. General relativity, when applied to a collapsing star, essentially raises its own hand and says, "Past this point, I can no longer be trusted. Please bring a better theory." That kind of built-in honesty is part of why physicists trust general relativity so deeply everywhere outside of singularities, even while openly admitting its limits at the very center of a black hole. This uncertainty deep inside black holes connects to another puzzle physicists have been wrestling with for decades, sometimes called the black hole information paradox. In the mid-1970s, the physicist Stephen Hawking predicted that black holes aren't perfectly, eternally black after all. Through a subtle quantum effect happening right at the edge of the event horizon, black holes should very slowly radiate a faint stream of particles outward, gradually losing mass over unimaginably long timescales, a process now called Hawking radiation. This radiation has never been directly observed, since it would be incredibly faint for any black hole we know of, but the theoretical calculations behind it are widely respected. The puzzle is this: if a black hole eventually radiates away its mass and disappears completely, What happens to all the information about whatever fell into it originally? Basic principles of quantum mechanics suggest that information can never truly be destroyed, only rearranged. But Hawking's original calculation suggested the radiation coming out would be essentially random, carrying no trace of what went in. Physicists are still actively working through this puzzle, and no fully agreed upon resolution exists yet. It remains one of the genuinely open questions sitting right at the crossroads of gravity and quantum physics. Let's step back from those deep, unresolved mysteries now, and return to firmer ground, because there's a great deal about black holes that has moved well beyond theory into confirmed observation. Black holes form in more than one way, and tonight we're going to focus on the two main types astronomers study most closely: stellar mass black holes and supermassive black holes. We touched on the birth of a stellar mass black hole briefly before, when we talked about the deaths of massive stars. So let's revisit it here with a bit more care, since this is really where the story of black holes properly begins. When a star far more massive than our Sun, generally somewhere above about 20 times the Sun's mass, though the exact threshold depends on details like the star's composition, finally exhausts its nuclear fuel, its core collapses under the crushing weight of its own gravity. In slightly less massive stars, that collapse halts once the core reaches the density of a neutron star, held up by the same quantum pressure that keeps neutrons from being squeezed any closer together. But if the collapsing core is massive enough, generally more than about 2 to 3 times the mass of the Sun, not even that neutron degeneracy pressure is strong enough to stop it. There's no known force in physics capable of halting the collapse at that point. The core simply keeps falling in on itself, compressing past the density of a neutron star, past anything we can describe with confidence, until it crosses its own Schwarzschild radius and becomes a black hole. Researchers studying this process closely have found that the exact outcome depends heavily on the mass and composition of the original star. Stars up to about 80 times the mass of the Sun tend to leave behind black holes somewhat below 40 times the mass of the Sun, after shedding a great deal of their outer material in the supernova itself. Even more massive stars, in a range between roughly 80 and 140 times the mass of the Sun, can undergo a rarer and even more violent process called a pair instability supernova, in which extreme heat inside the star's core briefly converts high-energy light directly into pairs of particles and antiparticles, destabilizing the star and triggering a catastrophic pulse of mass loss, sometimes disrupting the star so completely that it leaves no black hole behind at all. It's a reminder that even in death, stars don't all follow one single script. The exact path depends on details of mass, composition and rotation that astronomers are still working to fully map out. For a long time, these stellar mass black holes could only be inferred indirectly, mostly by observing their gravitational effects on a visible companion star. One of the earliest and best studied examples is Cygnus X1, a bright X-ray source discovered in the early 1970s. Astronomers noticed a massive, unseen companion orbiting a visible supergiant star, pulling on it with far more gravity than any ordinary star that size should have, and producing bright X-rays consistent with material being violently heated as it spiraled towards something impossibly compact. For years, this was considered one of the strongest indirect cases for a real astrophysical black hole. More recent measurements put the mass of the unseen object in Cygnus X1 at somewhere around 21 times the mass of the Sun. Since then, more stellar mass black holes have been found through similar methods, and some record setters have genuinely surprised astronomers. In 2024, researchers using data from the European Space Agency's Gaia mission identified a black hole roughly 33 times the mass of the Sun, sitting quietly in a wide, gentle orbit with a companion star, only around 2,000 light-years from Earth, remarkably close in cosmic terms. This one, nicknamed Gaia BH3, is currently recognized as the most massive stellar black hole known within our own galaxy, and its size has pushed astronomers to reconsider some of their models of how such heavy black holes can form. But the observation that truly transformed our confidence in black holes, moving them from strong inference to direct, unmistakable proof, happened on September 14, 2015. On that day, twin detectors belonging to the Advanced LIGO Gravitational Wave Observatory, one in Louisiana and one in Washington State, picked up an extraordinarily faint ripple passing through the fabric of space and time itself. This ripple, called a gravitational wave, was the signature of two black holes, one about 36 times the mass of the Sun, and the other about 29 times the mass of the Sun, spiraling together and merging into a single black hole roughly 62 times the mass of the Sun, more than 1 billion light-years away. The remaining 3 solar masses worth of energy, the difference between the combined mass of the 2 original black holes and the mass of the merged result, had been converted directly into the energy of the gravitational waves themselves, radiated outward in a fraction of a second, according to Einstein's own equation relating mass and energy. To understand how faint that signal actually was by the time it reached Earth, it helps to picture the scale of the instruments built to catch it. Each LIGO detector uses laser beams travelling down 2 perpendicular tunnels, each 4 kilometers long, bouncing between precisely positioned mirrors. A passing gravitational wave stretches space in one direction while squeezing it in the other, changing the length of those tunnels by a truly minuscule amount, roughly 1/10,000th the width of a single proton. And yet, across 1 billion light-years of travel, that impossibly small distortion was exactly what LIGO's instruments were built to detect. The chirp itself, the pattern of the signal as the 2 black holes spiraled faster and faster together in their final moments before merging, lasted only about 2/10ths of a second, rising in pitch the way a whistle rises as it spins faster, before ending abruptly in the instant of collision. This event, named GW150914 after the date it was detected, was the first direct detection of gravitational waves in history, confirming a prediction Einstein had made a full century earlier, and it stands as the first direct, unambiguous evidence that binary black holes, meaning 2 black holes orbiting one another, genuinely exist and genuinely merge. In the years since that first detection, the network of gravitational wave observatories around the world, which has grown to include facilities in Italy and Japan, alongside the original LIGO detectors, has picked up signals from well over 100 additional black hole mergers. Along with the neutron star mergers we described earlier, what was once a purely theoretical prediction sitting quietly in Einstein's equations has become an entire new field of astronomy, one that listens to the universe rather than simply looking at it, picking up the faint, deep vibrations left behind by some of the most violent events matter can ever take part in. Now let's turn to something on an entirely different scale. At the centre of nearly every large galaxy that astronomers have studied closely, including our own Milky Way, sits an object of almost incomprehensible mass, a supermassive black hole. These aren't just larger versions of the stellar mass black holes we just described. They're a different category altogether, ranging from hundreds of thousands to many billions of times the mass of our Sun. Our own galaxy's central supermassive black hole is called Sagittarius A star, often written with an asterisk after the name, following an astronomical convention for particularly energetic objects. It sits at the exact centre of the Milky Way, roughly 27,000 light-years from Earth, in the direction of the constellation Sagittarius. For decades, astronomers suspected something enormous and invisible was sitting at the galaxy's centre, based entirely on the way nearby stars behaved, orbiting an apparently empty point in space at extraordinary speeds, the way planets orbit a star. One particular star, known as S2, was tracked for years as it swept through an orbit so tight and so fast that at its closest approach it was moving at several % of the speed of light, swinging around the unseen object at the galaxy's heart and then arcing back out again, over and over, following a predictable, mathematically precise path. By carefully tracking the orbits of these stars over many years, astronomers were able to calculate the mass of the invisible object they were circling with remarkable precision. about 4 million times the mass of our Sun, confined to a region of space, not much larger than our own solar system. This painstaking work, using some of the most powerful telescopes on Earth to track individual stars over decades, earned Reinhard Genzel and Andrea Ghez a share of the 2020 Nobel Prize in Physics. Then, on May 12, 2022, astronomers achieved something that had once seemed almost impossible. They released the first ever image of Sagittarius A star itself, or, more precisely, an image of its shadow, the dark silhouette it casts against the glowing, superheated material, swirling just outside its event horizon. This image came from the Event Horizon Telescope, an international collaboration that links radio telescopes from locations spread across the entire planet, effectively turning Earth itself into a single telescope large enough to resolve detail at this almost unimaginable distance and scale. The image shows a lopsided, glowing ring of light surrounding a dark central shadow, exactly the kind of pattern general relativity predicts should appear around a black hole's event horizon, viewed from a particular angle, with material orbiting and glowing on one side more brightly than the other. It's worth noting that imaging Sagittarius A star was in some ways even harder than imaging a much larger black hole the same team had already photographed in 2019, at the centre of a distant galaxy called M87, roughly 6.5 billion times the mass of our Sun. Because Sagittarius A star is comparatively so much smaller, matter around it moves and changes on a timescale of mere minutes, rather than the days or weeks it takes for material to shift noticeably around the much larger black hole in M87, making it far more difficult to capture a clear, stable picture. Researchers on the project have described it a little like trying to photograph a running puppy with a long camera exposure compared to photographing a calmly sleeping, much larger dog. The team ultimately combined thousands of individual images gathered over many hours to produce one final, averaged picture stable enough to publish and trust. This brings us to something we haven't fully described yet: the glowing ring of material surrounding a black hole, known as an accretion disk. It's worth spending some time here, because this disk is really the reason we can detect and study black holes at all, given that the black hole itself, by definition, emits no light of its own. When gas, dust, or other stellar debris drifts close to a black hole, it rarely falls straight in along a direct path. Instead, because of a basic physical principle called the conservation of angular momentum, the same reason a spinning ice skater speeds up when she pulls her arms in close to her body, infalling material tends to spiral inward gradually, tracing a flattened, rotating disk around the black hole rather than dropping straight down. Picture it almost like water circling a drain, gathering speed and heat as it narrows toward the center, except that unlike water in a sink, this material can spend an extraordinarily long time, sometimes many thousands of years, slowly working its way inward, before it finally crosses the event horizon. As particles in this disk collide and rub against one another, friction converts their motion into intense heat. Near the outer edges of the disk, temperatures might reach a relatively modest few million degrees, but closer to the event horizon, where material is moving at an appreciable fraction of the speed of light, temperatures can climb into the tens of millions of degrees for the disks around stellar mass black holes, hot enough to radiate strongly in X-rays, which is exactly the kind of radiation astronomers use to detect and study these systems from Earth. Around supermassive black holes, the accretion disk tends to be somewhat cooler on average, since a larger black hole's event horizon is proportionally farther from its most intense gravity, though a surrounding structure called a corona, an extremely hot, diffuse layer of plasma, still produces powerful X-ray emission even there. Some of the hottest regions in these coronas, right where they interact with the inner edge of the disk, have been estimated at close to 1 billion degrees, a temperature almost impossible to picture in any ordinary terms. In the most extreme cases, when an enormous amount of material is actively falling into a supermassive black hole, the resulting accretion disk can outshine every star in the entire surrounding galaxy combined. Astronomers call these intensely active systems quasars, a name that dates back to when they were first discovered and briefly mistaken for unusually bright, star-like points of light, before their true, far stranger nature became clear. A quasar isn't a special kind of object separate from a black hole. It's simply a supermassive black hole in the middle of an especially active feeding period, pulling in gas and dust fast enough to light up its surroundings brighter than the hundreds of billions of stars around it combined. Some of the most distant quasars astronomers have observed are also among the most distant objects known in the entire universe, their light having travelled for more than 13 billion years to reach us, meaning we're seeing them as they existed when the universe was still very young. Some black holes with actively feeding accretion disks also launch narrow, extraordinarily powerful jets of superheated material outward from their poles, at speeds approaching the speed of light itself, stretching in some cases for hundreds of thousands of light years beyond the galaxy that contains them, driven by intense magnetic fields twisted up by the swirling motion of the disk. These jets are among the most energetic phenomena ever observed anywhere in the cosmos. A single jet can carry as much energy outward as the combined light of an entire galaxy, focused into a thin, precise beam rather than spread out in every direction. Where exactly this jet launching mechanism gets its energy, whether primarily from the spinning accretion disk itself, or from the rotational energy of the black hole's own spin, siphoned away through its powerful magnetic field, is still an active area of research, though most current models suggest both processes likely play a role together. It's worth pausing to appreciate just how strange it is that we can study any of this at all. A black hole itself is, by definition, invisible. We will never directly see one glowing in the dark. Everything we know about them comes from watching how they affect the world around them. The stars they pull into fast, tight orbits, the gas they heat to searing temperatures as it spirals inward, the faint ripples they send rippling outward through space and time itself when two of them finally collide. In a strange way, black holes are a little like footprints in sand. You never see the person who made them. You only see the shape they left behind, and from that shape alone, careful observers have learned to reconstruct an entire hidden world. Between the stellar mass black holes formed in the deaths of individual stars and the supermassive black holes anchoring entire galaxies, there's a gap that astronomers are still working to fill in. Objects in this middle range, sometimes called intermediate mass black holes, would weigh somewhere between about 150 and 100,000 times the mass of the Sun. A handful of promising candidates have been proposed, including one suspected to sit at the centre of a dense star cluster called Omega Centauri, identified through the unusually fast motion of stars near its core. But compared to the well-confirmed populations of stellar mass and supermassive black holes, this middle category remains far less certain, with ongoing debate about whether specific candidates are genuinely black holes or can be explained some other way. It's one of several places where the map of what we know about black holes still has real gaps in it. Gaps astronomers are actively working to fill with better instruments and more careful observation. Let's return for a moment to that word we used earlier, theoretical. It's worth being honest and clear about exactly where the solid, well-confirmed science ends and the more speculative frontier begins, since a good, trustworthy account of black holes has to hold both of these carefully, without blurring them together. What's firmly confirmed, supported by decades of careful observation, includes the existence of the event horizon as a real physical boundary, the existence of both stellar mass and supermassive black holes, the direct detection of black holes merging through gravitational waves, and the direct imaging of the shadow cast by two supermassive black holes, one at the heart of our own galaxy and one far beyond it, at the centre of the galaxy M87. These aren't hypotheses anymore. They're observed, measured, and repeatedly confirmed facts about the universe we live in. What remains genuinely theoretical, still actively debated among physicists, includes the true nature of the singularity at a black hole's center, since general relativity's prediction of infinite density is almost certainly a sign the theory has reached its limits rather than a literal description of reality. The eventual fate of information that falls into a black hole, tied up in that unresolved information paradox, also remains an open question. And the deeper question of how gravity and quantum mechanics can be combined into a single unified theory capable of describing what's actually happening inside a black hole's event horizon is, quite simply, one of the largest unsolved problems in all of modern physics, one that some of the most capable minds alive today are still working to untangle. There's something quietly humbling about sitting with both of these categories at once, the confirmed and the unconfirmed, side by side. We've learned to detect ripples in space and time itself, caused by objects so extreme that light cannot escape them, objects we've now photographed directly, from a distance of thousands and even millions of light years. And yet we still don't fully understand what's actually happening at the very centre of these objects, the place all that mass ultimately settles into. It's a reminder that even the most well-established science sits on a foundation that keeps extending outward into deeper unknowns, layer after layer. The closer we look, maybe that's part of what makes black holes such strange objects to sit with quietly late at night. They're not distant abstractions. There's very likely one sitting at the exact centre of the very galaxy, holding your own solar system in its orbit right now, quietly anchoring hundreds of billions of stars in a slow, patient turn that takes hundreds of millions of years to complete just once. And at the same time, that same object remains at its very core one of the deepest open questions in all of physics, a place where our best equations simply run out of answers, confirmed and mysterious all at once, massive and invisible all at once, sitting calmly at the heart of nearly every galaxy in the observable universe, including our own, while the stars around it, and the planets around those stars, and the quiet, breathing creatures on at least one of those planets, go on turning through their nights, mostly unaware of just how strange the centre of their own galaxy really is. For now, though, let's leave the singularities and the unresolved paradoxes where they belong, quietly unsolved, and turn our attention outward again, away from these strange, invisible points, and toward the vast, glowing structures that gather and grow around them. Because supermassive black holes like the one at the heart of our own galaxy don't sit alone in empty space. They sit at the very centre of enormous, swirling collections of stars, gas, and dust, hundreds of billions of stars in some cases, all bound together, all slowly turning around that same hidden point of impossible density. How exactly a galaxy comes to gather itself around a black hole like this, how the two grow and shape each other across billions of years, is a story that deserves its own quiet, careful telling. And that's exactly where we're headed next, drifting gently outward from the edge of the abyss, toward the wide, star-filled structures that call it home. Come back with me now, further along this long, unhurried river of cosmic time. Let your body settle again into stillness. Tonight we step back from individual stars and look at something larger, the enormous, gently turning cities of stars called galaxies, and in particular, the one we happen to call home. There is no need to hold on to every number or every name. Just let this wash over you slowly, the way distant light drifts across an open sky. If you have ever stepped outside on a truly dark, clear night, far from any city lights, you may have seen a faint pale band stretching across the sky, almost like a soft smudge of cloud that never moves. That band is not cloud at all. It is the combined light of hundreds of billions of stars, seen edge on, from within the very structure that contains them, our own galaxy, viewed from the inside, looking out along the flattened plane of its disk. Every one of those distant points of light, and countless more too faint or too far away to ever see with human eyes, belongs to the same enormous patient structure we are about to explore together. 100 billion suns gathered together. A galaxy, in the simplest possible terms, is an enormous collection of stars, gas, dust, and other material, all held together by gravity, all slowly orbiting a shared centre. Galaxies are not small. Even a modest galaxy can contain many billions of stars, spread across tens of thousands of light-years of space. And galaxies are not rare. The observable universe contains an almost incomprehensible number of them, scattered across the darkness in every direction we look. But galaxies are not all the same shape, and the differences between them tell a story about how each one came to be, how old it is, and what has happened to it over the long span of cosmic time. Nearly a century ago, an astronomer named Edwin Hubble looked carefully at the galaxies he could observe, and noticed that most of them fell into a small number of recognizable shapes. He organized them into a scheme that astronomers still use today, in a refined form, to describe and classify galaxies across the universe. Spirals, the graceful pinwheels. The first major shape is one you have probably seen in photographs, even if you did not know its name. Spiral galaxies have a flattened, rotating disk of stars, gas, and dust, with graceful curling arms winding outward from a brighter, denser central region called the bulge. Our own galaxy, the Milky Way, is a spiral galaxy, and we will return to its particular structure shortly. The spiral arms themselves are not fixed, solid structures, the way the arms of a pinwheel are fixed to its centre. They are better understood as regions of enhanced density, areas where gas and dust are compressed slightly more than their surroundings, triggering bursts of new star formation, because young, massive stars burn hot and blue, and because they live such short lives compared to the age of a galaxy, the arms of a spiral galaxy tend to glow with the light of young stars still being born, giving the arms their bright, distinctive appearance, even though the material moving through them is constantly changing. Many spiral galaxies also feature a straight bar of stars cutting through the central bulge, with the spiral arms extending from the ends of that bar rather than from the bulge itself. Astronomers call these barred spiral galaxies, and it turns out our own Milky Way belongs to this subtype as well. It can help to picture a spiral galaxy the way you might picture cream slowly swirling into a cup of coffee, caught partway through the stirring. The overall shape drifts and turns gracefully, curling arms trailing outward from the centre, and yet nothing about that swirl is rigid or fixed in place. Individual stars drift through the spiral arms, the way individual cars might pass through a slow-moving traffic jam on a highway, entering from behind, lingering briefly in the denser, brighter region, and eventually continuing onward and out the other side, while new stars are constantly born to take their place. The pattern of the spiral persists, elegant and recognizable across hundreds of millions of years, even though the specific stars making it visible are always slowly changing. Ellipticals, the calm and settled giants. The second major shape is quite different. Elliptical galaxies have no disk, no spiral arms, and often very little gas or dust remaining. They appear instead as smooth, rounded, glowing shapes, ranging from nearly spherical to distinctly stretched and oval, filled primarily with older, redder stars orbiting the galaxy's centre in a wide range of directions, rather than moving together in an orderly, flattened disk the way stars in a spiral galaxy do. Because elliptical galaxies generally lack the cold gas clouds needed to form large numbers of new stars, they tend to be relatively quiet places, astronomically speaking, with very little ongoing star formation. This is one of the clues that helps astronomers understand how elliptical galaxies come to exist. Many of them appear to be the result of large galaxy mergers, moments when two or more galaxies, often including spirals, collide and gradually combine over hundreds of millions of years. During this violent, drawn-out process, the neat orbital motion that once defined each galaxy's disk becomes scrambled, and much of the remaining gas is either consumed in a burst of star formation or blown away entirely, leaving behind the smooth, settled shape of an elliptical galaxy. We will return to this collision process a little later, because it is not just a historical curiosity. It describes an event our own galaxy may eventually experience. If a spiral galaxy feels a little like a young, restless dancer, still spinning and still being fed fresh material for new stars, an elliptical galaxy feels more like an elder who has settled comfortably into stillness. its most energetic years already behind it. The stars within it continue to orbit, drifting along their own long looping paths around the galaxy's shared centre. But without the fresh gas needed to spark new generations of bright, young stars, the overall glow of an elliptical galaxy tends to shift toward a softer, redder hue, dominated by older stars that have been shining steadily for billions of years. Asterisk, irregulars, and the smaller in-between shapes. Not every galaxy fits neatly into these two families. Irregular galaxies lack any clear, organized shape at all, appearing instead as somewhat chaotic gatherings of gas, dust, and stars. Some irregular galaxies were likely disrupted by a close gravitational encounter with a larger neighbour. Others may simply never have gathered enough mass or experienced the right conditions to settle into an orderly disk or a smooth sphere in the first place. Between the spiral and elliptical families, astronomers also recognize an intermediate type called lenticular galaxies, which have a flattened disk shape similar to a spiral galaxy, but lack the pronounced spiral arms and active star formation, appearing instead somewhat smooth and quiet, like a hybrid between the two major shapes, and scattered throughout the universe in far greater numbers than their larger, more famous cousins, are dwarf galaxies, small collections of anywhere from a few million to a few billion stars, often orbiting as satellites around larger galaxies, the way our own Milky Way is orbited by several smaller dwarf companions. It is easy, when picturing the universe, to imagine galaxies as being roughly similar in size to our own. But the truth is that most galaxies in the universe are actually far smaller and far fainter than the Milky Way. These dwarf galaxies rarely make it into dramatic photographs or popular imagination, yet they vastly outnumber the large, bright spirals and ellipticals that tend to capture our attention, quietly orbiting their larger neighbours or drifting alone through the vast spaces between the more prominent structures of the cosmos. Ask building galaxies from the bottom up. How does a galaxy actually come into being in the first place? This question connects directly back to an earlier point in our journey together, to the dark matter halos that began gathering matter during the universe's earliest, darkest ages. Just as those halos provided the gravitational foundation for the very first stars, larger and larger halos eventually provided the gravitational foundation for entire galaxies. The leading model astronomers use to describe this process is called hierarchical structure formation, sometimes described more simply as a bottom-up process. Rather than a galaxy the size of the Milky Way forming all at once, in one single dramatic collapse, the evidence overwhelmingly favours a much more gradual and additive story. Small clumps of gas and stars formed first, deep within relatively modest dark matter halos, scattered throughout the young universe. Over time, gravity drew these small structures together. They collided, merged, and combined again and again, building larger and larger galaxies out of many smaller pieces, somewhat the way a large snowball grows by rolling through the snow and gathering smaller clumps along its path. Observations using the James Webb Space Telescope have given astronomers a remarkable window into this process, revealing that galaxies in the very early universe tended to look smaller, clumpier, and far less organized than the graceful spirals and smooth ellipticals we see nearby today. Many lacked any clear disk or bulge at all, appearing instead as knotty, irregular regions of intense star formation. Only gradually, as mergers and continued gas accretion proceeded across billions of years, did galaxies settle into the more familiar, orderly shapes that dominate the universe around us today. There is a gentle kind of symmetry worth noticing here, one that echoes something from earlier in our journey together. Just as an individual star begins with the smallest, quietest imbalance in a cold cloud of gas, a galaxy begins the same way on a far grander scale, a slightly denser patch of dark matter drawing in slightly more material than the emptiness surrounding it, then slowly, patiently growing. Nothing about the universe seems to like sudden, complete creation. Almost everything we have discussed so far, stars, galaxies, and the very structures that hold them together, grows the same unhurried way, small beginnings compounding gradually into something vast. Given enough time and enough patience. I want to note briefly, since we'll explore this topic properly and in far more depth in a later chapter, that dark matter plays an absolutely central role in all of this galaxy formation, providing the essential gravitational framework that ordinary visible matter falls into and gathers around. For tonight, simply hold on to the basic outline. Small structures came first. Larger galaxies were assembled gradually, piece by piece, collision by collision, across the long unfolding of cosmic time, asterisk coming home to a galaxy called the Milky Way. With that broader picture in mind, let us turn our attention to the one galaxy each of us calls home, the Milky Way. Every star you have ever seen in the night sky with your unaided eyes, with only a small handful of rare exceptions, belongs to this single galaxy, one particular structure among the countless billions scattered throughout the observable universe. The Milky Way is a barred spiral galaxy, its disk stretching across roughly 100,000 light-years, though estimates for its precise extent vary somewhat depending on exactly how astronomers define its faint outer edges. Within that disk, astronomers estimate the Milky Way contains somewhere between 100 billion and 400 billion stars, a genuinely enormous range that reflects just how difficult it is to count stars accurately across such a vast structure, especially since much of our galaxy's own disk is hidden from view by thick, obscuring clouds of dust. Our galaxy's structure can be thought of as a small number of distinct, overlapping parts. At the very centre sits the nucleus, and surrounding it, a dense, roughly spherical bulge, populated largely by older stars, and threaded through with a bar-shaped structure of stars stretching outward from the core. Extending from the bulge, the galactic disk holds the majority of the Milky Way's gas, dust, and actively star-forming regions, organized loosely into several curving spiral arms. Our own Sun sits inside this disk, roughly 26,000 light-years from the galactic center, tucked within a relatively minor, partial arm structure sometimes called the Orion Spur, nestled between two larger, more prominent arms named Perseus and Sagittarius. Surrounding this entire disc-shaped structure, a much larger, more diffuse stellar halo extends outward, populated by ancient stars and dense, ball-shaped groupings called globular clusters, some containing hundreds of thousands of stars bound tightly together, among the oldest structures found anywhere within our galaxy. Beyond even this visible halo, astronomers infer the presence of a still larger, invisible halo of dark matter, extending the galaxy's true gravitational reach far beyond what any telescope can directly see, a subject we will return to properly in a future chapter. Try for a moment to hold the scale of our own small corner of this structure in mind. Light from the center of our galaxy takes about 26,000 years to reach us, meaning the glow we might associate with the galactic core, if we could somehow see straight through the dust that blocks it, would be showing us the galactic center as it existed 26,000 years in the past, long before any written human history began. And that distance, vast as it feels, is still less than a third of the way across our galaxy's full disk. The Milky Way is, by any ordinary human measure, almost impossibly large, and our entire solar system, sun, planets, moons and all, occupies only the tiniest, most unremarkable corner of it, quietly orbiting the galactic center once every 220 to 230 million years or so, a single galactic year that has, so far, only completed a small handful of times since our solar system first formed. Asterisk, the quiet monster at the center, at the very heart of the Milky Way, hidden behind thick clouds of gas and dust that block ordinary visible light entirely, lies an object astronomers call Sagittarius, a star, usually written with an asterisk after its name. This object is a supermassive black hole, containing roughly 4 million times the mass of our Sun, confirmed through careful, patient observations of stars orbiting tightly and rapidly around this seemingly empty point in space. This discovery was significant enough that two of the astronomers involved, Andrea Ghez and Reinhard Genzel, were awarded the Nobel Prize in Physics in 2020 for their work confirming its nature, tracking the orbits of individual stars swinging around this invisible point in space for years at a time, plotting their paths with painstaking precision until the mass and density hidden at the centre left no other reasonable explanation. Despite its enormous mass, Sagittarius A star is, by the standards of supermassive black holes found at the centres of other galaxies, relatively calm and quiet, not actively pulling in and consuming large amounts of surrounding material at any dramatic rate right now. The region immediately around it, however, remains an extraordinarily crowded and energetic place, home to a dense cluster of stars packed far more tightly together than anywhere else in our galaxy, along with young, massive stars whose presence so close to a supermassive black hole still puzzles astronomers, since the intense gravitational forces in that region would seem to make ordinary star formation there quite difficult. Consider for a moment just how strange it is that something so powerful can sit so quietly at the heart of the very galaxy that surrounds you every single night. Every star you have ever wished upon, every constellation you have ever traced with your eyes, has spent its entire existence gently orbiting this hidden, invisible anchor tens of thousands of light years away, patient and largely undisturbed, holding the whole vast structure of the Milky Way together through nothing more than the quiet, constant pull of its gravity. Asterisk, a galaxy destined to meet its neighbour, perhaps? For decades, one of the most confidently stated predictions in all of astronomy involved the eventual fate of our own galaxy. The Andromeda Galaxy, our nearest large galactic neighbour, sits roughly 2.5 million light-years away, and detailed measurements using the Hubble Space Telescope confirm that Andromeda is moving steadily closer to the Milky Way, drawn in by the mutual gravitational pull between the two galaxies. Based on this motion, astronomers long predicted that the Milky Way and Andromeda would collide and gradually merge into a single larger galaxy, sometimes nicknamed Milkomeda, occurring somewhere around 4 to 4.5 billion years from now, with the merger fully completing perhaps 2 billion years after that. It is worth pausing to clarify what a galaxy collision actually involves, since the word collision can conjure an image of violent direct impact. In reality, the space between individual stars within a galaxy is so enormous that the likelihood of any two stars actually striking one another during such a merger is exceedingly small. What changes dramatically instead is the overall structure and shape of the galaxies involved, as gravity gradually pulls stars, gas, and dust into new orbits and new configurations, stretching out long, faint streams of stars, triggering bursts of new star formation as gas clouds are compressed and disturbed, and eventually smoothing the two neat spiral disks into a single larger elliptical galaxy, not unlike the settled, orderly ellipticals we discussed earlier in this chapter. Picture two enormous, softly glowing whirlpools of light, each many thousands of light years wide, drifting slowly toward one another across an almost incomprehensible gulf of empty space. As they draw close, their mutual gravity begins to pull long, faint ribbons of stars away from each edge of each galaxy, stretching them out into delicate, curving arcs and streams, some reaching hundreds of thousands of light years into the surrounding darkness. The two galaxies may swing past one another once, twice, sometimes several times over hundreds of millions of years, each pass slowing their relative motion a little further, before gravity finally pulls them together for good, their two separate spinning disks gradually dissolving into one another, their neatly ordered orbits scrambling into the smoother, more random motion that defines an elliptical galaxy. It is a process unfolding over such an enormous span of time that no single moment within it would look particularly dramatic. And yet, viewed across its full span, it represents one of the most transformative events a galaxy can ever experience. I want to share something more recent and genuinely interesting here, because it reflects exactly the kind of honest uncertainty that makes real science so compelling. In June of 2025, a team of astronomers led by Till Sawala at the University of Helsinki published a detailed new study in the journal Nature Astronomy, using the most precise and up-to-date measurements available from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft. Rather than simply confirming the long-predicted collision, their extensive simulations, incorporating a wider and more carefully measured range of variables than earlier studies, including the gravitational influence of smaller nearby galaxies such as the Large Magellanic Cloud and the Triangulum Galaxy, found something considerably less certain than the earlier consensus suggested. Running 100,000 separate simulations forward across the next 10 billion years, the team found that a direct collision between the Milky Way and Andromeda now appears to have only about a 50% probability, essentially an even coin flip, rather than the near certainty many earlier studies had implied. According to this newer analysis, a completely head-on collision remains genuinely unlikely, with the team estimating less than a 2% chance of that particular, most dramatic scenario. Instead, in most simulations that do eventually lead to a merger, the two galaxies first swing past each other in a close but non-direct encounter, gradually losing orbital energy through gravitational interaction, before eventually spiraling together and merging over a longer stretch of time. But in a substantial fraction of the simulated scenarios, the two galaxies pass each other at a large enough distance that no merger occurs at all, at least not within the 10 billion year span the researchers modelled. I share this recent finding not to contradict the popular and often repeated story you may have heard elsewhere, but because I think it captures something genuinely beautiful about how science actually works. For over a decade, the collision between the Milky Way and Andromeda was treated as one of the most secure long-term predictions in all of astronomy. New data, gathered more precisely and analysed more thoroughly, has revealed that the true picture is considerably more uncertain than previously understood, and researchers now expect additional data from the Gaia mission to help narrow that uncertainty further as it continues to be analysed in the coming years. Whatever the eventual outcome turns out to be, whether our galaxy merges with its neighbour or continues on a separate path indefinitely, this uncertainty itself is a reminder that even our most confident-sounding predictions about the deep future remain open to revision as our tools and our data continue to improve. Whether or not that particular collision ever fully occurs, it is worth remembering that our Sun's own future is far more firmly settled than the galaxy's. As we explored earlier in this journey, our Sun will leave its stable, main sequence life behind in roughly 5 billion years, swelling into a red giant regardless of anything happening to the wider galaxy around it. And if the Milky Way and Andromeda do eventually merge, astronomers studying the various simulated outcomes note that individual solar systems like our own would very likely be swept outward into new, more distant orbits within the resulting merged galaxy rather than being destroyed outright, since, as we discussed, the stars themselves are unlikely to actually collide. Asterisk, a galaxy among countless galaxies. Step back now for a moment and hold the full shape of this chapter's story together. Galaxies, immense gently rotating collections of billions of stars, began as small scattered clumps of matter within the dark matter halos that formed during the universe's earliest ages. Gravity drew these small structures together again and again across billions of years, building the graceful spirals, the smooth, settled ellipticals, and the countless irregular and dwarf galaxies that fill the observable universe today. Our own galaxy, the Milky Way, took shape through exactly this same slow, patient process, gathering its hundreds of billions of stars into a flattened, spinning disk wrapped in spiral arms, anchored by a supermassive black hole at its quiet hidden centre, and drifting through space alongside its neighbour Andromeda toward a future that remains, even now, genuinely uncertain. There is something worth resting on, here at the end of this chapter, in the sheer scale of what we have just described. A galaxy containing hundreds of billions of stars is, itself, only one among countless similar structures scattered throughout the observable universe, each one its own vast city of stars, its own long history of collision and formation, stretching back across billions of years. Take a slow breath and let yourself sit for a moment inside that scale, One small, warm world circling one ordinary star, itself circling the quiet hidden heart of one galaxy among more galaxies than anyone could ever hope to count. And yet, even a structure this large, this old, and this seemingly permanent is still held together, still shaped, still bound by something we have only mentioned briefly so far in this journey, an invisible scaffolding of matter that outweighs everything we can actually see. That invisible framework and the strange unseen force that is slowly pulling the wider universe apart, even as gravity holds galaxies like our own together, is where we will travel next, drifting further along this long quiet river of cosmic time, into the deepest and strangest mysteries the universe still holds. Settle in again, and let this next part of the journey feel a little more like coming home. Everything we have explored so far has taken us across scales almost too large to hold in the mind. Entire galaxies, vast collisions unfolding over billions of years. Tonight, we come closer. We are going to walk gently through our own small neighborhood of space, the collection of worlds orbiting the star that lights our mornings and warms our skin. This is the story of the solar system, how it formed, what it contains, and the quiet icy edges where it finally fades into the dark beyond. Let your breathing slow and let your thoughts drift outward, past the walls of this room, past the sky, out into the wide orbiting family of worlds we call home. Think of the last time you watched a sunset, the way the light softened and reddened as it slipped toward the horizon. That same sun, the one you have watched rise and set your entire life, is the anchor of everything we are about to explore. Every planet, moon and drifting fragment of rock or ice in this chapter owes its existence and its orbit to that one steady, glowing star. It can be strange to think of the sun not as a backdrop to our lives, but as the central character in a much older story, one that began long before Earth existed, and one that patiently, gradually, built the very ground beneath you. Asterisk. A cloud that decided to become something around 4.6 billion years ago. In a quiet, unremarkable region of our galaxy, there was no sun and there were no planets. There was only a cloud, a vast, slowly drifting collection of gas and dust left behind by earlier generations of stars that had lived and died and scattered their material back into space. Astronomers call this cloud the solar nebula, and its story is, in many ways, a smaller, more intimate echo of the very first stars we explored earlier in this journey. Something disturbed that quiet cloud. Perhaps the shock wave from a nearby exploding star rippled through it, or perhaps the gentle cumulative pull of a passing structure nudged it out of balance. Whatever the specific trigger, gravity began to win, exactly as it always does. The cloud started to contract, and just as we saw with the very first stars, that contraction caused it to spin faster and flatten into a wide rotating disk, with the vast majority of its material gathering into a dense, glowing sphere at the center. That sphere would become the sun. The remaining material, spread thinly throughout the surrounding disk, began its own slow transformation. Tiny grains of dust, no larger than specks caught in a sunbeam, gently collided and stuck together, forming slightly larger clumps. Those clumps collided with other clumps, gathering more material still, in a patient, cumulative process astronomers call accretion. Over the course of a few million years, a relatively short span by cosmic standards, these growing bodies became what astronomers call planetesimals, rocky or icy building blocks, ranging from the size of a boulder to the size of a small moon. And through countless further collisions, some planetesimals grew large enough and gathered enough surrounding material to become true planets. Where each planet ended up forming had everything to do with temperature. Close to the newly forming sun, it was far too hot for ice or other easily evaporated materials to survive, so only rocky metallic material could condense and stick together, giving rise to the small, dense, rocky worlds we now call the inner planets. Farther out, beyond a boundary astronomers sometimes call the frost line, temperatures dropped low enough for ice to remain solid, allowing much larger amounts of material, ice included, to gather together, giving rise to the enormous gas and ice giants of the outer solar system. It is worth pausing on just how patient and gradual this entire process really was. Nothing about the birth of a solar system happens quickly, at least not by human standards. The transformation from scattered dust to fully formed planets unfolded across tens of millions of years, an achingly slow accumulation, collision after gentle collision, each one adding only the smallest amount of new material. And yet, given enough time, that slow accumulation was more than sufficient to build worlds as large as Jupiter, and as intricate and varied as the small rocky planet you are resting on right now. Once the young sun's nuclear fusion finally ignited, much as we described in an earlier chapter, it unleashed a powerful stream of charged particles called the solar wind, sweeping much of the remaining gas and dust out of the inner solar system entirely. What remained, scattered and settled, became the family of worlds we still recognize today. Mercury, closest to the flame. Let us begin our tour close to home, starting with the planet nearest the Sun. Mercury is small, only a little more than a third the width of Earth, and it completes a full orbit around the Sun in just 88 days, faster than any other planet, which is part of why it was named for the swift messenger god of ancient Rome. Mercury has almost no atmosphere to speak of, only the faintest trace of gas, far too thin to trap any meaningful heat or to soften the planet's extremes. This creates a strange and punishing contrast. During the day, temperatures on Mercury's surface can climb to around 800 degrees Fahrenheit, hot enough to melt certain metals. At night, with no atmosphere to hold that heat in place, temperatures plunge to nearly 300 degrees below zero. Despite this blistering daytime heat, Mercury is not actually the hottest planet in the solar system, a distinction we will get to shortly. And strangely, deep within craters near Mercury's poles, regions that never receive any direct sunlight at all, scientists have found evidence of water ice, quietly preserved in permanent shadow, despite the planet's otherwise scorching reputation. Venus, wrapped in a furnace of its own making. Moving outward, we come to Venus, often called Earth's twin, because of how similar the two planets are in overall size and structure, but any resemblance ends there. Venus is wrapped in an extraordinarily thick atmosphere, made overwhelmingly of carbon dioxide, with clouds composed of sulfuric acid drifting high above its surface. This dense atmosphere traps heat with tremendous efficiency, driving what scientists call a runaway greenhouse effect, and as a result, Venus is the hottest planet in the entire solar system, with a surface temperature of around 870 degrees Fahrenheit, hot enough to melt lead, and notably hotter even than Mercury, despite being considerably farther from the Sun. The atmospheric pressure at Venus's surface is roughly 93 times greater than what we experience at sea level on Earth, comparable to the crushing pressure found nearly a mile beneath the surface of Earth's oceans. Venus also rotates unusually slowly, and in the opposite direction from most other planets, meaning a single day on Venus, from sunrise to sunrise, actually takes longer than a full Venusian year. Beneath its thick, churning clouds, Venus hides a rocky, volcanic surface shaped by mountains and volcanoes, though direct observation of that surface from above is essentially impossible without instruments capable of piercing straight through the dense atmospheric haze. Astaroth, the one we know. Next comes our own home, Earth, the third planet from the Sun, and as far as anyone has ever confirmed, the only place in the entire universe where life is known to exist. We will not linger too long here, since Earth's story is, in many ways, the story each of us is already living. But it is worth pausing to appreciate a few of the specific conditions that make our planet so remarkable. Earth sits at almost exactly the right distance from the Sun to allow liquid water to exist stably on its surface, neither boiling away as it does closer to the Sun, nor freezing permanently solid as it does farther out. Earth also possesses a strong magnetic field, generated deep within its molten metallic core, which helps shield the planet's surface and atmosphere from much of the Sun's more damaging radiation. Earth is the largest of the four inner, rocky planets, and it holds another distinction worth mentioning gently here, since it will not be the topic of any single chapter in this journey, but deserves a quiet nod all the same. It is the only planet in our solar system known to host a large single moon so close in size relative to its host planet, a companion whose steady gravitational pull helps stabilize the tilt of Earth's axis, in turn helping to stabilize our planet's seasons across long stretches of time. There is something worth resting on here, in the quiet middle of this planetary tour. Of every world we will describe tonight, rocky or icy, blazing or frozen, only this one, as far as anyone has ever confirmed, has given rise to oceans, forests, and the particular kind of stillness you are resting in right now. Every other planet in our solar system is by comparison silent and empty, a landscape of rock, gas or ice, with no one to notice its beauty. Whatever else this chapter teaches you about the wider solar system, it is worth pausing, just for a moment, to appreciate how rare and unlikely a quiet, breathing world like this one truly is. Asterisk, Mars, the red and restless, neighbours. Beyond Earth lies Mars, often called the red planet, because of the reddish, rust-coloured dust, rich in iron oxide, that covers much of its surface. Mars is considerably smaller than Earth, and its atmosphere is roughly 100 times thinner, far too thin to retain much heat or to support liquid water on the surface today. Though a great deal of evidence suggests that Mars once had a thicker atmosphere and flowing liquid water billions of years in its past. Mars is home to some genuinely extreme geological features. Olympus Mons, a massive volcano on the Martian surface, rises roughly 15.5 miles above the surrounding terrain, making it by far the tallest known volcano in the entire solar system, nearly 3 times the height of Mount Everest above sea level here on Earth. Because its thin atmosphere holds so little heat, temperatures on Mars swing dramatically, and the planet is prone to vast, sweeping dust storms that can, at times, engulf the entire globe. Asterisk, crossing into the asteroid belt beyond Mars. Before we reach the giant planets of the outer solar system, we pass through a wide, scattered region called the asteroid belt, a band of countless rocky bodies orbiting the Sun between Mars and Jupiter. It is tempting to imagine this region as impossibly crowded, the way it is sometimes portrayed in films, ships weaving frantically between tumbling boulders. In reality, the asteroid belt is remarkably empty. Its countless objects spread across such a vast volume of space that spacecraft have passed through it repeatedly, without any real risk of collision. The largest object within the asteroid belt is Ceres, discovered in 1801, and, for a time uncertain in its classification, considered first a planet, then an asteroid, before finally being recognized in 2006 as a dwarf planet, a category we will return to shortly. Ceres measures roughly 580 miles across and contains about a quarter to a third of the entire mass of the whole asteroid belt combined, despite occupying only a small fraction of the belt's total volume. Unlike most of its rockier, irregularly shaped neighbours, Ceres is large enough that its own gravity has pulled it into a roughly spherical shape, and evidence gathered by NASA's Dawn spacecraft, which orbited Ceres between 2015 and 2018, suggests it may even contain significant amounts of water ice, and possibly a layer of salty liquid water beneath its dusty surface. Many astronomers describe Ceres as something like an embryonic planet, a world that began forming in earnest but was ultimately prevented from growing any larger by the powerful, disruptive gravity of nearby Jupiter. Jupiter, the giant that shaped everything around it. Speaking of Jupiter, we now arrive at the largest planet in our entire solar system, a true giant among giants. Jupiter is so enormous that roughly 11 Earths could be lined up side by side across its diameter, and its mass is more than twice that of every other planet in the solar system combined. Unlike the small, rocky worlds we just explored, Jupiter is what astronomers call a gas giant, composed overwhelmingly of hydrogen and helium, with no solid surface to speak of at all, only ever deepening layers of gas transitioning gradually into strange exotic states of matter deep within its interior. Jupiter's atmosphere churns with colourful, turbulent bands of cloud, and it hosts one of the most famous storms in the entire solar system, the Great Red Spot, an enormous swirling hurricane-like storm large enough to comfortably swallow the entire planet Earth. one that has been continuously observed for centuries. Jupiter also possesses an enormous number of moons, more than 90 currently confirmed, including 4 particularly large ones: Io, Europa, Ganymede, and Callisto, first observed by Galileo Galilei in 1610, and still called the Galilean moons in his honour. Ganymede, the largest of these 4, is actually larger than the planet Mercury, making it the single largest moon anywhere in our solar system. Jupiter's sheer gravitational influence has profoundly shaped the entire solar system around it, helping to sculpt the asteroid belt, flinging countless smaller bodies into distant orbits, and even helping to shield the inner planets, including our own, from a portion of the debris that might otherwise strike them. It can help to imagine Jupiter as something like a quiet, watchful guardian, standing sentinel at the outer edge of the inner solar system. Its immense gravity has, over billions of years, gently swept many wandering comets and asteroids out of harm's way, or pulled them in entirely, absorbing impacts that might otherwise have found their way towards the smaller, more fragile worlds closer to the Sun. Astronomers still debate exactly how much protection Jupiter genuinely offers Earth in this way, but there is little doubt that its presence, so large and so early in the solar system's history, helped shape the safer, more settled architecture that allowed a planet like ours the time it needed to quietly develop life. Saturn, adorned with rings of ice. Beyond Jupiter lies Saturn, the second largest planet in our solar system, and, without question, the most visually distinctive, thanks to its magnificent system of rings. Those rings are made up of countless individual particles of ice, mixed with smaller amounts of rocky debris, ranging in size from tiny grains of dust to chunks as large as a house, all orbiting Saturn in a thin, flattened band that can appear, from a distance, almost like a single solid structure. Saturn is, like Jupiter, a gas giant composed primarily of hydrogen and helium, and it is remarkable for being so low in density that, in theory, if you could find a body of water large enough to hold it, Saturn would actually float. Saturn hosts a large family of moons as well, and among them, Titan stands out as particularly extraordinary. Titan is the second largest moon in the entire solar system, and it is the only moon known to possess a thick, substantial atmosphere, composed mostly of nitrogen, along with lakes and rivers of liquid methane and ethane spread across its frigid surface. A genuinely alien landscape that continues to fascinate scientists studying the possible chemistry of other worlds. Imagine, for a moment, drifting slowly past Saturn from a great distance, watching sunlight catch the countless icy particles that make up its rings, each one far too small to see individually, yet together forming something that looks, from afar, almost impossibly delicate and deliberate, like a single thin band of light wrapped gently around the planet's middle. It is one of the most quietly beautiful sights in the entire solar system, and it exists purely as the natural, patient result of gravity, ice, and time. Uranus, tilted on its side, continuing outward, we reach Uranus, the first of the 2 so-called ice giants in our solar system. While Uranus does share some similarities with Jupiter and Saturn, its interior contains a much larger proportion of water, ammonia, and methane in dense fluid states, distinguishing it meaningfully from the hydrogen and helium-dominated gas giants closer to the Sun. Uranus takes on a pale cyan blue colour caused by methane in its upper atmosphere, which absorbs red light and reflects blue and green light back toward observers. Uranus is genuinely unusual in one particular way that sets it apart from every other planet in our solar system. Rather than spinning upright, more or less like a top, Uranus is tipped over onto its side, rotating at an extreme angle of roughly 98 degrees relative to its orbit. This unusual tilt is thought to be the result of a massive collision earlier in the planet's history, though the precise details of that ancient impact remain a topic of ongoing study. Because of this dramatic tilt, Uranus experiences some of the most extreme seasons found anywhere in the solar system, with each of its poles experiencing roughly 21 years of continuous sunlight, followed by roughly 21 years of continuous darkness across its lengthy 84-year orbit around the Sun. Neptune, windswept and distant, Finally, at the outer edge of the traditional 8 planets, we reach Neptune, the second ice giant and the most distant planet from the Sun. Despite receiving only a tiny fraction of the sunlight and warmth that reaches Earth, Neptune is home to the most violent winds recorded anywhere in the solar system, with measured wind speeds exceeding 1,300 miles per hour, driven in part by significant internal heat that Neptune still radiates outward from its formation billions of years ago. Neptune shares Uranus's deep blue colouring, caused by methane in its atmosphere, though Neptune's blue tends to appear noticeably richer and more vivid. Neptune's largest moon, Triton, is itself an unusual and fascinating world, orbiting Neptune in the opposite direction from the planet's own rotation, a strong indication that Triton did not form alongside Neptune at all, but was instead captured later by Neptune's gravity, likely originating from the same distant icy region of the solar system we are about to explore next. Beyond the planets, into the realm of ice past Neptune, the solar system does not simply end. It gradually transitions into a vast frigid region called the Kuiper Belt, stretching from roughly 30 to 50 times the distance between Earth and the Sun. This distant, icy region is home to countless small frozen bodies, remnants left over from the early solar system's formation, along with several recognized dwarf planets, including Pluto, whose reclassification from full planet to dwarf planet in 2006 remains, even now, a point of gentle debate and nostalgic disagreement among astronomers and the public alike. Farther still, at distances almost too vast to comfortably imagine, lies a theorized region called the Oort cloud, a vast, roughly spherical shell of icy material believed to surround the entire solar system, extending anywhere from around 2,000 to as far as 100,000 times the distance between Earth and the Sun. I want to be especially clear and honest about something here. The Oort cloud has never actually been directly observed or imaged by any telescope or spacecraft. Its existence remains technically an inference, a theoretical explanation supported by the behavior of certain comets, rather than something astronomers have confirmed through direct detection. It is, nonetheless, very widely accepted among astronomers as the most likely explanation for where certain comets originate, since the physics involved fits remarkably well with everything else we understand about the early solar system's formation. Comets, wanderers from the cold, dark edges. This brings us gently to comets themselves, icy, dusty wanderers that occasionally journey in from these distant frozen reaches into the warmer regions of the inner solar system near the Sun. As a comet approaches the Sun, its outer layers of ice begin to warm and vaporize, releasing gas and dust that form a glowing temporary atmosphere around the comet's solid core, called a coma, along with the long, glowing tail so often associated with comets in the night sky. A tail that always points away from the Sun, shaped and pushed outward by the pressure of sunlight and the solar wind, regardless of the direction the comet itself happens to be traveling. Astronomers generally divide comets into 2 broad families, based on how long they take to complete a single orbit around the Sun. Short-period comets, completing their orbits in under 200 years, are thought to originate primarily from the Kuiper Belt, the icy region just beyond Neptune we described a moment ago. Long-period comets, some taking many thousands of years to complete a single orbit, are believed to originate from that much more distant, theorized Oort cloud, occasionally nudged out of their extremely distant, stable orbits by the gentle gravitational influence of a passing star, or by the broader tidal pull of our galaxy itself, sending them tumbling inward on an extraordinarily long journey toward the warmth of the inner solar system. There is something quietly moving about the journey a single long-period comet makes. Some of these icy travellers spend hundreds of thousands, even millions of years drifting through the profound cold and darkness of the outermost solar system, moving so slowly and so far from any source of light that they remain essentially frozen and unchanged, waiting. Then, disturbed ever so slightly, they begin an achingly long fall inward, taking thousands of years just to reach the inner solar system, before finally, briefly, blazing to life near the Sun, and swinging back outward again into the dark, perhaps never to return within the span of any human civilization that might happen to witness their passing. Asterisk. A family bound together by gravity. Step back now, and hold the whole shape of our solar system together in your mind. One more time, gently. A single ordinary star, warming a small rocky world tucked comfortably in its middle distance, surrounded by 3 additional rocky siblings closer to the sun's heat, 4 enormous, colourful giants further out, a scattered belt of rocky debris and one small, embryonic world caught between them, and finally a distant icy frontier stretching outward into the true edge of the sun's gravitational reach, where comets sleep for millions of years before occasionally waking to make their slow, silent journey back toward the light. All of it, every planet, every moon, every distant icy wanderer, formed from the same slowly spinning cloud of gas and dust, gathered patiently by gravity across a span of only a few tens of millions of years, itself a relatively brief moment compared to the many billions of years since. Our solar system is, in this sense, a small, intimate story, nested within the much larger story we have been following together across this entire journey, one particular cloud, among countless others scattered throughout our galaxy, that happened to collapse and spin and gather itself into a sun, and a small blue living world, quietly circling that sun ever since. And yet, even as we rest here, safely within the boundaries of our own solar system, it is worth remembering that the universe holds an almost uncountable number of other clouds, other young stars, and other planets, forming and settling into their own quiet orbits around distant suns we have never seen with our own eyes. Some of those distant worlds astronomers have discovered are stranger and more varied than anyone once imagined possible, and what we have learned about them, and what it might mean for the deeper question of whether we are truly alone, is where our journey will travel next. Ret here a while longer, and let your mind drift outward once more. We have spent time walking through our own small family of worlds, the planets, moons, and icy wanderers that circle our sun. Tonight, we step beyond that boundary entirely, out past the edge of our solar system, into the darkness between the stars, where countless other suns quietly hold their own families of planets, some near, some almost unimaginably far. For a very long stretch of human history, this was pure speculation, an old and beautiful guess with no way to confirm it. Tonight we explore what changed, and what astronomers have actually found out there in the dark. Let your body settle a little deeper into stillness. There is nothing urgent here, only distant light, and the patient work of people determined to find out what it is trying to tell us. Consider for a moment the simple act of looking up at a clear night sky and picking out a single, faint star. That star, whatever it is, has almost certainly been shining for far longer than human civilization has existed, and around a great many of these stars, scattered across the darkness in every direction, worlds are quietly circling, some scorched and barren, others cold and icy, and perhaps, here and there, a few gently temperate, not unlike the world you are resting on right now. For most of human history, we had no way of knowing this for certain. We could only wonder and imagine and wait. Asterisk, a question that waited centuries for an answer. For most of recorded history, the question of whether other stars might have their own planets was little more than philosophy. Ancient thinkers speculated about it, poets imagined it, but there was no way, with the instruments available, to actually detect a planet orbiting a star other than our own sun. Stars themselves are already almost unimaginably distant, and the planets that might circle them are smaller, dimmer, and utterly lost in the glare of their much brighter host stars. Trying to see a planet directly, next to its star, has often been compared to trying to spot a firefly hovering beside a lighthouse beam from thousands of miles away. It was not until the 1990s that astronomers finally confirmed the first planets orbiting stars beyond our own sun, and this discovery fundamentally transformed astronomy. Since then, the pace of discovery has only accelerated. As of early 2026, astronomers have confirmed more than 6,000 exoplanets, a term simply meaning a planet found outside our own solar system. with several thousand additional candidates, still awaiting the careful, patient confirmation that turns a promising signal into a verified discovery. And this number continues climbing, with new planets added to the official record on a rolling, ongoing basis, sometimes dozens in a single week. It is worth sitting for just a moment with how quickly this entire field of knowledge has come into being. Someone who was already an adult when the very first confirmed exoplanet was announced has, within their own single lifetime, watched that number grow from one lonely, uncertain discovery to more than 6,000 confirmed worlds. An entire branch of astronomy essentially built from nothing within a few short decades. Few areas of science have expanded quite so quickly, or quite so dramatically reshaped our basic picture of what the universe actually contains. How, though, do astronomers actually find something as small, faint and distant as a planet, when even seeing the star it orbits already pushes the very limits of our best telescopes? The methods involved are clever, patient, and, in their own way, quite beautiful, relying not on brute force but on careful, precise measurement of the smallest possible changes in starlight. Asterisk. Watching for a shadow passing across a star. The most productive method astronomers currently use is called the transit method, and it relies on a wonderfully simple idea. If a planet's orbit happens to be aligned in just the right way, from our vantage point here on Earth, that planet will periodically pass directly in front of its star, blocking a tiny, tiny fraction of that star's light as it does. This dip in brightness is almost absurdly small, often just a tiny fraction of 1%, roughly comparable to the change in light you might notice if a single gnat flew across the beam of a distant spotlight. But with sufficiently sensitive instruments, watching a single star continuously and precisely over long stretches of time, that faint repeating dip becomes detectable and measurable. If astronomers observe this dimming repeating at regular intervals, they can be reasonably confident they have found a planet, and the details of that dimming reveal a remarkable amount of information. The depth of the dip tells astronomers the planet's approximate size, since a larger planet blocks more light than a smaller one. The regular timing between each dip reveals the planet's orbital period, how long it takes to complete one full circuit around its star. Space telescopes purpose-built for this kind of patient, continuous monitoring, first Kepler and more recently the Transiting Exoplanet Survey Satellite, known as TESS, have been responsible for the discovery of thousands of exoplanets, using exactly this method, staring steadily at enormous numbers of stars simultaneously, waiting for that telltale rhythmic flicker. There is something quietly moving about the patience this method demands. A telescope using the transit technique cannot simply glance at a star once and know whether it hosts a planet. It must watch faithfully and continuously for the exact same tiny dimming to repeat itself, again and again at precisely regular intervals, sometimes over the course of months or years, before astronomers can be confident they are looking at a genuine planet rather than some other passing coincidence. It is not so different, in spirit, from watching the moon rise from the same window, night after night, and only gradually coming to trust the rhythm of its return. Asterisk, listening for a star's gentle wobble. The second major method, called the radial velocity technique, takes a fundamentally different approach. Rather than watching for a planet blocking its star's light, this method looks for something more subtle, the way a planet's gravity gently tugs on its host star in return. It is easy to imagine a star sitting perfectly still while a planet orbits obediently around it. But in reality, both bodies orbit their shared centre of mass, called the barycenter. For a star far more massive than its orbiting planet, this shared point sits very close to the star's own centre, but it is not exactly at the centre, which means the star itself traces out a small, repeating wobble as the planet swings around it. That wobble is impossibly small to see directly, even with the most powerful telescopes, but it can be detected indirectly through its effect on the star's light. As the star wobbles very slightly toward us, its light compresses just slightly toward the blue end of the spectrum. As it wobbles very slightly away from us, its light stretches just slightly toward the red end of the spectrum. This shifting back and forth, called the Doppler effect, the same basic principle behind the changing pitch of a passing ambulance siren, can be measured with extraordinarily precise instruments, allowing astronomers to detect the faint gravitational fingerprint of a planet they cannot even see, sometimes a shift in the star's light of only a few centimeters per second, a change smaller than an ordinary walking pace, measured across a distance of trillions of miles. This method also offers something the transit method alone cannot: a reasonably direct estimate of a planet's mass, since a heavier planet produces a stronger, more noticeable wobble in its host star. Astronomers frequently combine both methods together, since each compensates for the other's limitations. A star observed transiting reveals a planet's size, while that same star's subtle wobble reveals the planet's mass, and together those two measurements allow scientists to calculate the planet's density, offering a meaningful clue about whether a given world is likely rocky, icy, or predominantly gaseous. Beyond these two dominant techniques, astronomers have developed a handful of additional methods as well, each suited to particular kinds of planets or particular circumstances. Gravitational microlensing takes advantage of a strange effect predicted by Einstein's theory of relativity, in which the gravity of a star and its planet, passing directly in front of a much more distant background star, can briefly bend and magnify that background star's light in a distinctive, telltale pattern, and a small number of exoplanets, generally large, young and orbiting relatively far from their host stars, have even been captured through direct imaging, meaning astronomers have managed to photograph the faint glow of the planet itself, separated from its much brighter star. Each of these methods carries its own strengths and limitations, together forming a broader toolkit that has allowed astronomers to build up the remarkable catalogue of worlds we now have. Asterisk, not too close and not too far. Once a planet has been detected and its basic properties measured, one of the very first questions astronomers ask is whether that planet sits within what is often called the habitable zone of its star, sometimes given the friendlier nickname of the Goldilocks zone, borrowed from the old children's story about porridge that was neither too hot nor too cold, but just right. The idea itself is fairly intuitive once you sit with it for a moment. Every star radiates heat outward into the space surrounding it, and a planet's temperature depends heavily on how close it orbits to that heat source. Too close to its star, and any water on a planet's surface would boil away entirely, evaporating into space. Too far from its star, and any surface water would freeze solid, locking a planet in permanent ice. Somewhere in between those two extremes lies a band of orbital distances where conditions could, at least in principle, allow liquid water to exist stably on a planet's surface, and it is this particular band that astronomers call the habitable zone. It is worth being honest and careful here, since the term habitable zone can sound more definitive than it really is. Sitting within a star's habitable zone does not guarantee that a planet actually has liquid water, let alone life. It simply means the orbital distance is right. In principle, for that possibility, assuming a suitable atmosphere and other favourable conditions are also present. Venus, for example, technically sits near the inner edge of our own Sun's habitable zone, and yet its thick, punishing atmosphere has made it one of the most hostile environments in the entire solar system, as we explored in our previous chapter. The habitable zone, in other words, is a genuinely useful starting point for narrowing down where to look, not a guarantee of anything more specific. It might help to think of the habitable zone less as a promise, and more as an invitation, a polite suggestion that a particular world might be worth a closer look. A planet within that zone still needs the right kind of atmosphere, the right chemical ingredients, and, quite possibly, the right kind of protective magnetic field before liquid water, let alone life, could ever take hold. Astronomers use the habitable zone the way a careful traveller might use a rough map, not as a guarantee of what they will find, but as a sensible place to begin the search. The width and location of a habitable zone also depends heavily on the particular star involved. Hotter brighter stars push their habitable zones much farther outward, while smaller, cooler stars, including the exceptionally common dim red dwarf stars we discussed in an earlier chapter, have much narrower habitable zones located quite close to the star itself. This detail turns out to matter a great deal for one of the most fascinating planetary systems astronomers have ever discovered. Asterisk, a tiny, crowded solar system of its own. In February of 2017, astronomers announced the discovery of a genuinely remarkable planetary system surrounding a small, dim red dwarf star called TRAPPIST-1, located roughly 40 light-years from Earth. This modest little star, barely larger than the planet Jupiter, despite technically qualifying as a true star, turned out to host 7 separate planets, all of them remarkably close in size to Earth itself. An extraordinarily tight, tidy little planetary system with all 7 worlds squeezed into an orbital region smaller than the distance between our own Sun and the planet Mercury, a genuinely astonishing arrangement that surprised even the astronomers who discovered it. Because TRAPPIST-1 is so much smaller, dimmer and cooler than our own Sun, its habitable zone sits correspondingly close to the star, and remarkably, 3 or possibly 4 of its 7 planets appear to orbit within that zone, meaning they could, at the right distance, potentially support liquid water on their surfaces. This makes the TRAPPIST-1 system one of the single most compelling and heavily studied targets in the entire search for potentially habitable worlds beyond our own solar system. Try for a moment to picture what the sky might look like from the surface of one of these 7 worlds. Because all 7 planets are packed so closely together, orbiting so near their small dim star, an observer standing on any one of them would likely see several of its sibling planets hanging visibly in the sky at once, some appearing larger and closer than our own moon does from Earth, drifting slowly across a dim reddish daylight cast by their cool red dwarf sun. It is a genuinely strange and beautiful image, 7 worlds sharing something close to a single tight-knit sky. I want to be careful and honest here as well, since the excitement around TRAPPIST-1 can sometimes outpace what astronomers actually know for certain. Red dwarf stars like TRAPPIST-1 tend to be considerably more volatile in their youth than stars like our own Sun, prone to intense flares and bursts of high-energy radiation that could, over time, strip away a planet's atmosphere entirely, potentially undermining its habitability regardless of its otherwise favourable orbital position. Whether the TRAPPIST-1 planets have managed to hold onto meaningful atmospheres despite this challenging youth remains a genuinely open and actively studied question, one astronomers continue investigating using the James Webb Space Telescope's ability to examine these distant worlds in increasing detail. Asterisk, our nearest possible neighbour. Closer to home, in astronomical terms, lies another particularly compelling discovery. Proxima Centauri, the very nearest star to our own Sun, itself a faint red dwarf only about 4 light-years away, hosts a planet called Proxima Centauri b, discovered in 2016. This planet is remarkably close to Earth in mass, and it orbits within Proxima Centauri's habitable zone, meaning that, if it possesses an Earth-like atmosphere, conditions on its surface could theoretically support liquid water. Because Proxima Centauri is a notably active flare star, however, considerably more volatile than TRAPPIST-1, many astronomers remain cautious about its planet's true prospects for hosting complex life, since repeated flares could make maintaining a stable, protective atmosphere considerably more difficult over long stretches of time. 4 light-years might sound impossibly distant, and by any ordinary human measure it certainly is, farther than any spacecraft humanity has ever built, could realistically reach within a single lifetime. And yet, on the scale of the entire galaxy, 4 light-years is nothing at all, practically next door. Proxima Centauri b remains the closest known exoplanet to Earth, and it is precisely that closeness that keeps it near the very top of the list whenever astronomers discuss where to point their most sensitive instruments next. Asterisk. A world that briefly seemed to whisper of life. Perhaps no single exoplanet has generated more excitement and more careful scientific back and forth in recent years than a distant world called K-18b, located roughly 124 light-years away. This planet, somewhat larger than Earth and smaller than Neptune, a size category with no direct equivalent in our own solar system, orbits within the habitable zone of its small red dwarf host star, and observations using the James Webb Space Telescope revealed that its atmosphere contains water vapor, along with methane and carbon dioxide, findings that led some researchers to propose that K2-18b might be what scientists call a Haitian world, a hypothetical type of planet covered by a deep global ocean, wrapped in a thick hydrogen-rich atmosphere. There is a particular kind of quiet excitement that comes from imagining a world like that, a planet larger than our own, wrapped entirely in a single deep dark ocean, with no visible land anywhere, its surface hidden beneath clouds and a thick hydrogen-rich sky. It is the kind of image that captures the imagination, precisely because it feels, at once, both entirely alien and strangely familiar. An ocean, after all, is something we understand intimately here on Earth, even if this particular one belongs to a world more than 100 light-years away. In 2023, and then again in a more detailed announcement in April of 2025, a team of researchers reported tentative evidence within K2-18b's atmosphere of a molecule called dimethyl sulfide, a gas that, here on Earth, is produced almost exclusively by marine life, largely tiny ocean organisms called phytoplankton. This announcement made headlines around the world, and understandably so, since it represented one of the closest things astronomers had ever offered to direct atmospheric evidence potentially connected to life beyond our own planet, a claim striking enough to reach well beyond the usual audience of astronomy enthusiasts and into the wider public conversation. I want to walk through what happened next carefully, because I think it offers one of the clearest, most honest windows into how real scientific claims are actually tested. In the months following that 2025 announcement, multiple independent teams of researchers reanalyzed the same James Webb Space Telescope data, using different analytical methods and different assumptions about which molecules might be present. Several of these follow-up studies, published later in 2025, found that the original evidence for dimethyl sulfide did not hold up to closer scrutiny. Some researchers found the signal was better explained by other, entirely non-biological molecules, with similar chemical fingerprints. Others found that background noise within the instrument's data made any confident detection of dimethyl sulfide specifically difficult to justify at all. By later in 2025, a substantial portion of the scientific community studying this particular planet had concluded that the original claim did not yet meet the rigorous standard of evidence required to support a genuine biosignature detection. I share this story not to dampen your sense of wonder, but because I think it is a genuinely beautiful example of science working exactly as it should. An exciting, carefully qualified claim was made. Other scientists tested it rigorously, using independent methods, exactly as good science demands. And when the evidence did not hold up cleanly, the broader community updated its understanding accordingly, rather than clinging to the more exciting version of the story. As of the most recent research available, K2-18b remains a genuinely fascinating world, worthy of continued study, but the specific claim of detected biological activity there is not currently considered confirmed or well supported. NASA itself, when addressing the original announcement, was notably careful to clarify that even a confirmed detection of a single potential biosignature molecule would not, on its own, constitute proof of life, since multiple, independent, converging lines of evidence would likely be needed before any such claim could be considered genuinely established. It would be easy to hear this story and feel a little disappointed, as though a beautiful possibility quietly slipped away. But there is another way to hold it. Science rarely moves in a single, triumphant leap from question to answer. It moves in small, careful steps, claims tested, revised and tested again, each round bringing us a little closer to something we can genuinely trust. The story of K2-18b is not the story of a discovery that failed. it is the story of a discovery still patiently being made. Asterisk, what it would actually take to know for certain. This brings us gently to the current, honest state of the broader search for life beyond Earth. Despite more than 6,000 confirmed exoplanets, and despite genuinely exciting candidates like the TRAPPIST-1 system, Proxima Centauri b, and K2-18b, no exoplanet has yet provided evidence of life that the scientific community broadly considers confirmed. This is not a discouraging conclusion so much as an honest and important one, and it is worth resisting the urge to treat it as a disappointment. The tools currently available to astronomers, remarkable as they are, can only detect indirect atmospheric clues from these unimaginably distant worlds, faint chemical fingerprints buried within light that has travelled for decades, or centuries or longer, before ever reaching our telescopes. What would it actually take to move from a tentative, debated hint toward genuine, broadly accepted confidence? Scientists studying this question generally agree that no single molecule, however suggestive, would likely be enough on its own. Instead, researchers look for what is sometimes called a convergence of evidence, multiple independent chemical signals that, together, would be difficult to explain through any known non-biological process ideally confirmed by more than one telescope or research team working independently of one another. This is an intentionally high bar, and reaching it may take many more years of patient, careful observation, quite possibly stretching across multiple future generations of telescopes still waiting to be designed and launched. Asterisk. A universe that seems to favour company. Step back now and hold the full shape of this chapter gently in your mind. Just a few short decades ago, astronomers could not say with any certainty whether any other star in the universe hosted planets of its own. Today we know of more than 6,000 confirmed worlds circling other suns, and the underlying statistics suggest that planets may, in fact, be the rule rather than the exception, with astronomers now generally believing that most stars in our galaxy likely host at least one planet of their own. Some of these worlds sit in comfortable, temperate orbits, not unlike our own gentle position around the Sun. Others are scorched, frozen, or utterly alien in composition, unlike anything found anywhere in our own solar system. Whether or not life exists on any of these distant worlds remains genuinely unknown, an open question that may take many more years or decades of patient observation to answer with real confidence. But the sheer scale of what has already been discovered, thousands of worlds, and likely many billions more still waiting to be found, offers its own quiet, profound reassurance. Whatever else may be true about the universe we have explored together across this journey so far, one thing is now firmly established. Planets, it turns out, are not rare, precious exceptions scattered thinly through an empty cosmos. They are, by every indication our best instruments can offer, everywhere, waiting patiently in the dark for someone, somewhere, to finally notice their quiet, rhythmic light. There is something worth carrying with you into sleep tonight, in that thought. Somewhere out there, right now, countless worlds are quietly turning in their own private darkness, circling stars whose light left them years, decades, or centuries before it ever reached us. Some may be barren and silent. Others, perhaps, are not. We may never know for certain in our own lifetimes, but the simple fact that we are asking the question, carefully, patiently, and honestly, says something quietly hopeful about who we are. Beneath all of this searching, though, one particular mystery continues to shape and constrain nearly everything astronomers hope to someday discover about these distant worlds. An invisible presence that outweighs the ordinary matter making up every star, planet, and person we have described so far. And it is to that deep, patient mystery that we will turn our attention next. There's a strange fact sitting quietly underneath everything we've talked about so far tonight. The stars, the galaxies, the planets, the glowing clouds of gas drifting through the dark, all of it, everything we can actually see with a telescope, makes up only a small fraction of what's really out there. Most of the universe is invisible, not hidden behind something, not too far away to see, simply fundamentally invisible in a way that light itself cannot touch. Let yourself settle into that thought for a moment. You don't need to solve it. Nobody has fully solved it yet. You just need to rest here, in the dark, while we walk through what we do know and what we honestly don't. Let's begin close to home, in a quiet observatory, decades ago, with a puzzle that started small and grew into one of the largest open questions in modern physics. In the 1970s, an astronomer named Vera Rubin, working alongside the instrument designer Kent Ford, set out to measure something that seemed almost routine at the time: how fast stars orbit around the center of their galaxies. She focused much of her early work on the Andromeda galaxy, our nearest large galactic neighbor, using specialized instruments that let her measure faint shifts in the light coming from glowing clouds of gas within it. Those shifts, called Doppler shifts, work the same way a passing ambulance siren changes pitch as it moves toward you and then away. By carefully measuring them, Rubin could calculate exactly how fast different parts of the galaxy were spinning, at different distances from its center, based on the ordinary laws of gravity, and based on how much visible matter astronomers could actually see through a telescope. The outer regions of a galaxy should orbit more slowly than the inner regions, the same way outer planets in our solar system orbit the Sun more slowly than inner ones. Mercury, close to the Sun, races around in just 88 days. Neptune, far out at the edge, takes 165 years. This drop-off in orbital speed with distance is simple, predictable physics worked out centuries ago, and it applies just as cleanly to a spinning galaxy as it does to a solar system, at least according to the mathematics. If you know roughly where most of a galaxy's visible mass sits, mainly clustered toward its bright, glowing center, you can predict how quickly stars at any given distance should be moving. Astronomers expected galaxies to behave the same way planets do, tracing a gentle downward curve as you move outward from the crowded center toward the quiet, sparse edges. They didn't. When Rubin plotted her measurements, the line she expected to slope gently downward instead stayed almost perfectly flat. Stars far out at the edges of the Andromeda galaxy were moving just as fast as stars much closer to the center. By any ordinary accounting of visible matter, those outer stars should have been moving too quickly to stay bound to the galaxy at all. They should have been flung outward into open space long ago, scattered like water flying off a spinning wheel. But they weren't flying off. They stayed in their orbits, calm and steady, as if some additional unseen source of gravity was holding everything together. At first, many scientists were skeptical of these results, but Rubin kept going. Over the following years, she and her collaborators carefully measured the rotation curves of more than 75 spiral galaxies, and the pattern held again and again, galaxy after galaxy. It wasn't a fluke, and it wasn't an error in her instruments. Something was clearly wrong with the simple picture of a galaxy as nothing more than the stars and gas we can directly see. It's worth mentioning that Rubin wasn't actually the very first person to notice a version of this puzzle. Back in 1933, decades earlier, a Swiss astronomer named Fritz Zwicky had studied a cluster of galaxies called the Coma Cluster, and found that the galaxies within it were moving far too quickly to stay gravitationally bound together, based on their visible mass alone. Zwicky proposed that some kind of unseen matter, which he called dark matter in his own language, must be holding the cluster together. At the time, his idea was largely dismissed as too radical to take seriously. It would take Rubin's much more detailed, much more carefully repeated observations decades later to convince the wider scientific community that this invisible mass was real, and not just a strange quirk of one unusual galaxy cluster. By the early 1980s, dark matter had moved from a fringe idea into a central, accepted pillar of modern astrophysics, and the term itself is really just an honest description of our ignorance. We call it dark matter because we can detect its gravity, clearly and repeatedly, but we cannot see it, and we don't yet know exactly what it's made of. Since Rubin's original work, evidence for this unseen matter has piled up from multiple completely independent directions, which is part of why scientists take it so seriously today. One especially striking piece of evidence comes from something called gravitational lensing, According to Einstein's theory of general relativity, mass doesn't just create the ordinary pull of gravity we're used to, it actually bends the space around it, and light travelling near a massive object gets bent along with that space, following a curved path instead of a straight one. This means that if enough mass sits between us and a distant galaxy, that mass can act almost like a lens, bending and distorting the light from that distant galaxy on its way to us, sometimes smearing it into faint arcs or streaks. By carefully measuring exactly how much that light gets bent, astronomers can calculate precisely how much total mass is doing the bending, whether or not that mass gives off any light of its own. One of the clearest examples of this technique in action comes from a system astronomers call the Bullet Cluster, the aftermath of a collision between two enormous galaxy clusters that happened billions of years ago, roughly 3.7 billion light-years from Earth. When two galaxy clusters like this collide, most of their ordinary matter exists as hot, glowing gas, which can be observed directly using X-ray telescopes. This gas behaves a bit like air resistance during the collision, slowing down and piling up in the middle of the wreckage. But when astronomers used gravitational lensing to map out where most of the actual mass in the system was located, they found something striking. The bulk of the mass wasn't sitting with the slowed down gas in the middle at all. It had passed straight through the collision, mostly undisturbed, continuing onward with the individual galaxies on either side. Whatever this invisible mass was, it clearly wasn't behaving like the ordinary gas-based matter we can directly observe. It seemed to pass through the collision, almost as if the other galaxy cluster wasn't there at all, interacting with everything around it, almost exclusively through gravity. This observation, published in 2006, was described by the researchers themselves as offering some of the most direct proof of dark matter's existence available at the time. In fairness, since that original study, a small number of more recent papers have proposed alternative explanations for parts of what's observed in the Bullet Cluster, so it's not treated as an entirely closed, settled case by absolutely everyone in the field, but it remains one of the clearest, most frequently cited pieces of evidence that most of the mass in the universe genuinely isn't made of the same ordinary matter that makes up stars, planets, and us. Taken together, these different lines of evidence have let astronomers build up a rough picture of where dark matter actually sits, even without knowing exactly what it's made of. Rather than being spread perfectly evenly through space, dark matter appears to gather into enormous, roughly spherical clouds called halos, each one wrapped loosely around a galaxy or a cluster of galaxies, extending far beyond the visible edges of the stars and gas we can actually see. Our own Milky Way is thought to sit at the centre of one such halo, a vast, invisible cloud stretching out for hundreds of thousands of light years in every direction, dwarfing the comparatively thin, flat disk of visible stars embedded near its middle. In a very real sense, every galaxy we can see with a telescope is really just the bright glowing core of something much larger and mostly invisible, a small, luminous seed resting inside an enormous, quiet shell of matter we still can't directly observe. So what exactly is this invisible matter? Here, honestly, we have to admit that nobody knows for certain yet. This is one of the places where we need to be especially clear about the difference between what's confirmed and what remains an open, actively pursued question. What's confirmed is that something with real, measurable gravitational mass exists throughout the universe, well beyond what we can see directly. Multiple independent lines of evidence, rotation curves, gravitational lensing, and the fine details of the cosmic microwave background, the faint afterglow of the Big Bang that we described earlier in this journey, all point toward roughly the same conclusion: that this invisible matter makes up a huge share of the universe's total gravitational mass. Current measurements suggest ordinary matter. The atoms that make up stars, planets, and people accounts for only around 5% of the universe's total contents. Dark matter, meanwhile, is estimated to make up around 27%, more than 5 times as much as everything we can directly see and touch. What's not confirmed is exactly what dark matter is made of, at the level of individual particles. Several serious candidates have been proposed by physicists, and experiments are actively searching for them right now, deep underground. In laboratories specifically shielded from ordinary background radiation. One leading candidate is a hypothetical particle called a WIMP, short for weakly interacting massive particle, a particle that would rarely, if ever, interact with ordinary matter except through gravity and one other very weak force. The idea is that our entire solar system is constantly drifting through a faint, invisible fog of these particles as it orbits the galaxy, and that every so often one might collide gently with an ordinary atomic nucleus here on Earth, producing an almost imperceptibly small flicker of energy. Detectors built to catch this flicker are typically placed deep underground, sometimes in old mines, shielded by thousands of feet of solid rock, specifically to block out the ordinary cosmic radiation that would otherwise drown out such a faint signal. Another candidate, called the axon, would be far lighter than a WIMP, and would interact with matter in a slightly different way, primarily through its relationship with magnetic fields. In the presence of an extremely strong magnetic field, an axon is theorized to occasionally convert into a single particle of light, a photon, which specialized detectors are designed to catch. Researchers have built detectors specifically designed to catch faint signs of either possibility, patient instruments waiting quietly underground, or in specialized labs for the rarest of interactions, sometimes running continuously for years at a time, waiting for a single meaningful signal to rise above the background noise. So far, despite years of careful searching, no experiment has definitively detected a dark matter particle directly. It remains one of the genuinely open frontiers of physics, a search that has occupied brilliant scientists for decades without a confirmed answer yet. Let's sit with that uncertainty gently for a moment, because it's actually a remarkable thing to hold in your mind as you drift towards sleep. We are more confident that dark matter exists than we are about what it actually is. That might sound backwards, but it happens more often in science than people realize. We can be extremely confident that something is real, based on its effects, long before we understand its deeper nature. It's a little like knowing, with complete certainty, that wind exists, purely from watching leaves rustle and branches sway, long before anyone had worked out that wind is simply moving air. Now, dark matter isn't just a strange gravitational curiosity sitting quietly at the edges of galaxies. It appears to have played an absolutely essential role in building the universe's largest structures, stretching all the way back to its earliest moments. Very early in cosmic history, not long after the Big Bang, the universe was almost, but not quite, perfectly smooth and uniform. Extremely faint variations in density, tiny differences of roughly 1 part in 100,000, were imprinted throughout the early universe, and these variations are still visible today, preserved in the faint patterns of the cosmic microwave background. In regions that were just slightly denser than their surroundings, gravity had a little more material to work with, and it slowly began pulling even more matter inward, amplifying those tiny original differences over time. Here's where dark matter's particular nature becomes especially important. Ordinary matter in the early universe was still tightly coupled to light and radiation, unable to collapse and clump together efficiently until the universe had cooled and expanded considerably, roughly 380,000 years after the Big Bang, when the first atoms finally formed and light was able to travel freely for the first time. Dark matter, by contrast, doesn't interact with light at all. It was free to begin clumping together under gravity's pull far earlier, forming enormous invisible structures called halos, long before ordinary matter was ready to follow. These early dark matter halos essentially built the scaffolding of the universe first, a hidden gravitational framework quietly taking shape in the dark. Later, as the universe continued expanding and cooling, ordinary matter gradually fell into the gravitational wells that dark matter had already carved out, condensing into gas clouds, and eventually into the very first stars and galaxies. Without dark matter's head start, most cosmologists agree that the universe simply wouldn't have had enough time to build large, organized structures as quickly as it clearly did. The tiny density variations imprinted in the early universe, differences of roughly 1 part in 100,000, are simply too small and too weak, acting through the pull of ordinary matter alone, to explain how quickly galaxies and galaxy clusters actually assembled themselves. Dark matter, unburdened by its lack of interaction with light, effectively gave the process a running start, allowing gravity to begin its slow, patient work of gathering material together far earlier than would otherwise have been possible. Galaxies, galaxy clusters, and the vast filaments and voids that make up what's sometimes called the cosmic web all appear to trace back to this same underlying dark matter scaffolding, an invisible framework that ordinary, glowing matter later settled into, the way frost settles into the fine grooves of a window pane, following a pattern that was already there. When astronomers build large-scale computer simulations of the universe, feeding in the known properties of dark matter and letting gravity run its course over billions of simulated years, the resulting patterns of filaments, clusters, and voids closely match what telescopes actually observe when they map the real distribution of galaxies across the sky. That agreement between quiet, patient simulation and messy, complicated observation is one of the strongest pieces of evidence that dark matter's gravitational scaffolding really did shape the universe we see today. Now let's turn to the second great mystery of tonight's chapter, one that's every bit as strange, and in some ways even more surprising than dark matter itself. For most of the 20th century, cosmologists generally assumed that the expansion of the universe, which we've talked about earlier in this journey, should be gradually slowing down over time. This assumption made intuitive sense. Gravity pulls things together. All of the matter in the universe should be exerting a constant gravitational drag on the overall expansion, gently applying the brakes, the way friction slows down a ball rolling across a floor. The only real question astronomers thought was how much the expansion was slowing, and whether it would eventually slow enough to reverse entirely, or simply continue decelerating forever. In 1998, 2 independent teams of astronomers, one called the Supernova Cosmology Project, the other the High Z Supernova Search Team, set out to measure exactly how much the expansion had been slowing down. Both teams used a very specific tool for this measurement, a particular kind of exploding star called a Type Ia supernova, the same kind of explosion we described earlier when we talked about the deaths of stars. These explosions are especially useful for this purpose because they tend to release almost exactly the same amount of energy every time they occur, making them what astronomers call standard candles. Reliable enough that comparing how bright one appears from Earth reveals how far away it actually is. It works a little like judging distance from a lighthouse at night. If you already know roughly how bright a particular lighthouse's beam truly is, up close, you can estimate how far away you must be, simply by how dim that same beam appears from where you're standing, by carefully measuring the distances and the redshifts, meaning how much their light had stretched due to cosmic expansion, of dozens of these distant exploding stars. Both teams expected to confirm a slowly decelerating universe. Instead, both teams found something nobody had predicted. The universe wasn't slowing down at all. It was speeding up. Distant supernovae appeared dimmer, and therefore farther away than they should have been if the expansion were merely coasting along at a constant rate, or gradually decelerating under gravity's pull. The only way to explain the extra distance was if the expansion of the universe had been accelerating for billions of years. This discovery, confirmed independently by 2 separate research teams working with different data, absolutely upended the standard assumptions cosmologists had held for decades. It was significant enough that it earned 3 of the researchers involved the Nobel Prize in Physics in 2011. To explain what was driving this unexpected acceleration, scientists introduced a new term for a phenomenon nobody fully understands: dark energy. Just like dark matter, the name dark energy is really just an honest label for something we can measure the effects of, but cannot yet explain at a deeper level. Whatever dark energy actually is, it appears to be acting like a kind of steady, gentle outward pressure, embedded directly into the fabric of space itself, gradually pushing everything apart a little faster with each passing moment. And its scale is genuinely staggering. Based on the most precise measurements currently available, dark energy appears to make up somewhere around 68 to 70% of the total energy content of the entire universe, making it, by a wide margin, the single largest component of everything that exists. Ordinary matter, the stuff of stars and planets and people, and dark matter combined, still add up to less than a third of the universe's total contents. We live, it turns out, in a universe overwhelmingly dominated by something we still don't fully understand. One of the strangest properties of dark energy, and one that sets it apart clearly from ordinary matter or even dark matter, is how it behaves as the universe expands. Ordinary matter becomes steadily more diluted as space grows larger, the same amount of material spread across an ever-increasing volume, the way a fixed number of scattered seeds becomes sparser as a field grows wider. Dark matter dilutes in much the same way, since it's still a form of matter, simply one that doesn't interact with light. Dark energy doesn't dilute this way at all. As best as current measurements can tell, its density stays essentially constant, even as space itself keeps expanding around it. This means that, as the universe grows, the total amount of dark energy actually increases, simply because there's more space for it to fill. And since dark energy is what's driving the expansion in the first place, this creates a kind of quiet self-reinforcing cycle. More space allows for more dark energy, and more dark energy drives faster expansion, which in turn creates still more space, on, gently accelerating, with no obvious end built into the mechanism itself. Scientists are actively working to determine exactly how consistent dark energy's behavior really is over cosmic time. Recent large-scale efforts, including a major study called the Dark Energy Survey, have used thousands of distant supernovae gathered over years of careful observation to test whether the density of dark energy has truly remained perfectly constant throughout cosmic history, or whether it might have varied subtly over billions of years. So far, the results remain broadly consistent with dark energy behaving as a constant, unchanging quantity, sometimes called a cosmological constant, though the data doesn't yet rule out the possibility of small variations over time. As one of the researchers leading this work put it plainly, this remains genuinely unknown territory, without a clear theoretical framework, yet connecting dark energy to the rest of known physics. It's worth being completely honest about just how much remains uncertain here, since a trustworthy account of the universe has to include its unanswered questions alongside its answered ones. We don't know at a fundamental level what dark matter particles actually are, despite decades of dedicated searching. We don't know what dark energy fundamentally is, only how it appears to behave on the very largest scales we can measure. We don't fully understand why dark energy's density would happen to be constant, or nearly so, though several theoretical frameworks have been proposed to try to explain it, and we don't yet have a single unified theory that successfully connects dark matter, dark energy, and the rest of established physics into one coherent picture. These aren't small or minor gaps sitting at the edges of our understanding. Dark matter and dark energy together make up around 95% of the total contents of the universe. In a very real sense, we've spent the better part of this entire journey through cosmic history describing the smallest slice of what actually exists, roughly 5%, while the overwhelming majority of the universe remains, for now, a quiet and patient mystery. There's something worth sitting with in that thought, as you drift further towards sleep tonight. The universe we can see, the stars, the galaxies, the vast glowing structures we've spent this whole journey exploring, is genuinely real and genuinely remarkable. But it's also, in the most literal sense, only a small fraction of the whole picture. Most of what surrounds us, filling the space between every galaxy, threading invisibly through every cluster, gently but relentlessly stretching the universe wider with each passing moment, remains unseen, unnamed, at any deeper level, and largely unexplained. Think about what that actually means for a moment, lying quietly in the dark. Every star you've ever looked up and noticed, every galaxy any telescope has ever photographed, every glowing nebula, and every distant ancient quasar, all of it together, adds up to only a small sliver of everything that exists. The rest, the overwhelming majority, moves through the cosmos completely unseen, felt only through its gravity, or through the slow, steady way it stretches the space between everything else apart. We've spent this entire journey walking through the visible history of the cosmos, the light, the matter, the stars living and dying, and it turns out we've only been describing the smallest, brightest corner of a much larger, mostly silent room. And this quiet, invisible tug-of-war between dark matter's gravity, pulling things together, and dark energy's steady pressure, pushing everything apart, doesn't just describe where the universe has been. It also shapes where the universe is headed. The balance between these two vast, unseen forces, one gathering matter into galaxies and clusters, the other steadily widening the empty space between them, will ultimately determine what becomes of everything we've talked about tonight. Every star, every galaxy, every quiet corner of the cosmos we've drifted through together. What that balance ultimately means for the very far future of the universe is a story we'll turn to next, as we let this long, patient history of the cosmos finally settle toward its own distant, unhurried horizon. We've travelled a long way together tonight, from the first fraction of a second after the Big Bang, through the birth of stars, the deaths of stars, the growth of galaxies, and the strange unseen forces that quietly hold everything together and slowly pull it apart. Now, at the very end of this journey, there's only one direction left to look: forward. Not toward tomorrow, or next year, or even the next 1,000 years, but toward the almost unthinkable stretch of time still waiting ahead of us, long after everything familiar has faded away. This is the last chapter of our story tonight, and it moves slowly, the way the universe itself moves. There's nothing to brace for. Just let your eyes stay closed, and let's drift together toward the far, quiet edge of time. Right now, the universe is still young, still bright, still busy. It's a little over 13.8 billion years old, and stars are still forming inside countless galaxies, glowing steadily, filling the dark with light. But this bright, active period doesn't last forever. Astronomers have a name for the current era of cosmic history. They call it the stelliferous era, a word that simply means the age of stars. And like every era before it, it will eventually come to an end. It helps to think of the universe's entire future as a series of long, slow chapters, each one stretching for a length of time almost impossible to hold in the mind. We are living inside the very first of these chapters right now, an era defined by starlight, by warmth, by the slow, patient business of stars being born, living out their lives, and dying over and over, galaxy after galaxy. What follows this chapter, though, unfolds far more slowly, and far more quietly, than anything we've talked about so far tonight, stretching across timescales so large that human numbers begin to feel almost decorative, more a gesture toward the scale involved than a truly graspable measurement. Let's start there, with the stars themselves, and follow their story forward across a span of time so vast that ordinary numbers start to lose their meaning. Right now, galaxies are full of gas and dust, the raw material needed to build new stars. But that material isn't infinite. Every time a new star forms, a little bit of that raw material gets locked away. Some of it eventually returned to space when stars die, but never quite as much as went in. Over unimaginably long stretches of time, this slow depletion adds up. Astronomers estimate that star formation across the universe will likely wind down somewhere between 1 trillion and 100 trillion years from now, as galaxies gradually run out of the fresh, cold gas clouds needed to build anything new. The stars that last the longest through this slow fade are the smallest ones, called red dwarfs. These are dim, cool stars, far less massive than our Sun, and they burn through their fuel with remarkable patience. While a massive star might burn out in just a few million years, and a sun-like star lasts around 10 billion years, the smallest, faintest red dwarfs are expected to keep shining for somewhere between 1 and 20 trillion years. To put that in perspective, that's up to roughly 1,000 times longer than the current age of the entire universe. Red dwarfs make up the vast majority of stars in our galaxy today. Roughly 3 out of every 4 stars in the Milky Way, and in the far future, they'll be the last stars left glowing in the dark, faint red embers scattered thinly across galaxies that have otherwise gone quiet. Our own sun, meanwhile, follows a very different and much shorter path than these small patient stars. It will continue burning steadily for roughly another 5 billion years before swelling into a red giant, its outer layers eventually drifting away into space, leaving behind a slowly cooling white dwarf where its core once was. That's a story we've touched on earlier in this journey, and it will unfold long before most of what we're describing tonight even begins. In cosmic terms, our Sun is a relatively short-lived star, destined to fade only a small fraction of the way into the long story we're telling right now. While all of this unfolds, galaxies themselves won't stay still either. Over the coming billions of years, galaxies are expected to continue merging with their neighbours, gradually combining into larger and larger structures. It helps to picture it a little like building a sandcastle at the edge of the shore, where each new handful of sand makes the structure a bit bigger, until eventually smaller mounds are simply absorbed into one larger one. Our own Milky Way is expected to merge with the nearby Andromeda galaxy, and over time, entire local groups and clusters of galaxies are expected to gradually collapse inward, merging together into single, enormous elliptical galaxies. Orderly spiral disks, like the one we live inside right now, with their calm, rotating arms of stars, will fold together into rounder, more chaotic, disorganized shapes, the graceful spiral structure lost in the slow violence of repeated collisions. Meanwhile, the accelerating expansion of the universe, the same expansion we discussed earlier when talking about dark energy, will keep pulling everything outside our immediate cosmic neighborhood farther and farther away. Eventually, galaxies beyond our local group are expected to become so distant, and so quickly, that their light could no longer reach us at all. For an unimaginably long stretch of the far future, the night sky may show nothing but a single, dim, reddish elliptical galaxy, the merged remains of everything once nearby, sitting alone in an otherwise empty, silent dark. Any future observer looking outward from that lone galaxy would see nothing beyond it. No other galaxies, no evidence in the sky itself that the universe was ever anything but that one quiet island of stars, drifting alone in an endless black. Eventually, even the red dwarfs will use up their fuel. Once the last red dwarf finally goes dark, somewhere on the order of 100 trillion years from now, the era of shining stars will be over completely. What remains behind will be a strange, quiet collection of stellar corpses. White dwarfs, the slowly cooling cores left behind by stars like our own Sun, neutron stars, and black holes, along with failed stars called brown dwarfs that never gathered quite enough mass to ignite in the first place. Astronomers call this next stretch of cosmic history the degenerate era, named for the dense, exotic states of matter that make up these leftover objects. It's worth pausing here, because this era isn't entirely silent. Every so often, in this cold, dark future, 2 white dwarfs might drift close enough together to collide or merge, pulled together across unimaginable distances and stretches of time by the same patient gravity that shaped galaxies long before. If their combined mass crosses a certain threshold, roughly 1.4 times the mass of our Sun, that collision can trigger a sudden, brilliant supernova explosion, a bright flash cutting briefly through the darkness before fading again. These occasional flickers of light, growing rarer and rarer as time goes on, may be some of the last true starlight the universe ever produces. Little by little, even these rare flashes will become less frequent, as the raw material for them slowly runs out too, the collisions growing more and more infrequent as the universe continues to stretch and thin. Beyond these occasional bright flashes, The degenerate era is expected to be an extraordinarily dim, quiet stretch of cosmic history, populated mostly by cold, dark stellar remnants drifting slowly through mostly empty space, their once brilliant light reduced to only a faint residual glow, or none at all. Over even longer stretches of time, current theoretical work, and this part is genuinely still an area of open research rather than settled fact, suggests that even white dwarfs themselves might not last forever. A white dwarf, once it finishes forming, simply radiates away its leftover heat, slowly cooling over enormous stretches of time. Some physicists predict that these dense stellar remnants could very slowly transform into something even colder and darker, sometimes called black dwarfs, once they've radiated away essentially all of their remaining heat and light. Through extraordinarily slow processes involving the eventual settling of their internal matter. Estimates for how long this transformation might take are staggering, on the order of thousands of trillions of years or more. Times so far beyond the current age of the universe that they're difficult to hold in the mind as anything other than an abstract idea. As it stands today, since the universe hasn't existed nearly long enough for any white dwarf to complete this cooling process, not a single true black dwarf is thought to exist anywhere in the universe yet. Every white dwarf that has ever formed is, in a sense, still young, still slowly releasing the last of its ancient warmth into the surrounding dark. Now let's turn to something even stranger. What eventually happens to black holes themselves? Earlier in our journey, we all talked about black holes as objects so dense that nothing, not even light, can escape their gravity. But in the 1970s, the physicist Stephen Hawking proposed something surprising. Black holes, it turns out, aren't permanently black after all. Through a subtle quantum effect happening right at the edge of a black hole's boundary, they slowly leak a faint stream of particles outward, gradually losing mass over time, in a process now called Hawking radiation. This radiation has never been directly observed, since it would be extraordinarily faint for any black hole we currently know of. But the underlying theoretical physics is widely respected and considered a serious, well-supported prediction. The catch is the sheer scale of time involved. For a black hole with the mass of our own Sun, this process would take roughly 10 to the power of 67 years to complete. A number so large it's easier to think of as a 1 followed by 67 zeros than to try to picture directly. Larger black holes, holding more mass, and therefore more energy to radiate away, actually take even longer to evaporate than smaller ones, the opposite of what intuition might suggest, since a bigger black hole has a cooler effective temperature, and therefore leaks its energy away far more slowly and gradually. For the largest supermassive black holes, the ones sitting at the centres of galaxies, some estimates put full evaporation at around 10 to the power of 98 years. More recent theoretical work, published by researchers at Radboud University in 2023, and expanded further afterward, has suggested that this evaporation process might actually apply more broadly than Hawking's original prediction, and might happen somewhat faster than earlier estimates for some objects, potentially bringing the evaporation of the last black holes down to around 10 to the power of 78 years by their calculations. It's important to be clear that this is still an active, evolving area of theoretical physics, not a fully settled result, and different research groups continue to refine these numbers. But either way, whether it's 10 to the power of 78 years or 10 to the power of 98 years, we're talking about timescales so enormous that the entire history of our universe, so far 13.8 billion years, doesn't even register as a meaningful fraction of it. It would be like comparing the width of a single atom to the entire distance across our solar system. Once even the largest black holes have fully evaporated, releasing their remaining energy as one final, faint burst of radiation, there won't be much left in the universe at all. No stars, no stellar remnants, no black holes. Just an extremely thin, cold scattering of particles and photons drifting through an almost perfectly empty, ever-expanding darkness. Astronomers sometimes refer to this final quiet stretch of cosmic time as the Dark Era, a fitting name for a universe that has finally run out of anything resembling structure, warmth or light, left to drift in near-perfect stillness for a length of time that dwarfs everything that came before it, combined. This brings us to the deepest, most fundamental question about the far future of the universe. What happens after that? Here, we have to be especially careful to separate what's well supported by current evidence from what remains genuinely speculative, since different possible endings have been proposed, and they don't all carry equal scientific weight. The scenario currently favoured by most cosmologists, based on everything we've discussed about dark energy and the accelerating expansion of the universe, is something called heat death, sometimes also referred to as the Big Chill or the Big Freeze. This isn't a dramatic, explosive ending. It's closer to the opposite, a long, gradual settling into stillness. Heat death is rooted in one of the most fundamental laws of physics, the second law of thermodynamics, which states that entropy, a measure of disorder, or the spreading out of usable energy, always tends to increase over time in an isolated system. This idea was first developed in the 1850s by physicists studying the behaviour of heat engines here on Earth, long before anyone thought to apply it to the entire universe. It's a simple, familiar pattern, really. A hot cup of tea left on a table will always cool down to match the temperature of the room around it, never the other way around, since heat naturally flows from warmer places to cooler ones, spreading out until everything reaches the same, even temperature. Applied to the entire universe, this same simple principle suggests that energy will eventually spread out so evenly, and temperatures will become so uniform throughout space, that no meaningful difference remains anywhere to do any kind of work. No stars burning brighter than their surroundings, no temperature differences to drive any process at all, just a vast, cold, motionless silence spread evenly across an unimaginably large, ever-expanding universe. It's worth noting that heat death doesn't necessarily mean the temperature would drop to an exact absolute zero. Some models suggest that if the density of dark energy remains constant, the temperature might level off at an extremely low but non-zero value instead. Either way, the practical result would be the same. A universe with no usable energy left anywhere, forever, a place where change itself, in any meaningful sense, has simply stopped happening. There's a second, more violent hypothesis that depends entirely on the exact nature of dark energy, something scientists still don't fully understand. If dark energy isn't perfectly constant over time, but instead grows stronger and stronger as the universe expands, a scenario sometimes called phantom energy, the result could be something scientists call the Big Rip. In this hypothesis, the accelerating expansion of the universe wouldn't just continue steadily, it would keep intensifying, faster and faster, in a runaway feedback loop, one that some researchers have modelled as unfolding with a strange, almost inverted order compared to how the universe first came together. Rather than galaxies gently drifting apart, entire clusters of galaxies would eventually be torn loose from one another, their mutual gravity no longer strong enough to resist the accelerating stretch of space between them. From there, the process would only speed up. Individual galaxies would come apart next, then star systems, then planets themselves would be pulled apart from their parent stars, and finally, in the very last moments before the hypothesized end, the expansion would grow strong enough to overpower even the forces holding individual atoms together, dissolving matter itself down to its most basic components in one final, catastrophic instant. It's important to stress that the Big Rip is a hypothesis that depends on a specific, currently unconfirmed property of dark energy. Current measurements, including recent, very precise studies using large samples of distant supernovae, remain broadly consistent with dark energy behaving as a simple, unchanging constant, though scientists continue to test this carefully, since even small deviations could have enormous consequences over the deep future. Some very recent large survey data, still being carefully studied and debated within the scientific community as of this description, has hinted that dark energy's strength might possibly change slightly over cosmic time, though this finding is preliminary and requires much more confirmation before it could meaningfully shift the balance between these competing possible futures. If a Big Rip scenario were confirmed to be underway, some early theoretical estimates have suggested it could unfold within tens of billions of years, though this figure depends heavily on assumptions that remain unverified. And more moderate versions of the underlying phantom energy idea would push any such ending much further into the future. There's a third hypothesis as well, one that stands in almost complete contrast to the other two. This is called the Big Crunch, and it imagines the opposite fate entirely. Instead of expanding forever, the universe would eventually stop expanding, reverse course, and begin collapsing back in on itself, gravity finally winning out over the outward push of expansion, drawing everything back together into an extremely hot, dense state, in some ways mirroring the very beginning of the universe, but in reverse. Under this hypothesis, galaxies that have spent billions of years drifting apart would slowly begin drawing back together. Instead, first gently then, with increasing speed, until the entire observable universe eventually collapsed back down toward an extremely small, extremely hot point, not unlike the conditions believed to have existed at the very start of the Big Bang itself. For the Big Crunch to happen, the universe would need to contain enough total matter and energy for gravity to eventually overcome the expansion entirely, reversing course rather than continuing outward forever. Based on current measurements, this scenario looks unlikely. The observed density of matter in the universe appears to fall well short of what would be needed to reverse the expansion, generally estimated at somewhere between 10 and 40% of the density that would actually be required. And the discovery of accelerating expansion, driven by dark energy, makes a future collapse seem even less probable under our current understanding, since dark energy actively works against the kind of gravitational pull a collapse would require. Most cosmologists today consider heat death, a slow, cold fading away, to be the most likely outcome. Based on everything we currently know, though it's worth remembering that our understanding of dark energy is still incomplete, and future observations could still shift the picture in ways we can't fully predict yet. It's a genuinely open area of ongoing research, and part of what makes cosmology, even at this very advanced and careful stage, still such a humbling and unfinished science. It's genuinely remarkable, when you stop to think about it, that human beings, standing on a small planet, orbiting an ordinary star in an ordinary galaxy, have been able to reason our way toward these questions at all. We've measured the age of the universe. We've traced the life cycles of stars from birth to death. We've detected ripples in space and time itself, and mapped the faint, ancient afterglow of the Big Bang. And using nothing more than careful observation, patient mathematics, and an enormous amount of collective curiosity, we've managed to sketch out plausible outlines of what might happen to everything, trillions upon trillions of years from now, long after every star we can currently see has gone dark. Let's take a quiet moment to think about our own place inside all of this vast stretch of time, because it puts something in genuine perspective. The universe is roughly 13.8 billion years old. Human civilization, in any recognizable form, stretches back only a few thousand years. Even our entire species, going back to its earliest origins, only accounts for a few 100,000 years, an almost immeasurably small sliver compared to the age of the universe itself. And when you place that same sliver against the far future we've just described, trillions upon trillions of years still waiting ahead, our own existence becomes even harder to meaningfully measure. If you compress the entire expected lifespan of the universe, from the Big Bang all the way through the eventual evaporation of the last black hole, into a single calendar year, all of human history so far would occupy a stretch of time far too brief to even register as a single, visible tick of the clock. Even the entire span of time in which stars will still be forming, the stelliferous era we're living through right now, would only occupy the very earliest sliver of that same calendar year, with almost the entire remaining year given over to the quiet, cooling stretch of the degenerate era, and whatever follows after it. And yet, here we are anyway, a brief, curious, thinking species, alive during an early, brilliant, relatively narrow window of cosmic time when stars are still abundant, when galaxies are still full of light, when the night sky is still genuinely worth looking up at. We happen to exist during the stelliferous era, the age of stars, a period some cosmologists have pointed out is actually a fairly early chapter in the universe's total story, given how much longer the quieter eras that follow are expected to stretch on for. In some strange way, tonight's entire, sprawling journey through the history of the cosmos, from the Big Bang, through the birth and death of stars, through galaxies and black holes, and the vast unseen scaffolding of dark matter, has really been the story of a very fortunate moment, a moment when the universe happens to be bright enough, warm enough, and structured enough for something like curiosity, and something like you lying quietly in the dark right now, letting your thoughts drift along with all of it, to exist at all. Consider for a moment everything that had to happen first, just for tonight to be possible. A star, long before our sun ever existed, had to live and die, scattering the carbon and oxygen and calcium that would eventually become part of you. Billions of years of gravity, patiently gathering gas and dust into galaxies, stars and planets. A quiet rocky world, settled at just the right distance from just the right kind of star, warm enough for water to stay liquid on its surface. And then, more billions of years of simple chemistry slowly becoming complex chemistry, and complex chemistry slowly, gradually, becoming something that could think and wonder, and eventually build telescopes powerful enough to look all the way back toward the beginning of everything, and to imagine, with real confidence, how it might all eventually end. That's a small thing. It's not something owed to us, or guaranteed by the universe in any deep sense. It's simply remarkably true for this particular stretch of cosmic time, in this particular corner of a very large and very old universe. The stars above you tonight, however many trillions of years they still have left to shine, are part of the same unbroken story that stretches all the way back to a single unimaginably hot and dense point, nearly 14 billion years ago, and that will keep unfolding, slowly and patiently, long after every one of us and every star we can currently see has faded quietly into the dark. If tonight's journey through the history of the cosmos helped you drift off, or simply gave you something quiet and vast to rest your mind on, consider leaving a like and subscribing to This Is Space. It costs nothing, takes only a moment, and it genuinely helps this small channel keep exploring the universe together, one gentle, curious night at a time. Thank you for spending these hours with us, out here among the stars, drifting quietly through billions of years of cosmic history together. Sleep well, and we'll see you in the next journey.